Namaskar. A very good morning to one and all. I'm Sudarshan Fani from ARCI, Hyderabad, and partly associated with the University of Hyderabad. And it's my absolute pleasure this morning to invite everybody to this workshop on recent advances in additive manufacturing. This workshop is being organized under the auspices of the Institute of Eminence, University of Hyderabad. Industry 4.0 is something that we all hear in the manufacturing sector these days, and additive manufacturing-based technologies are an important ingredient to meet some of the lofty goals that have been set in that regard. As you all know, the government of India has taken special interest in promoting the manufacturing sector, and today's event is a small but significant effort in that direction. And one of the big players in metal additive manufacturing in India was late Dr. Sri G. Padmanabham, former director of ARCI. He was a visionary who believed strongly in industry and academia interaction. And today's event, in some ways, is a culmination of his pioneering efforts to bring state-of-the-art additive technologies to ARCI, and also very closely engaging with the School of Engineering Sciences and Technology at the university through the master's program in manufacturing. At this juncture, I'd like to everybody to pay a moment of homage to him and just think about him, because this event in some ways is a culmination of his early efforts in interacting with the university. Thank you. Today's workshop is going to cover a wide range of topics in additive manufacturing, starting from the core aspects of the technology, the metallurgical aspects, the various applications from the industries. And in fact, from the program sheet, you can see we have a great set of distinguished speakers covering the industry and the academia. We have live demonstrations, we have expert panel discussions, and of course, great food and unmatched university ambience. So I would like to request your undivided attention all through the program, especially the young minds that I see here. Please do take full advantage of the presence of a lot of experts and actively engage in the event all through the day. So without much delay, let's go ahead and get started. I'd like to begin by inviting Professor Jagdishwar Rao, Vice Chancellor, University of Hyderabad, to come on to the stage. May I now request Dr. Tata Narsingh Rao, Director, ARCI, and Adjunct Professor, IIT Hyderabad, to come on to the stage. I'd like to now request Dr. Ghansham Krishna, Director, IOE, University of Hyderabad, to come on to the stage, please. I'd like to now request Dr. Professor Dibakar Das, Dean, School of Engineering Sciences and Technology, to come on to the stage. May I now request Professor Dibakar Das, Dean, to present the welcome address.
Very good morning to all of you. Honorable Vice Chancellor Professor Vijay Rao, Director ARCI Dr. Tata Narsingh Rao, Professor SEST and Director Institute of Eminence Director Professor M. Ghansham Krishna, delegates from the industry, faculties, colleagues from the university, outside the university, from other educational institute, dear students. On behalf of School of Engineering Sciences and Technology, I extend a very warm welcome to all of you. I thank the conveners of this workshop, Professor Gautam, Dr. Sudarshan, Dr. Guru Raj, for organizing this beautiful workshop, which is very, very relevant and timely, I should say. Let me give you a very brief about the School of Engineering Sciences and Technology. It was established in the academic year 2008 and 9 with an objective to impart research-oriented higher education. Since the inception of the school has been able to secure almost more than 20 crores of research funding from external agencies. School have been able to secure 6th very prestigious Prime Minister's Research Fellowship. The faculties of the school have been able to publish more than 450 publications in journals with good impact factor. The alumni of the schools are placed in various industries and higher educational institutes in the nation and abroad. So currently the school runs 5 programs. MTechs in Materials Engineering, Nanoscience and Technology, Manufacturing Science and Engineering, and PhD in Materials Engineering and Nanoscience and Technology. So the entire show is run by only 8 faculties. So they are doing excellent job. Once again, I welcome all of you in this workshop, and I'm sure you will enjoy and you will be benefited from the day-long deliberations on additive manufacturing. Thank you.
Thank you, Professor Das. I'd like to now request the Vice Chancellor to address the gathering.
Why is this on? Any reason? Let's switch it on. I was just wondering, too many lights are not good, for me.
Wanted to illuminate your face.
Good morning to all of you. Firstly, my esteemed guest here, Tata Narsingh Rao Garu, and my own colleagues, Dean SEST and Director IOE, and Professor Gautam, who has been the main culprit for this meeting. Good culprit. And all other invitees as well as our own university colleagues here. Additive manufacturing is a very, very contemporary topic. I'm not an engineer, but I do appreciate many areas of engineering because it's very difficult to live without engineering. It's almost impossible to live without appreciating engineering these days. So therefore, most of us are familiar with this part of engineering and the importance of this engineering. In that sense, I think this one-day deliberation, this is called workshop, not a conference. So workshop, this one-day workshop is extremely relevant for students to learn, for young researchers to think about this area very deeply and plan accordingly. When we look at this area of additive manufacturing, immediately you realize that this area has been somewhat mistakenly overtaken by a term called 3D printing. In some sense, to me, my personal view, 3D printing somewhat trivializes the area per se. It's not just printing, it's an engineering science. So therefore, I feel that unfortunately that printing has come in and has become much more of a popular parlance than additive manufacturing engineering. So that's one correction that I make in my mind. When I think about additive manufacturing engineering as an engineering science, it's an old science actually. My body is made up by additive manufacturing actually. My body is actually printed by evolutionary forces. In some, a layer by layer, there is a blueprint in my genome that specifies that it has to be this way, and the blueprint is unfolded by adding material layer by layer in a very impeccable manner. But remember, there is also subtractive manufacturing in the bodybuilding. I'll give you the best example. This hand was developed initially as a web, continuous web. It has been made into digital fingers by removing this part. the gaps have been removed areas. And these areas have been removed by what is called program killing. So this is additive manufacturing plus subtractive manufacturing. It's an interesting combination. In fact, most designs have to follow this dynamic combination. There is nothing that you go one way. Of course, this is engineering, this is not just biology. We have to, in the university system, we have to train large number of students because India doesn't have enough of trained manpower in this technology, unfortunately. As a university system, we should be training large number of students because this technology allows us cost-effective way of scaling up many manufacturing processes, from large aircrafts to small robots. All these are covered in this area called additive manufacturing, where cost has become a very important parameter, and the automation, the algorithms, the AI technology has robustly come in and has lowered the cost and scaling very efficiently. Several orders of magnitude cost lowering has been done in some areas because of AI-based intelligent simulations, where you don't have to now make mistakes. You go straight into precise manufacturing in first cycle itself. Earlier, we used to do manufacturing by constant evolution. Now there is precise manufacturing at time zero, in some sense. So it's a very interesting, challenging area. We should be training large number of young manpower for this technology, for the world, in fact. And again, we should be developing tools for this. Printers, we don't have enough printers. We still do not have enough smart materials in the country. Although we have some resources, we strategically, we still do not own very important resources. The time is not completely lost, I believe. Time window is still there, but we are running out of that time window, is what I hear from experts. So strategic materials, strategic printers, and important highly trained manpower. These are the three requirements. And I hope this workshop will spur some kind of nucleation towards this. We should be doing this for the country and therefore for the globe. Because ultimately it is India that is going to be serving the globe, whether one likes it or not. In the years to come, in few decades to come, the whole world will very, very acutely start looking at India. Can you give us? What have you done? So this is really the time for us to strategize and position ourselves at a very important vantage point of view. I really appreciate this effort. We need to do more of these efforts in important areas. There are many other important areas also. Engineering school should take a lead and partner with IIT, ARCI. Hyderabad is such a makkah for all kinds of interesting activities. We should be doing a lot more than what we are doing. We have been doing some of late. Kansham Garu also knows. But more has to be done. So that, if we increase the encounter frequency, some interesting collisions will take place. If you don't increase the collision frequency, then you won't have productive collisions. Productive collisions is a function of collision frequency. So increase the frequency is my request. Namaste.
Thank you, sir, for an excellent address, and I hope we take your points and hope the country is well and truly on its path to getting a preeminent state at the global stage. Thank you, sir. May I now request Dr. Tatana Singh Rao, guest of honor, to address the gathering, please.
Good morning, everyone. Thank you, Gautam, and all my colleagues, and thank you so much, sir, Mr. Vice Chancellor, for giving this opportunity. And then I feel honored to sit beside you, because we know about you a long time when you are an ISER, because Professor Ganesh, we know each other a long time, and then I got an opportunity. And I was also happy when I met you in Bangalore, and we spent enough time. So, sir, it's a very good example you gave. That is, the human being is a very well designed and engineered product with additive and subtractive manufacturing. I strongly believe that one. And then now I start thinking. No, but this actually one has to think, because we always think only at material powders and then additive manufacturing and some CAD files and all. But we have to think in different angles. That's what he says, the frequency of collisions, even not just among the material scientists, but physicists, even biomedical people. Now we are working with a lot of doctors in Bangalore, especially for maxillofacial, where it is patient-specific implants are required exclusively from biomedical additive manufacturing. And I also agree with you, the 3D printing is very common word, what is used. And then every nook and corner, you can see that they just 3D print whatever shape, those are all plastics, 3D printed plastics. That's why I tell our people that let us don't call 3D printing, better to stick to additive manufacturing or rapid prototyping. Use some advanced words so that people will understand differently. Otherwise, it will be given a low value for the topic what we're talking. You just call it 3D printing, right? Because a lot of doctors, when I was interacting with maxillofacial doctor, he says 3D printing we are doing because he make whole skull with a 3D printed one, and then they start doing the operations on that one to make it easier. It's like a digital twin, they talk. Then one more point what you made, I'm picking up points from you so that my life becomes easy. So one more point I picked up from you, because the natural resources and raw materials what are available in this country, and then unless we speed up, and we are going to lose them. And even you see the iron ores, we still have to have the best steel, and then we still import Nippon steel and Asahi steel, which are too expensive, because the last part of that technology, 90 to 99 and 95 to 90, is logarithmic struggle to go on improving towards the 99.90. Anyone can do. We can even make a model whatever you see, because it's just reproducing. But the quality comes at every point when you keep increasing. So that's one of the things what we should understand. That's why you see a lot of iron ore is being exported. You have a lot of land mining mafias, because we don't have enough proper technology to that level. And now we are talking about very strategically important material, that is lithium. J&K, Jammu and Kashmir, they have 5.9 million tons of lithium resources in J&K. It is GSI, Geological Survey of India. They showed it is G3 level. That means 2 more levels have to be done. But why are we so slow? And then once you do that, then it is not lithium there. You have to extract lithium from the ores. That means it is extractive metallurgy, pyrometallurgy, then chemistry, solvent extraction. Then you convert to the material, which is the raw material for making the lithium iron phosphate or lithium nickel, which is the key material for all your battery plants. In future, India is going to talk about megawatt level of plants for batteries, for electric vehicle and other applications. And the key material inside, what is required, whether it is lithium iron phosphate or lithium titanate, all these are in megatons it is required, and then there is no supply of these materials. Even at the prototype level, we are struggling to get these materials imported. Earlier, China used to give, and then the problem is all globe wants these materials. So unless you have your own technology, you cannot do that. Now just actually we transferred one technology first time in India, lithium iron phosphate, to one Telangana-based company, and we're also giving our incubator. Today we're going to sign that one agreement with them for the incubator, and they're going to make in next 3 months 50 kilos per day production technology, and they're going to cater. Now a lot of foreign companies are looking, because China has other problems. They want supply from India for the export. So these people have got a lot of export market. And similarly, hydrogen economy. And we have very well-known hydrogen technology, because your chloralkali plants are having electrolyzers. They produce hydrogen, but it used to get wasted. But now if you properly design the electrolyzers, you can produce hydrogen. And now HT, one company, Pune-based, they are exporting electrolyzers. And then because of Ukraine war, hydrogen is very much on demand, because there is no gas supply to all Europe, and in winter they will be freezing and they want some gas. And UK gives a lot of subsidy on hydrogen to match with diesel and petrol prices. We were there in delegation with Secretary 2 months back. But it is 10 rupees or 8 rupees per kg of hydrogen, and DOE wants 2 rupees or 1 rupees per kg. And we're already very close to that numbers, which means that while hydrogen application for electric vehicle or any other application is going to take some time, but hydrogen production itself is already there. So we can export hydrogen in some form, so that we start exporting and then get the dollars out of that. So this is how the strategy National Hydrogen Mission is looking for. And come to additive manufacturing. In additive manufacturing, I think most of the people, and then a lot of institutes in India, and IIT Hyderabad is pioneering in that, and ARCI, of course, with the, at the right time, Professor Padmanabham, Dr. Padmanabham, who was my former director, unfortunately, we lost him. And then he established this additive manufacturing. He's a laser expert, welding expert, and he started this additive manufacturing unit. And then that time no one knows whether it will take a good leap, because a lot of money was spent on that. But today I see that it's a fantastic area, and then we are also in forefront of this topic. But I'm still not happy, like Professor said. We have capability to run, but we don't run that fast, because theek hai, chalta hai, I'm running anyway. So that is not the way. For example, I tell you, in additive manufacturing itself, we have two systems. One is SLM and another is E-beam melting. And then SLM, we have done some strategic components to defense, and then they're qualified. And the other one, E-beam melting, especially for titanium alloys, we're working on that one, especially closely with the medical guys, because those are more relevant to medical. But the medical doctors who visited us, they say that, especially for maxillofacial ones, you need titanium to have enough strength, but they want very lightweight. Because when they use titanium, because of the heavy weight, and is not able to sustain, and then patient is so uneasy. Because we have a lot of medical tourism, people who are fighting in Middle East, they keep coming here because India is cheap for the medical tourism, and then they get operated. So a lot of scope for that. I don't want that things to continue just being selfish, but we have a lot of scope and then use for this kind of technology. And another one, whether it's a biomedical or strategic sector, the materials what you require for additive manufacturing, that's powders. So that's not so easy, because you know that when you buy from a machine from a company, and then you have to buy the powders from the same A company, because there are specific powders with whether it is a density of the powder or spherical shape and size and so on. And for these two applications, strategic and medical, you need to have the certification of these powders itself to start with. So I was telling her, we do make powders, because we have gas atomizer in ARCI. We do make powders of steels and alloys of specific names, but they are not certified yet. So I was telling our people in few days back in a meeting that, can we make our own powders? We are making powders, and can you make a component what we have given to ARCI and got it qualified with the commercial powders? Can we make the same thing and then try that one? Then no sir, our powders are not certified. Do it, because that is, it's easy to always make some components, and then work so much to see that our powders are qualified and then certified, so that we start exporting the powders. So these are some of the things where the challenges are high. There the speed is not enough. That's why I totally agree. And unless that is covered by young people, you're all young anyway. So it will not take the speed what is required. And buying just machines of additive manufacturing, it doesn't make so much sense unless I'm ready to give money because we have enough corpus. I am ready to give money to Gurraj and their team. But I say that give me a plan. They say that binder jet machine we want. Okay, we'll give. If you want 10 crores, we're ready. But show me a plan of what you are going to deliver. Not just reading some papers and making another no, it doesn't work. You have to show how you generate money back to us down the line 5 or 10 years. But show me the plan then. So I told him 6 months I'm going to retire. In 6 months you give a proper plan and get the money from me. Otherwise we don't know who will come and then. So this is a story to us, but this is a story to all. Don't waste your time and don't waste just to get some papers and then keep your profile updated because we are at the right time and at the right place. So we have to see that how we can help the country in national building and how we can export, and then now our rupee is becoming a international currency and then it is competing, maybe down the line it may compete with dollar. So we have to take advantage of all this, and you are at the right time, all your young people. If you don't take advantage, then you are the loser. So I wish you all the best, and I'm sure that this workshop will be very great success. Thank you.
Thank you, sir. I hope we pick up pace and improve our rate at which we deliver. So may I now request Professor Ghanshyam Krishna to address the gathering.
Good morning. Professor Vijay Rao, Vice Chancellor, University, Dr. Tata Nasing Rao, Director ARCI, Professor Das, Dean SEST, all distinguished guests, and students. It is always difficult to be the last speaker in any session.
You want the last word.
So that may be the privilege of. So you end up repeating much of what has been said, but I will not do that. I want to give you a perspective of from the institution of eminence. So it will be a slightly non-technical kind of this thing. I'll just take a couple of minutes. I remember, before I do that, I remember going to Belarus with Dr. Padmanabham as part of a delegation in 2018. And over 4 days that we spent there, we had very extensive discussions on manufacturing and how he had a vision which is now, I think, fructifying at least in ARCI and in institutions, our university and IIT and so on. But he was very passionate about it. And I remember long discussions and walks in the very cold weather before Belarus closed down permanently, I think, for all of us. So this is good that it is dedicated to him. I think it's something that we should remember him for his vision. Now, coming to the institution of eminence, just briefly, when the university was given the status of institution of eminence in 2019, one of the goals and one of the objectives was to improve the perception, visibility of the university so that it could lead to, possibly lead to improved standing in the world's academic ecosystem. And so during the COVID time, we had slight difficulty, but we have now very quickly gone from the planning stage to implementation of the program. And we are now in the final stages of the IOE. We are in the last financial year. And we are now looking at sort of tangible outcomes of all these programs that we are supporting. So just to give you an idea, I mean, this is for internal consumption, of course, that just in the last 7 months, Institution of Eminence has financially supported 50 conferences, workshops, seminars, and distinguished lectures of this kind. and we have spent a fairly large amount of money, in excess of about 2.5 crores. So the financial support is there, and what we are looking for in this sort of financial year, I think our Vice Chancellor and we have discussed this. We are looking at now outcomes, what is the outcome of all this support. And I am hoping that additive manufacturing, as everybody has said, is a very important area. But we would also like to see some tangible outcome from this program. And one of those things could be, this is just a suggestion, I am very fond of this manufacturing. Actually, when the MTech program in the School of Engineering was started, I was kind of involved in the conception stage, and we were all in the faculty. I think we were far ahead of the country at that point. I don't know if there are any other institutions in the country which offer a manufacturing science and engineering program. So this university was far ahead of the rest of the country. And I think it is time to, in some sense, cash in on the lead in the race, so to speak, and get more people, more students into the program. And one way, of course, is to organize a workshop like this and attract more students, and at least tell them that we have a program, and hopefully one of the outcomes of this program, apart from the discussions on the research and development, would probably be an increased intake in the MTech programs. And as we are all aware, many of us are aware, the MTech programs in this country in general are losing popularity for whatever reason. But we need to see that more people get into the system. And one of the goals of the IOE is to increase the student strength by increasing the intake into these teaching programs. So, manufacturing science, as already has been stated, is a very important current area of both science and technology. There are a lot of basic problems that have not been addressed, and a lot of technology-related issues that need to be addressed. And it has to be a collaborative effort. It cannot be done just by one institution. So I would like to urge the School of Engineering Science to take this opportunity to publicize the MTech program also. I see that there is a panel discussion, so maybe it could be aimed at students, and tell them what the program is about, and maybe attract them to apply for admission to this program. So thank you again for the opportunity to talk to all of you. I wish the program all its success. It's an important program, and we look forward to a positive and tangible outcome from this. Thank you.
Thank you, sir. I hope this event results in a spurt in the enrollment in the MTech program. So I'd like to now request the Vice Chancellor and the Director IOE to honor the guest of honor. Thank you, everyone. With this, we come to an end of the inaugural ceremony. I'd like to now request Professor Ghanshyam Krishna to chair the inaugural session.
So good morning again. Welcome to the first technical session. And the inaugural talk is by Professor G.D. Janakiram. He is a professor in the Department of Metallurgical and Material Science of IIT Hyderabad. He was formerly with IIT Madras. I remember meeting him for one PhD exam in School of Engineering when he was still in there. So I welcome you. And we're going to talk about, and you're going to give us an overview of the metal additive manufacturing. So welcome.
Thank you.
I'll allot you around 35 minutes or so.
Yeah. Good morning to all of you. I'm really honored to be here, and I see that I'm talking in front of many eminent people here, so I feel nervous. So being the first talk in the workshop, it is my duty to give you a broad overview of additive manufacturing technologies. It is quite challenging to do that in 35 minutes, 40 minutes, to talk about additive manufacturing in its full length and breadth is very challenging. So what I thought is, I would focus more on metal additive manufacturing. We have many different additive technologies. Some of them are meant for producing end-use metallic parts. And these are the most interesting technologies in the industrial context today. So I will focus on metal additive manufacturing. Of course, give you a very brief glimpse of other additive technologies as well. So what is additive manufacturing? Any layer by layer material addition is not additive manufacturing. It has a very precise legal definition. It refers to a process by which digital 3D design data is used to build up a component by layers by depositing material. There are several keywords here. Digital design data, and then material addition, and then a layer by layer approach. Currently, many additive technologies utilize the layer-wise material addition strategy. But it is possible to conceive additive manufacturing in more sophisticated ways. It is possible to deposit material in a non-layer strategy and still be able to produce a three-dimensional part in a progressive manner. So what is important in the definition of additive manufacturing is not layer by layer approach. It is material addition in a progressive manner. There are three attributes to any additive manufacturing process. We always go from digital to physical. That means a physical part is produced utilizing digital data. So you have a virtual model, and that is converted to a physical part. Then all additive technologies are fully automatic, and they should go unattended. And of course, the third attribute is very important. That is no part-specific tooling. In additive manufacturing, we do not use any part-specific tooling. For example, if you want to produce a casting, you need a pattern, and then you make a mold, and then the component is produced by casting. And this pattern and that mold are specific to that particular casting. We cannot use them for producing any other geometry. Whereas in additive manufacturing, you have a standard set of tools, and they can be used for producing any part. what is the implication of this definition is this. If I employ a skilled welder and ask him to deposit weld metal in a shaped manner, he would be able to do that, right? And he can perhaps produce fairly complex shapes. But that is not additive manufacturing, because this operation is manual, and then the welder is not using any digital data. Of course, the part is produced layer by layer, but that doesn't qualify this manual welding approach to be additive manufacturing. Now, additive manufacturing is something like 30 years old technology now. We have the first commercial additive manufacturing machine back in 1989. A system called stereolithography was commercially introduced in the US by a company called 3D Systems. So we have come a long way. But for a technology, 30 years is not really a long time. And therefore, we still say that additive manufacturing is an evolving technology. It is the most contemporary technology and things like that. All those are true. 30 years is not a very long time for a technology. It used to be rapid prototyping originally. Initially, when these technologies were commercially introduced, people called them or referred to them as rapid prototyping technologies. But that is not the most inclusive definition of additive manufacturing or to these technologies. Then for some time, people used alternative terms like rapid manufacturing, solid freeform fabrication, of course in a loose manner, 3D printing, and also direct digital manufacturing. So the terminology evolved over a period of time. And now, universally the most accepted term is additive manufacturing, which actually conveys two essential elements of this technology. You are adding material to manufacture a component. So that is additive manufacturing. Of course, in some additive manufacturing processes, you may actually involve some subtraction, material subtraction. And these technologies are now referred to as hybrid additive manufacturing technologies. So you have some pure additive processes, and you also have some material addition plus subtraction processes that are now referred to as hybrid technologies. Another important thing is to realize that additive manufacturing has very close connection to welding and joining. After all, you are progressively adding material, that is, joining materials is anyway involved. A lot of people actually say that additive manufacturing is nothing but welding under some special boundary conditions. It is true, but in my opinion, it is also gross oversimplification, because the context is entirely different. In welding, you only have one interface to worry about, whereas in additive manufacturing, you have thousands of interfaces to worry about. And therefore, we have to treat additive manufacturing a bit different from welding. Of course, our knowledge of welding and materials joining are fundamental to understand what happens during additive manufacturing. Now, in any additive manufacturing process, you have 4 process steps. The additive process chain involves making a CAD model, for which you have many different mature commercial software like SolidWorks. What is done is this CAD model, solid model, is then tessellated. That means the outer bound surfaces of the part are represented with a set of interconnected triangles. That is actually referred to as tessellation. And this tessellated model should be watertight. That means there should not be any gaps in the part surface. And then this tessellated model is sliced, mathematically sliced into number of horizontal cross sections. And then the contour paths and material deposition paths are obtained from these cross sections. During this pre-processing stage, many other important aspects are dealt with. For example, in what orientation you build a part. If there is a overhanging feature, what kind of support structures do you need to provide? In most additive manufacturing processes, you need to provide some support structures for any overhanging or downward facing features. Otherwise, you have to have something underneath to be able to deposit material. Or you have to have something underneath to firmly anchor the material so that distortion cannot take place, right? So support structures, then where do you place your part? Typically the additive build volume can accommodate multiple parts. So where do you locate your part? And similarly, how do you bunch your parts? In a single build run, it is possible to combine multiple parts and carry out a single build run. So how do you locate, how do you bunch your parts? Similarly, part orientation. If you want to build this, would you like to build it in vertical orientation or horizontal orientation or at a inclined orientation, right? All these have important effects on the quality of the part that we obtain from additive manufacturing. Then, of course, in what material would you like to build the part? And for a given material, what would be your process parameters for achieving solid material without any defects? So all these are taken care of in the pre-processing stage. It is the pre-processing stage that actually demands a lot of knowledge of additive manufacturing. Otherwise, we cannot carry out any of these operations effectively. After that, everything is very simple. You just push the print button and the machine starts printing the part. And this is the fun part of additive manufacturing. You don't have to do anything. You can push the button, go out, watch a movie, then have coffee and come back and collect your part. It is very much possible. You don't have to be around when actual part fabrication is taking place. Then, post-processing, after the part is printed, the part is separated from, let us say, the build plate, and then it is subjected to a series of cleaning, finishing operations. The nature of these post-processing operations very much depend on what type of material you are using for part fabrication. Similarly, whatever process you are employing for making the part. In some processes, it is simple cleaning, maybe some sanding and applying some lacquer, things like that. But in some cases, the post-processing operations are very elaborate. You may have to do machining, you may have to do hot isostatic pressing, you may have to do a certain heat treatment to obtain the right microstructure and properties. So that is additive manufacturing in a nutshell. Then why are we excited about additive manufacturing? Of course, these technologies offer multiple benefits. First of all, in few hours, an idea can be brought to life. That is not the case with conventional manufacturing techniques. If you have to produce a part by forging, you have to order dies today, and the dies would arrive 3 months after, right? So your idea of making a part can only be realized after 3 months. But in additive manufacturing, that is not the case. Within hours, you can actually bring an idea into reality. Additive manufacturing is truly manufacturing simplified, fully automatic, then no part-specific tooling involved. Last-minute changes in design can be readily accommodated. This is of particular interest in making biomedical implants. Most of the biomedical implants are patient-specific, so one patient to another patient, we need to change the design. And that change in design is very expensive if you consider conventional manufacturing, but it can be done very easily without any additional expenditure in the case of additive technologies. Additive manufacturing, of course, offers unprecedented geometrical freedom. You can make as complicated as this, and there are no real restrictions on the complexity of the geometry or dimensions. Then you can also combine several different parts into one and reduce the assembly costs. And this also simplifies the shop floor logistics. For example, I know in some aerospace and automotive applications, an assembly out of, let us say, 140 individual parts can all be made as one unit. So 140 parts actually are reduced to one part. That is because you don't have restrictions on the shape, geometry. Of course, additive manufacturing is cost effective as well as time effective. This is not so straightforward. There are certain geometries for which additive manufacturing is cheaper compared to conventional manufacturing. As the part complexity increases, additive manufacturing becomes more and more cost effective. Similarly, there is a certain part production volume. Up to that point, additive manufacturing is quite cost effective. For example, if you want to produce only 10 pieces of this, additive manufacturing is more cost effective as compared to conventional manufacturing. But if you want to produce 10,000 pieces of this, then you have to think additive manufacturing may not be cost effective. Then additive manufacturing promises better properties and performance. You can achieve better performance by innovating with the design. You can also achieve better properties and performance by innovating with the materials. For example, you can control the microstructure the way you want and achieve better properties. If you want coarser grain structure in the core region and finer grain structure in the hub region, it is very much possible. Because localized microstructure control is possible with additive manufacturing, which is not possible with any conventional metal manufacturing processes. Then you can also make a part in multiple materials or in functionally graded parts, functionally graded materials, for achieving better outcomes, property outcomes. You can also design microstructure. It is possible to deliberately complicate the design microstructure so that your part cannot be reverse engineered. This is very important for some defense applications. If you make a certain weapon and you would like to achieve a certain performance with the weapon, and if you design your weapon such that it cannot be reverse engineered, you are happy. Your enemies cannot duplicate your weapons, right? As I said, mass customization is possible with additive manufacturing. If you consider finger joints, total hip replacement joints, all these are patient specific, and you can easily customize the part to a given patient or application. Of course, the most important, one of the important advantages of AM is its ability to meet on-demand goals. Additive manufacturing can be used for making parts on demand, that is manufacturing anywhere, anytime, any shape, let us say, right? And this has a lot of advantage when you talk about spares. A lot of automobile companies keep huge inventories of spare parts, because you never know how many spares would be needed in a given year or time frame. But in reality, they may not be using all those spare parts. So you are unnecessarily wasting a lot of money, space. Inventory management is complex. With additive manufacturing, nothing like that. You can order today, get your part tomorrow, right? Then additive manufacturing also democratizes manufacturing. Traditionally, manufacturing is highly capital intensive, and the economies of scale would apply, right? Traditionally. And that is why you have some monopolies, manufacturing monopolies. We cannot compete with, let us say, with China in making certain components because they have the economies of scale, right? We don't have that. But with additive manufacturing, you can actually have a company set up in, let us say, half of this hall, in space less than half of this hall. With one machine, with, let us say, 4 or 5 employees, you can actually make critical components for aerospace, defense, and supply. And that way, additive manufacturing can become a cottage industry. There is no compromise on quality, no compromise on economics, right? And in a country like ours, that is a big boon. We can actually think of many, many small startups participating in additive manufacturing, making parts and delivering to big players like ISRO, right? So, done with advantages of additive manufacturing, there are many more. We can keep discussing. Now, how do you classify additive technologies? According to ASTM, we have 7 classes of additive technologies. Like 7 hills, you have 7 classes of AM technologies. They are referred to using some generic names, like vat photopolymerization, filament extrusion, sheet lamination, binder jetting, material jetting, then powder bed fusion, the big player, then directed energy deposition, then some hybrid and miscellaneous processes. Now, in each of these classes, you can have many subclasses depending on what material you are using, what energy source you are employing. And I have given here some popular commercial processes. Mind you, these are all trade names, and these are company specific. These are generic names which we should use while referring to these technologies. For example, in vat photopolymerization, you have a vat filled with a photosensitive resin, and you have a XY gantry, and a laser is mounted on this XY gantry, and you spread a thin layer of resin on top of a build platform, perforated build platform, and then the laser selectively scans the resin layer. Wherever you have laser irradiating the resin because of photosensitive effect, not photosensitive effect, the resin is actually photocurable. So you have curing taking place, so the liquid resin turns to solid. In other words, you have generated a solid layer. Then the build platform is lowered by 1 layer thickness. Another layer of liquid resin is spread on top of it, and then you continue for scanning for the next layer. While doing this, you always ensure that every layer actually fuses with the previous layer. In the case of vat photopolymerization, every layer should cure into the previous layer, and the process parameters are so controlled, right? Now, this wet photopolymerization can be done using a point-wise curing mechanism. That means every point on the layer is cured point by point, right? Whereas it is also possible to use a curing mechanism that takes place over the entire layer in one go. So accordingly, you have layer-wise curing or point-wise curing. So with each of these, you have commercial examples. For example, the 3D systems stereolithography process is a point-wise curing technique, whereas a company called Carbon 3D recently introduced a layer-wise curing machine, right? And that is Carbon 3D process. Then in filament extrusion, essentially you have a thermoplastic filament, which is heated to a temperature above the glass transition temperature. So it becomes semi-molten. And then the filament is extruded through a small nozzle, and the material is deposited in a manner governed by the digital data of the part. By depositing material in a layer by layer manner, one can produce a three-dimensional part using filament extrusion. Here, one may employ a polymer. It is also possible to employ ceramic material bonded with some kind of suitable binder, or it is also possible to use metal powder loaded into a thermoplastic filament to fairly high level, something like 80-85 volume %. And then the filament is extruded and deposited. So after depositing such a filament, what you have is a green part, metallic powder particles bound only by the binder, right, plastic binder. And then the plastic is burnt out. Then the part is sintered, solid state sintered at a high temperature to achieve full density. This is more like your metal injection molding or powder metallurgy route for making a component. Yes, I may not be able to cover all my slides, but that is fine. So coming to binder jetting, here you can use a plastic powder or metallic powder or ceramic powder or mixtures of metal ceramic. For example, if you want to produce silicon carbide particle reinforced aluminum matrix composite, this would be the technology to look at. Among all additive techniques, binder jetting has greatest flexibility in terms of part material. But of course, you are only binding the powder particles by a plastic binder. So in as printed condition, the part is not strong. Subsequently, solid state sintering has to be carried out to achieve high strength, right? There are some advantages in utilizing binder jetting for making a metallic part. We'll maybe talk about it later. Then you have, importantly, powder bed fusion. I have some slides to show, so I will not go into the details. This powder bed fusion can be carried out employing a laser heat source or electron beam heat source. Accordingly, you have laser powder bed fusion or electron beam powder bed fusion. Multiple commercial players are involved in powder bed fusion business. Then you have directed energy deposition, which is a very broad category, subcategory. It can be carried out using laser powder approach. You have your feedstock material in the form of powder and energy source as laser. Similarly, you can also use laser wire approach for making components. You can also use electron beam wire. You can also use electric arc or plasma as the heat source. Each of these have unique advantages and limitations. So that is for us to actually ponder about later on. These two techniques are primarily applicable for making metallic parts. Of course, binder jetting is a competing technology, but here material fusion is involved. You are completely melting the material and the molten metal is solidifying. Whereas this doesn't involve melting and solidification. You only cause solid state sintering. There are also other metal additive approaches, very interesting, like ultrasonic consolidation or ultrasonic additive manufacturing, in which case you use thin metal foils. And these metal foils are welded to each other using ultrasonic welder, and then they are shaped using an integrated CNC machining setup. I will show some slides later on. Now, this video plays. You can keep watching. These are available even on YouTube. You have multiple videos of these processes. Essentially, in powder bed fusion, you spread a thin layer of powder, and you have a laser mounted on a XY gantry, and the laser selectively scans such that the material fuses into the previous layer, right? And with laser metal powder, you have the electro-optic systems, direct metal laser sintering, DMLS. This DMLS is a trade name, and the generic description is powder bed fusion, right? Now, this is what I was referring to. You have a layer of powder here, and you control your laser parameters such that the current layer fuses into the previous layer, right? This is the melt pool depth, which is at least 2 or 3 times higher than the thickness of the powder layer that you are spreading. And this is done deliberately to reduce the probability of having an unfused area in the final component. In principle, it is okay to melt just this much, right? Why should I melt much deeper? In principle, it is possible to produce a part by melting only the powder particles, right? But actually, the thickness of the melt pool or the depth of the melt pool is 2 to 3 times higher than the thickness of the powder layer. And this is actually to reduce the probability of having an unfused area, which would finally manifest as a defect, right? Now, you also need to consider how you scan or cover the entire layer area, fuse the entire layer area. For example, if this is the sliced cross section, then you have to do filling, in other words, hatching of the area, and also the contour, that is the outer bound line indicated by this black line here. And if you blow up, this would look like this, right? This is your hatch area, and this is your contour area highlighted by the blue color here. And the parameters for hatching and for making contour are different. You have to employ slightly different set of process parameters to achieve best outcomes while doing hatching and contouring. Similarly, a given layer area is scanned using multiple strategies. For example, you can divide the entire scan area into a number of segments and take up these segments one after the other in a random manner. For example, that is what is here as island scanning. You divide this entire area into a number of small square regions, and then go scanning from 1 to, let us say, 2 here, 3 here, right? And this is deliberately done to minimize the buildup of residual stresses. Otherwise, you are melting the material, allowing it to solidify. So there is a lot of residual stress getting generated. There are also thermal stresses. And if we scan in a monotonous manner, your stresses would be too high, which can lead to cracking or distortion of the part. So this randomized scanning is carried out deliberately. Similarly here, what is known as rotated stripe pattern, which is very common. You divide this entire cross-sectional area of the part into number of segments, and these segment lines are rotated at 67 degrees for every layer. For example, for the first layer, if the lines are here, your scan lines are always perpendicular to the segment lines, and the segment lines are rotated by 67 degrees for the next layer. So why 67 degree? 67 degree has certain advantage, because when you use 67 degree rotation, the exact same scan pattern would not repeat for at least a few thousand layers, right? And you don't want to repeat your scan lines after every few layers, right? And so there are many advances in the way scanning is carried out. And this is the other technology that I was referring to. Using electron beam as the heat source, powder bed fusion can be carried out. Yes, I will close now. Electron beam has many advantages compared to laser beam powder bed fusion. First of all, beam generation efficiency is very high with electron beam. And electron beam has no inertia. It can be manipulated easily using electromagnetic coils, right? And the third one is that the beam itself can be used for preheating the powder to any given temperature. Laser cannot be used for preheating the powder, because laser heating is not effective in solid state, because lasers are reflected by metals, right? All metals are highly reflective to lasers, right? Whereas electron beam can be readily used for scanning the entire powder layer to a preheat temperature, and then you actually scan for the melting run. And the advantage is that you can actually keep the thermal stresses very low, and also this preheating is advantageous in many ways, like you can avoid cracking in some crack sensitive materials, right? So electron beam, for example, can readily handle a brittle material like titanium aluminide, because all of you know titanium aluminide is a very brittle material. And if you attempt laser powder bed fusion, it would undergo cracking because of thermal stresses. But when you use electron beam welding, electron beam powder bed fusion, you can use very high preheat, so minimize cracking. So I think I have to end somewhere here, and I would be happy to answer if you have any questions. Of course, I could not cover much. I was only able to talk about powder bed fusion. Yes?
Very informative talk, Professor Janakira. Yeah, coming to the basic definition, I have slightly a different opinion. So you are saying that digitization has to be part of the additive manufacturing definition.
Yes.
For example, if you look at the snake's den that nature has given us, of course ants make it. And that's the classic example of additive manufacturing. For me, I think even humans have realized that this nature has already given to this us.
I beg to differ. That is nature, this is technology, right?
No, I'm talking about additive manufacturing.
A honeybee, the beehive is also made in additive manner, right? Beehive is made in an additive manner by progressive material addition. Of course, it is not layer-wise, and there is no software or CAD model of the honeybee hive, right? But that happens in nature, and we cannot, unless we cannot probably do that unless our artificial intelligence matures to the level of let us say nature. Yes. And right now the perception is that We need to have a digital model to drive manufacturing. That is only additive manufacturing. And without that digital model, it is possible to make a part. But our artificial intelligence should be maturing to the level of nature. And I don't see that is a possibility anytime in near future. Yes? Yes.
I was in IIT Chennai. There is one Indian company is already making.
Yes, correct.
So, but that is not listed. So I wanted.
These are only typical examples.
But that is also Indian one, no? So.
But that is not the most popular one.
No need. But at least young people will get.
And if you see, yeah, I know that's a good point. Good point, actually.
What is that company name?
Intech Additive.
Yeah, exactly. Yeah.
Intech Additive and also AMAS,
Yeah.
AMAS. And both are actually now making and supplying powder bed fusion machines. And Intech Additive has also a plan to introduce laser powder directed energy deposition. And AMAS, that is AMAS, has a plan to introduce wire arc additive manufacturing machines commercially. So these are good developments, right?
So if you put it, that is encouragement to us. And second thing is...
no. The rider is here. Popular commercial process.
Yeah, but remove...
So these are yet to become popular.
Yeah, let us make ourselves popular. And second thing is, the Skyroot technology, recently cryogenic engine, they demonstrated and well. What is that method and what is that? You have any idea?
Powder bed fusion only.
Okay.
And...
G? Okay.
EOS. Yeah. See, among all powder bed fusion machines, EOS has the greatest presence in terms of the number of systems installed.
Okay.
And their systems are also quite user friendly, but they won't allow you to use non-proprietary powders. Yeah.
Fine. Thank you.
Yes, please.
What kind of designs are refractory to additive manufacturing?
See, we say additive manufacturing has very few restrictions on geometry. Having said that, a given process has some restrictions on geometry. For example, in powder bed fusion, you cannot actually make a fully enclosed internal cavity, because that cavity would get filled by the unfused powder. So that is not a possibility. If we really have to make a part with fully enclosed internal cavity, we should be using ultrasonic additive manufacturing. And into that cavity, it is also possible to embed some electronics, sensors. So there are process-specific restrictions on geometry, but the overall restrictions, additive manufacturing as a whole has very few restrictions on geometry.
But you have a feature size that you cannot bring down less than the size of your spot. And
yes.
That's what one more problem I see, challenge.
Yeah.
Because which is in microns.
Yes. Among all additive techniques,
Yes,
laser powder bed fusion has the greatest feature resolution. Of course, stereolithography has even better feature resolution, but that is not applicable for metals.
Yeah.
And one more thing here. Even powder bed fusion cannot produce fully satisfactory surface finish or dimensional accuracy for most applications. Yes. So we should be prepared to do some machining or surface finishing operations in any case. Therefore, the feature resolution that we can achieve is inconsequential. We can always do it by machining.
Yeah, Jankiram sir, hello.
Yes, please.
Here from Twassa Manufacturing Solutions. Hello. Thank you very much for an in-depth, detailed overview, sir. Thank you very much for that. A couple of questions from my side was, in all of the technologies listed, sir, With respect to India, our country, our requirements, where do you see the maximum amount of potential, or what do you think is really path-breaking and is going to be dominating the additive space in the next couple of years?
Of course, manufacturing of biomedical implants is happening everywhere now. And even in India, that has become a reality. And there are multiple, at least 10, 12 different companies making implants using additive techniques. And of course, in transportation sector, aerospace especially, they have already adopted additive technologies. In automotive, we are yet to actually cross the barrier. It is used for prototyping as a product development tool, but not for producing end-use parts.
Sir, just one follow-up question to that. In the series of, say, DED or DMLS or powder bed fusion, where do you see maximum possible?
I would like to just add one more point there. See, in a country like India, we have really a requirement, a serious requirement for biomedical implants. And the requirement would only grow in future because of increasing longevities, right? And we have huge population. So we would need crores and crores of, let us say, knee joints or finger joints or hip joints. And additive manufacturing is going to play a very key role in meeting this requirement. Otherwise, we would be seriously limited by our business or economic situations. Yeah.
I think we'll take this offline.
Yes, please.
We'll close the session. Thank Professor Janaki.
Thank you very much. Thanks for your attention. It is not needed, sir. It's not needed. Thank you.
I'd like to now request Professor Dibakar Das to felicitate the Director IOE, the Chairman of the session. With this, we come to an end of this inaugural session.
Welcome back to the technical session. This is session 2 and we have 2 talks in here. First of all, I would like to invite Professor Sheshu Bhai ma'am, School of Physics, University of Hyderabad, to be the chair for the session.
Hello. Good morning to all. Thank you very much for this opportunity that SEST has given me to participate in this workshop. And we have some connection to additive manufacturing in the sense that when we had a networking resource center which we had in physics, we have 3D printing and 3D profile cutting and some machines that we have acquired, and we conducted a couple of workshops where almost 100 research scholars of our school and a few from SEST have participated for a couple of years. And this is basically to see how the basic 3D printing is done out of these ABS plastic filaments. That filament extrusion is what was taught to them as basics. And we use it for making molds by RPT, into which we do gel casting of ceramic and metal powder slurries to make components. So I was very much interested in attending this workshop, and it's a great pleasure to be here. Thank you, Professor Dibakar and Professor Gautam for it. Okay, so in this session we have about 3 talks. One of them will be online, and 2 the speakers are here. And the first talk is by Professor A. Murugayan from IIT Madras, and he is going to deliver a talk on alloy development for additive manufacturing of maxillofacial reconstructive implants. So, he's online?
He's online.
So we welcome Dr. Murugayan to start the talk.
Yeah, thank you, ma'am. Am I audible?
Yeah.
Okay, yeah. Maybe if you can turn the video on so that I can see with you. Or at least, yeah, okay, that's better. Yes, thank you. That's okay, Jay, I think it should be all right. Yes, yeah. Let me share my screen. Thank you, madam, for introduction and, yeah, okay.
Now you can feel it later.
Yeah, it's better, okay. Let me share my screen. Is my screen visible?
Yes.
Okay. Yeah, so thank you, Professor Jay, and the other colleagues in University of Hyderabad for inviting me to give this talk. And first of all, apologies for not making in person. I've been traveling extensively and fell slightly ill on Friday. So I thought, okay, better to stay away and give this talk online. Thanks for bearing with me for not being there in person. Anyways, I would have loved to come and then do this talk. So this talk, I am going to give it for 30 minutes, about 30 minutes on our recent effort on new alloy development for maxillofacial reconstructive implants. So this is actually a joint project between India and Norway. So through our DST and ARCI and Research Council of Norway project. And this was actually started before pandemic. But then it so happened that this work is has set a big way of helping pandemic patients, and we have been doing a lot of printing of maxillofacial reconstructive implants from the knowledge we generated from this project just 1 year before, from 2019, when we started this work, and how this knowledge is actually useful for this proposal. I'll just cover quickly, and then and to let you be aware that how the additive manufacturing comes into handy in such implant production as well. As I said, so this work is actually carried out by these 2 PhD students, one in IIT Madras, one of our students, and then Ms. Deena from the University of Stavanger. And the colleagues who are actually participating in this research are listed over here. And we are also collaborating with the startup in Chennai. And this startup is primarily started by surgeons who are expert in plastic surgery and maxillofacial reconstructive surgery. Okay, so I will just tell about some of our collaboration also in this project. The Norwegian partners are represented by University of Stavanger and Nordic Institute for Dental Materials from Norway. Yeah. Right, so this is the outline of my talk. Okay, so yeah. I'm going to give introduction about the work and then why the post-pandemic situation these implants are urgently required, and then some of our work on replacing conventional medical grade chromium, cobalt chrome alloys, with the new alloys which were actually intended to develop for these maxillofacial reconstructive implants. So what are the strategies we have been following, and how we are actually looking at developing new alloys which are cheaper and superior to conventional medical grade cobalt chrome alloy, and the actual item manufacturing process development for these newly developed alloys. We would also present here, and then conclude about why these new alloys are required for Indian text. Right, so First of all, as I said, when we were actually starting this work, we were never aware of the pandemics going to come within very short time. Right. So what happened during pandemic, especially the patients who were actually hospitalized for long time in ICU, and those patients were actually got this infection, which is actually known as a black fungus infection. And the technical term for this black fungal infection is mucormycosis. So this is very deadly fungus. Okay, so the primary source of this fungus is the air conditioning units of the hospital. Unfortunately, the patients who are actually hospitalized for a long time, more than a month in ICUs. So they were all, some of them got into this infection. And this is one of the most deadliest infections one can get. These COVID patients, they are also treated with a lot of steroids in orally, and that led to compromise in the immunity of the oral part of the patients. So what happens then, these black fungus tend to get into the bones, especially these regions, and the moment these fungus gets infected, okay, so there is a direct connection, channel between the brain and the facial part. Okay, so therefore the death is imminent. And the patients were actually given antibiotics. Unfortunately, because of the compromised immunity, they could not survive. So the moment the black fungus infection was noticed on these patients, best surgical procedure to save the patient life is to remove the infected regions. Okay, completely. These bones are all removed by surgical procedure so that the patient life can be saved. So this is one of the patient's CT scan, the actual patient data. So after the surgical procedure, this part of the infected bones are all removed so that life can be saved. So during just about 2021, when we look at the statistics of number of these such black fungus patients, the official data, recorded data, was about 52,000 cases in mucormycosis. This is official data, and the number of patients state-wise, if you look at, it's phenomenal. But unofficially, when we looked at the data, about 1.75 lakhs patients urgently require some part of reconstruction for the lost bones in their faces. Okay, the same patient, if you look at the post-surgery, the part of the infected region will completely removed, and then the patient is living without the facial, this maxillofacial bones. So after this, the treatment, so their life becomes miserable because they cannot eat, they cannot chew, and most of them are liquid diet, and then they also suddenly, within no time, because of this infection, they lost the facial structure. So the number of patients who are actually suffering from this mucormycosis post loss, psychologically also affected, and then health-wise because of the lack of nutrition, they are all suffering. So what we have initiated in collaboration with the surgeons when they are actually looking for these implants. These implants are mostly imported, and the imported implants would not even confine to the facial structure of these patients. And these imported implants are extremely expensive. Say, for example, if you want to reconstruct, this part of this patient, the actual implant cost, and if you're importing from Switzerland, there are few implant companies, it would cost about 45 lakhs. So it is not affordable for the poor patients who generally, go to government hospital and then get treated. So the best way of, helping those patients to, develop a strategy to design the implant, which can be this patient specific. What you see over here, the same patient who was struggling from very poor background. Basically, he was actually a cool in a farming land, right? So these patients were identified, and then subsequently we developed an algorithm in collaboration with engineering design. Professor Sarana Kumar of one of my colleagues who already made some effort on developing patient-specific implant designs. So we got his help, and then from the CT data, sit with surgeon and develop the implant design, and these implants subsequently can be printed. Okay, so once the implant is designed and we print, okay, currently these implants were printed using simple titanium 6 aluminum 4 vanadium implants, so that medically we can actually take it up and then it can go to surgeons theater, and then subsequently a patient get these implants. Okay, so this is the first effort where additive manufacturing, how we can bring back the people's life and the smile on their face, and without additive manufacturing, 3D printing, this would never be possible. And these are some of the implants what we have printed in our labs, okay, post pandemic in last 1 year from October 2021. So last one year, 1.5 years, we have been doing extensively on designing the implants and then printing these implants in our lab, so that these black fungus patients can be brought back to the smile. Right. Apart from these implants, we also need such facial reconstructive implants also for correcting birth defect. So this is one of the other patients where she had from birth, okay, a defective bone and in facial bone structure, her the facial cleft, okay, so it was not fully developed. So because of that, she has been living without proper right eye, due to the deformation and then loss of bone in the socket, what you see over here. So we also identify through a charity these patients, and we can also design the implants for such patients, and then we can print those implants and then move surgically implanted. And apart from these implants, we also require urgently, okay, so patient-facing implants, especially for facial structures, countries like us where the head injuries are extremely common. And again, this picture shows the facial reconstructive implants for the accidental trauma patients. The number of cases which we encounter are tremendous, especially the two-wheeler accidents. When the patients come to us, they always tell that they don't wear helmets, right? So these accidents lead to severe deformity and then fracture of facial bones. And in this case also the maxillofacial reconstructive implants should be made instantly, and that means that there is no waiting period. So we'll have to get the CT data instantly, we'll design the implant, and then subsequently the printing should be done so that a patient's life can be saved quickly. So the requirement of the maxillofacial reconstructive implants in a country like us is increasing, and this pandemic also made us to work towards alleviating the pains of the people by looking at how these implants can be readily made, and then subsequently, okay, so those patients' life can be saved. That. Right. So apart from these three cases, we also get a lot of tumor resection patients, and this tumor, most of you know that because of very common Indian habit of taking tobacco, and these patients are also undergoing these surgical procedures. When the tumor is removed, then the facial reconstruction should be carried out. Okay, so the requirement of the maxillofacial reconstructive surgeries is increasing day by day, and so we need at least an established procedure to design the implants, and then subsequently within a very short time, okay, so these implants can be printed or manufactured so that the patient life can be saved. So additive manufacturing, naturally, because of the advantage of materials and the time saving, and it's a wonderful way in which we can realize these implants within a very short period of time, and then these implants can be surgical implant. So we are actually starting up a new movement. Okay, so they have tried to phase in IIT Madras in collaboration with one startup. Okay, which we are all part of it. It's called Zodiac Innovation Lab, where we identify the patients. Especially right now, we are looking at the patients who require maxillofacial reconstruction implant after their black fungus treatment, mycosis treatment, and people, if they have very poor background, we actually help them and get the implants printed and then surgically implanted through the various CSR grants from the hospitals as well as the companies. So we help those patients to get their face restored, and then so that they can get their identity back. Okay, so we are primarily using additive manufacturing because of various advantages. I'm going to talk about it later, and then how this is actually changing the life of the people. Okay, so with this introduction, where we know that why these macrofacial reconstructive implants are really required, and some of the implants, medical implants that we use, we still use the cobalt chrome Balu-based alloys. So even though some of the maxillofacial reconstructive implants, which are actually not loaded functionally, okay, we use titanium, but some of the implants which have, for example, which goes in contact with the bone, okay, say for example here, these implants, so which in contact with the actual bone, sometimes we also use cobalt chrome moly, okay, to have a very good wear resistance and toughness. So the cobalt chrome alloy, we still use it not only for maxillofacial applications, also in the femoral implants, especially to replace femoral bones and hip total THR, total hip replacement implants. So these cobalt chrome alloys are still widely used in conjunction with the titanium Ta64 alloys. So why the cobalt chrome alloys based implants are still used? Because of its excellent wear resistance and corrosion resistance. Right? It also has a very tensile strength compared to titanium. Okay, it has excellent fatigue and then high stiffness and hardness. So the bone replacement implants are still, surgeons prefer to make it using cobalt chrome moly, right? And then these cobalt chrome moly, when you look at the medical grade cobalt chrome alloy, okay, it also has an excellent printability. Okay, so therefore additive manufacturing becomes attractive. So why? Because the implants can be made within no time. So when the CT data is available, using the algorithms, we can just straight away convert CT data, whether it is in DICOM format or COSMIC format. So we have the algorithm which can convert them into an STL file. And once the STL file is created and we sit with the surgeon, in an hour we can identify where are the anchoring points or some further modifications. So once the design is finalized, within a day we can realize the implant. Whereas suppose if you are asking a specific implant to be made, mostly it got imported, and it would not only require a large lead time, and as well as becomes expensive. Okay, so the additive manufacturing becomes an attractive for cobalt chrome alloy because it also has a very poor machinability. Okay, and moreover, developing a printing strategy for this cobalt chrome alloy would also reduce the dependency for import, and we can also develop and print implants on demand locally in India. So therefore, additive manufacturing becomes attractive to print cobalt chrome based alloys, and we can also customize, as I said, sit with surgeon, and then we design the implants where exactly so insertion will be there, and then we can modify the design, which I'll show that in the next slide on demand. Okay, so again, the cobalt chrome alloys are, as I said, we still use it for maxillofacial surgery. For example, dental implants, we still use a medical grade cobalt chrome alloy. Okay, so this is an OCF frame reconstructed using cobalt chrome, and these are some of the accidental trauma reconstruction we're always using in cobalt chrome alloy. Right, so and some of the implants which we make using cobalt chrome alloys are also shown over here, where these medical grade cobalt chrome alloys are all used, where it has a direct junction with the bone, and also these implants are all highly loaded. Okay, so especially when patients choose the food, we subject them to nice cycle fatigue as well. So because of these high wear resistance and fatigue resistance, for such the implants, okay, for a maxillofacial reconstructive surgery, the surgeons still prefer to make using cobalt chrome alloy. So having said that, why we need to invent a new generation of these cobalt chrome alloys. Primarily, if you look at the conventional medical grade cobalt chrome alloy, it has about 60% of cobalt. Okay, so cobalt is scarce, especially it is a man-made scarcity, right? So it is abundant, but for Indian context or even European context, it's very difficult to source cobalt. Like some of you are there in the defense industries as well. Okay, cobalt is becoming strategic. Okay, and also therefore it becomes extremely expensive. And if you look at the cost of cobalt, what you see over here is about 50 to 55,000 US dollars per ton of cobalt. And if you compare the cost of iron, it is nothing. Okay, so iron cost is about 465 US dollars per ton. So therefore it becomes expensive. These implants as such when you make, so the alloy cost itself is very expensive. So to making it cheaper, we'll have to replace cobalt with somewhat available, abundant and not strategic alloy elements. Okay, and also the always cobalt toxicity is a problem. Cobalt is a category 1B with respect to its carcinogenic and reproductive hazardous potential. Okay, so the cobalt ion, when it's released, it becomes carcinogenic. Okay, so the cobalt chrome implant device as such will be safe. Okay. But then the reducing the cobalt ion release can also become beneficial. Can also lead to reduction in the appeal for reducing the carcinogenic nature. So in our project, we were aiming to reduce the cobalt concentration in medical grade cobalt chrome alloy and replace cobalt with iron and moly. Okay, so that the cost of these alloys can be reduced, and then subsequently these alloys would still be printable. Okay, so our objective is if you reduce the cobalt concentration, the machinability or customly becomes very poor. So therefore, the only way is to use additive manufacturing to produce the implant. So therefore, we have set the two objectives in this project. One, to make the alloy cheaper by reducing the cobalt concentration, but then because of reduction in the other conventional manufacturability, we'll have to only print. So therefore, additive manufacturing can be a viable option to print those implants or print those alloys, which we actually invent in this work. So we developed, based on the fundamental thermodynamic approach, new compositions for these alloys, and then subsequently develop the parameters.
Get that. Could you try?
Okay. So develop the parameters for printing, and then subsequently carry out in vitro and then mechanical properties evaluation to see how these new alloys, which we actually discover in our labs, compare with the medical grade cobalt chrome alloy, and then subsequently we can take it in vivo and then qualification further. Okay. The advantage of this India-Norway project is one of the partners, NEOM, Nordic Institute for Network Materials. So they are the certification agency for all these implants which are used in Nordic countries. Nordic countries include Norway, Denmark, Sweden, and Finland. So therefore, they take care of the qualification. And in fact, we are actually taking into vivo, which we will talk about it later, so that the entire work can be completed in due course. Okay, so as I said, our objective of this work is to reduce the cobalt concentration, which is about 60% in medical grade cobalt chrome, which is commercially available. All the implants are made using this composition, where the cobalt is 63%. Okay, if you follow my question, and then it has about 25% chromium. Chromium primarily is added to create a passive layer for excellent biocompatibility and corrosion resistance, and it has about moly. So moly is primarily used as a soil solution strengthener. Okay, and also it can give VM6 C-type precipitation to increase wear resistance. It has some tungsten and silicon as well. As I said, the 60% cobalt makes these alloys extremely expensive. So our objective is to reduce the cobalt, okay, to about half. Okay, so now at about 30% and replace the cobalt with iron. Okay, so keep chromium intact so that we can get good corrosion resistance. So about 25 to 30% chromium is required always for forming in a passive layer. Right, and then we can play around with the other minor elements like moly and silicon, primarily to silicon for portability aspect. So we started with the basic exercise with an objective to get a single phase structure at room temperature, say either BCC or FCC, and that is what our objective. So we played around sequentially from starting from medical grade alloy, replacing with the iron, and then vary the alloying elements, especially the iron and the moly combination, such that the room temperature we make it single phase BCC or FCC. Right, we were aiming to get primarily room temperature FCC phase. Because once you stabilize BCC, it becomes magnetic. Okay, so alloy becomes magnetic, the implant is magnetic, and that cannot be directly used in body applications due to the MRI compatibility. Okay, so when we did all basic calculation, and we arrived at two basic compositions. Okay, so and these two phases, these two compositions gives us a BCC in metastable BCC. But then again, if you do a simple heat treatment, okay, and then the metastable BCC transform to FCC, and then FCC stays as an FCC. Okay, and then the implant becomes paramagnetic. Okay, so the detail about the optimization, and I want to don't be detailed because I just got a message from Jay that I need to wind up in 30 minutes so that the delay can be compensated. So quickly, I'll just show. So once we have arrived at the comparison, so we develop the powders required for additive manufacturing. So we use primarily laser powder bed fusion. Okay, and if you look at this, the one comparison, as I said, two comparisons arrived at. So one is an iron rich. So iron is about 30%, as I say, as shown in earlier slide as well. And the actual structure is primarily BCC. So one of the objectives is to generate single phase BCC. So the powder, what you apply is a single phase BCC. In a conventional medical grade cobalt chrome, you may get an FCC and as such, but then in our alloy, because of increased iron concentration, so we got primarily BCC, but then when you do a heat treatment, it becomes FCC. Okay, so we develop the powder, and then subsequently once the feedstock is made, okay, so we followed sequential printing additive manufacturing process development, starting from the single track analysis and identify how the keyhole forms, and then this keyhole instability develops as a function of laser power and scanning speed by carrying out single track analysis, including arriving at required B geometry, and then optimizing the step out distances, and then I identify the safe window in which we can operate. And then subsequently, this window, the combination of laser power and scanning speed, is identified. Okay, and subsequently, we can look at a simple cubic analysis based on the grid search approach. Once we achieve a defect-free structure, we can start producing the coupons for various testing. Okay, so this exercise is standardized in our lab based on the procedures developed by the Janakaram, which I showed earlier. Next slide. Right, and subsequently, once we identify the optimum process parameter, we can start producing the samples for the various testing required. Okay, so the approach what we have generally followed for identifying the process window for laser powder bed fusion can be obtained from this paper of Professor Janakaram. Say, and we start with the single scan studies. So we print the blocks and identify the combination of laser power. And then scanning speed with respect to the porosity formation and then microstructure basic properties. So once we identify the optimum process window, we print the coupons for mechanical properties, corrosion, and in vitro studies. And subsequently, we can go back if it is required later. Yes, so the first step we identify is to get required the combination of laser power and scanning speed. So most of you are aware of in the textbook stuff, what is carried out by varying the laser power and scanning speed and identify the keyhole behavior. And if we go into keyhole, we may have to identify whether the keyhole is stable, or in some cases, most of the cases in private bed, we always work on the conduction mode so that the keyhole induced porosity can be minimized. Okay, so we identify, for example, in this case, one of the safe parameter is 200 watts power and 700 mm per second. Okay, and these parameters I can subsequently look at to calculate the hatch spacings or step over distance, what we call in academic term. Okay, the step over distance always we keep if you measure the width. Okay, 70% of the width would be the actual step over distance we measure, so that the defects can be minimized in terms of lack of vision, or the surface roughness can also be optimized. Right, so the first step is to identify the geometry, right, by measuring the whirlpool width and then depth as a function of scanning speed for a given laser parameter. Right, and if you use, for example, a low laser power, high scanning speed, you mean that producing volume. And because of the surface tension driven flow, we would use the volume effect, right? And if you are actually using a very high power or very slow speed combination, you may end up producing a keyhole where the penetration can be across the multi-layer, and it may also lead to keyhole induced porosity when the keyhole is not closing. The actual keyhole beam pressure and the recoil and level pressure can maximize the keyhole formation forces, and subsequently the closure can be too unstable, and then leading to the porosity formation by the inside keyhole. Right, so if you have a very low energy density, so we may not even melt at all. Okay, so we can identify so what is the stable the pool that we actually create, and then subsequently we can identify the parameters and combination of hatch spacings based on this whirlpool width and depth analysis for a given laser power and scanning speed. Right, so once we identify, so we get the combination of the properties when as a function of build orientation and the build positions, and we can put number of cubes and identify the density as well as the hardness. Right, so this density analysis would also be carried out based on the defect analysis. So for example, increasing energy density, okay, how the actual the defects are forming, and we can quantify. So we have developed now machine learning based algorithms where the combination of the parameters can be given and to identify the actual the tendency for defect formation, and also the AI based algorithms to automatically quantify the defects in a given microstructure, especially in powder bed system. Right, so from this grid search approach, we can identify so what would be this parameter which can give the optimal density. The theoretical density of cobalt chrome moly, what we used is about 7.87 grams per cc. And then we identify the actual parameters which can match the theoretical density, and the microstructure with least defects, including holes and porosity. So we carry out an extensive image analysis based on the images carried out as a function of multiple build orientation. Right, so the light becomes easy. So when you have such algorithms, the entire folder, if you have thousands of images, and we can analyze all together using the algorithm and identify defect density as a function of the parameters. So once we identify again, so the first stage is to the stable parameters, and then second stage is to get the and set of parameters which can give the highest density with minimal defects. Okay, we can start printing the number of samples for subsequent analysis. Right, so this structure shows the actual the microstructure developed using the parameters.
May I request you to take 2 more minutes and come?
Yeah, I'll just wind up quickly.
Sure, thank you.
Thank you. Yeah. Right, so the microstructure what we see over here are the new alloys what we developed, it shows a similar structure. And what you see over here, even though we predicted conventionally using the thermodynamic approach and a single phase BCC is expected, but because of extreme fast cooling rates which are encountered in the powder bed system, and we also end up stabilizing a sigma phase structure, and we are now evaluating the role of the sigma phase in the mechanical properties. In a way, these sigma phases as such did not influence the properties significantly, which is shown in the subsequent slide. These cellular structures, which will form because of the strong the directional solidification, and based on the nucleation, you may expect the mixed mode of solidification that is prevalent in laser powder bed system. Right. So then we went on and looked at the subsequent characterization techniques, in which we were looking at what are the possible phases. If you look at, this is a conventional cobalt from medical grade alloy, and this is our alloy. You may see that apart from the BCC and sigma phase, so we may also expect some other phases would also be nucleating, right? So, and due to this, we were actually worried earlier, but then when we did the heat treatment, which I did not show over here, and we could convert the whatever sigma phase is actually forming into an FCC, and more safe phases can also be converted by developing the unique retaining procedures. And this slide shows the actual the comparison between the printed medical grade alloy, which is in blue curve, and the red curve actually shows our alloy, which we developed. Okay? And what we found is the mechanical properties are also much superior as compared to the conventional medical grade alloy, where both the strength and ductility are maximized. And a couple of other information I would like to share is again, so the primary objective of using this alloy is to reduce the amount of cobalt ion release in body. And this green, what is over here is the conventional medical grade alloy, which releases a much more higher concentration of cobalt chrome in the simulated body fluidic condition. Whereas in our alloy, the cobalt ion is reduced significantly, and we found the more iron is reduced. And in terms of in vitro corrosion behavior, and we found that passivation happens at much quickly as compared to the conventional medical grade alloy. So in a way, the alloy what we developed showed good promising results, and then we identified that this is a very promising alloy based on this the preliminary studies, and we are now taking it to next stage of qualification by using it in micro studies. Right. So just summarize what we have done. The algorithm which we developed, becomes handy. For example, the actual exercise what you carry out, to design the implants from the patient-specific data, right? It can readily be used to realize the implant. Now, this is one implant recently printed in our lab, which was used to treat a cancer patient, 12-year-old girl, and where we could customize the implant as well as make it modular, so that on the data on the table, surgeons can decide on the insertion and then subsequently the implant setting. So this is a model implant, this kind of implants, which is impossible to produce by conventional manufacturing. Right, so with this I summarize my quick talk on how these techniques, 3D printing, additive manufacturing can become extremely handy to develop new alloys which are difficult to manufacture by conventional manufacturing, how additive manufacturing is helping to relieve the pain of the people who are suffering, especially after post-pandemic. And we have developed a very promising cobalt chrome moly iron alloy for bioimplants, which can be printed. Okay, so I thank all my collaborators and of course organizer of this workshop also to give me a chance to present our recent work. Thank you, ma'am.
Thank you very much for a very informative talk and telling us your contribution to the area. This is really a direct application of additive manufacturing to benefit so many patients. And can we have a couple of questions, please? Can I invite a couple of questions for you?
Yes, ma'am. Please.
Question.
Muru, nice talk. Koti here.
Hi, Pasupati.
Yeah. my question is, cobalt chromium moly is a commercial alloy.
Yes.
Have you compared your results with the conventional alloy made by AM?
Yes, these are all conventional alloy made by AM only. For example, this graph. So this is cobalt chromium moly.
That is commercial alloy?
It is commercial comparison.
Okay.
Yes.
Okay.
Yes. All the studies you see comparison. This is commercial medical AM printed cobalt chrome.
Okay.
And this is the commercial AM medical grade alloy. And this is our alloy.
And the new alloys that you have designed and made,
Yes.
have you made similar compositions using traditional route? And I'll give
We
you a
also
condition.
have done the casting, vacuum arc melting. Okay. And so vacuum arc melting produced an FCC structure.
Yeah.
But whereas here in the printed, alloy we got BCC because of extreme rapid cooling rates. Okay, that's solidified. It will solidify first in BCC and then it will follow the same iron carbon system. Okay, delta ferrite and austenite and then again martensite. Whereas in here, because of the fast cooling rate, in the as printed condition we still make BCC. But subsequent heat treatment, the as printed alloy, our composition becomes FCC.
Okay, thank you.
Sir, hello sir. Sir, have you measured the modulus of this alloy? Because the bone modulus is very different.
Yes.
Different problems.
Yeah. So stress fielding, right? So that's what you're worried about. Yes. Yeah. So these alloys would have a much higher Young's modulus, right? I mean, but cobalt chrome are taken in for that matter. Okay. So you always have a stress fielding problem. And these implants we require. We see, natural bone can never be replaced by newer material. Right, so density wise also you see that it's 7.8%, 7.8 grams per cc. Whereas the bone density is less than 1. So these problems would always be there. But implants can only be made using the alloys which are compatible. Okay, so body, either titanium A64 or cobalt chrome alloy. So there is no other choice of getting a realistic material. The only way actually patients can start working is to have these implants. Okay, so your question now, Young's modulus compatibility will always be there, but then we don't have any other alternative material than this cobalt chrome or titanium. So we still make the implants with these alloys.
Thank you.
Yeah.
Sir?
Yes, go ahead.
My question is...
I have just one question. You have transformed the phase to FCC, made it paramagnetic, etc. Will it sustain to higher magnetic fields in case one has to go for MRI and things like that?
Yeah.
The stable.
Ma'am, we are actually currently working on in vivo testing. We have 3 MRIs in our campus. So with 13 Tesla, in fact, magnetic power. So in vivo is slightly confidential. I can't. So it is actually done by one of the hospitals here. And we are subjecting to maximum 13 Tesla magnetic field density. Okay, so that results probably will publish sooner.
Thank you very much for a very informative talk. Let's start the video. Thank you very much. We have something to felicitate you, but we are not able to do it online.
Yeah, so I'm going to me, Jay can be felicitated.
Thank you very much.
So you just stay here and take for you. And you have to come here to take this in person.
And give a direct talk.
Yeah, I would love to come,
Yeah, I think this is the
one.
one.
Thank you. I see, yes. Thank you, you can do that all for me later.
Thank you very much.
Thanks. Thank you, ma'am. Jay, I'll log off. Maybe in the evening you can meeting. Okay, bye.
Let's go to the next talk. When it is Akshita Dayananda, and from Wipro, Bangalore, and she will be giving the talk on additive manufacturing and production. I request the speaker to take about 30 minutes since we are running late. After that, we'll have some questions.
Sure.
Thank you.
Hello everybody, first of all thank you for the opportunity, and since my time is less I'll get started right away. My name is Akshata Hulmani Dayananda. I represent Wipro 3D. I lead the Advise division of Wipro 3D, which is the training, consulting and conducting funded R&D and these kind of activities. So I head that department. But who are we? So when it comes to additive manufacturing and Wipro, I think the first milestone that we hit and that we're very proud of is that we printed the first metal part which is orbiting in the satellite, that is GSAT-19, even to this day. So it's about 4-5 years now that the part has been in space, and it was not a very easy build. So you can see the part here at the left hand corner. It's a much taller build or a part that you can print in the normal machines. So the machines had to be tweaked, the designs had to be tweaked, and the parts had to go through a lot of testing before it went into the satellite. So there was a lot of learning which came from that. Yes, it was a milestone, but there was also a lot of learning, and that journey kind of continues even today, because we have been putting up a lot of certified parts in various applications. So here's a glimpse of some of the parts that have been certified and are being used as, end use components. So again, this is the first one which went up in the satellite, but if you see, there are a lot of other components that we have made, including other feed clusters. What I would like to probably highlight in this is that there is a mixture of materials here. Some of the parts are in aluminium, some of them are in steel, and if you see this one here, which is called as the inner ring, that part has been reverse engineered. What we mean is that our customer had a physical model and had a drawing, but did not know what the material was or did not have a CAD model for it, and nothing was there. So we had to 3D scan the part, develop the CAD, do an analysis of the material and see what's the closest material that we could 3D print as a substitute to this. And then we developed these components, and now this is in production, which means that it's gone through a lot of testing, it's been certified, and then every year we have a certain numbers to deliver. But why did they go through additive? It's because this particular part used to be imported, and the place that we used to import it from for a defense application said that they will not supply this anymore, which means that some aerospace machinery would not work because for the want of this product, right? So that's where we reap the benefits of additive manufacturing, and so can anybody. Like I was saying, here are a lot of different materials. Some of them is Inconel parts and titanium parts. Also here in the last one, what I would like to highlight is that the general idea of additive manufacturing, when you probably start looking at it for the first time, is that you make prototypes or structural components, okay, maybe to a certain extent, but it is possible to make parts which have rotary applications also, wherein the requirements that the part has to satisfy is much higher. So it was very sequential. First you start with something that's not very critical, and then you go to critical, and then something that's rotating, and so this journey has been happening, right? And we have been in this journey for about 10 years now, and if you see, then there are a lot of other production parts or certified parts also, which I will bring to you all today. So what does it take to do it? Like I said, you have a lot of prove out to do. Selecting the right geometry is the first step, definitely. But then after that, you need to have certain process controls to prove that the part is of a good quality. Each build is of a good quality. Part in every corner of your part is of a good quality. The powder that you are using, maybe once, twice over, thrice over, is also of good quality. So there is a lot of testing, process control. Even before process control, you have to identify what is it that affects the part quality, right? Is it the powder shape? Or is it how you use your powder and store your powder? Starts with powder, but then does the part quality change when you have one at the corner and one in the middle? So there are so many parameters, and first we need to identify what are the parameters which will have an effect on the part quality. Then we have to see how to control them and establish those processes. And then that's when they get the confidence, like in this case Semilac gave us the clearance because this was a defense application, and it's a journey. They need to learn about additive, we need to learn about qualification, what needs to be done and how it needs to be done. So when we go towards what is happening around the world, I would like to state some examples coming from the aerospace industries today. We all know that tooling industry was one of the first adopters of additive manufacturing, because they were able to have applications with conformal tooling, conformal cooling, and this aided in a much better tooling parts for them. So they were the early adopters. Medical, of course, is a very big adopter, and here is another adopter, which is space and also aerospace. Now if you look at this chart, we see that AM is kind of infiltrating the production of aircrafts in all of the different spaces that is possible in an aeroplane. Not only aeroplane, but also even rocket engine. Somebody brought up Skyroot today, right? So in all of these applications, and also in the very critical engine parts as well. Okay, so it all started with GE who productionized. So this is one example of a productionized AM part. This example is of the GE fuel nozzle. Now in here you see this tip here, right? Only this one has been additively manufactured. The material is cobalt chromium, and they have integrated about 12 parts into one part, designed it to harness the value of additive manufacturing such that the flow, the injection and all of that is optimized, right? As of today, there are 100,000 of these parts flying in the LEAP engine and working perfectly fine, right? So what I would like to say with this is, when you choose the right application and when you go through that journey of validating the part, then it is possible, and people have done it, that it can be productionized. So 100,000 parts is not less, right? You need about 18 or 19 in one engine. So this is one of the first examples, and people have only gone on and added a lot of other parts, but today as it stands, people are able to print about 1.5 meter large parts using additive, and it is still making an economically good case. Of course technically, but also economically it is making a good case to print such large parts additively. So that is where we have kind of journeyed to slowly but progressively. We've spoken a lot about metals, but also high performance polymers are also are being adopted very well for the aerospace industry, and things like this is a cup holder in the cockpit, this is a panel, this is for airflow, again a duct for airflow. So even polymers are gaining a lot of traction, and being used in the aerospace industry. So why are we talking about aerospace industries? We talk about the aerospace industry because it is one of those industries which will require a lot of testing and validation to be done, right? So that's why I wanted to show a few examples from the aerospace industries wherein parts have been already productionized. So here's a list of some of the certifications that are required. Almost always as a base certification, what is required is ISO 9001, okay? And then when we want to go to aerospace manufacturing, we need the AS 9100 certification. When you go to automobile, you need something called as IATF. If you have to go to marine and stuff, you need LR, but also now you have other certifications coming up. If you have to go to medical, you need ISO 13485. Okay, a lot of certifications, but why? Why do we want to do these certifications and how is it linked to production? Because these certifications will ensure that the processes that are followed are robust, right, and are well controlled, repeatable and dependable. That is why all of these certifications are very relevant when it comes to productionizing. So a company, an institute has to invest a lot of time and energy to have these certifications to bring in the confidence to move into production of AM. It's one thing to have a few machines and develop a few numbers of first applications, but then it's a completely different game when we want to make productionize the parts. And when it is in AM, productionizing of parts doesn't mean thousands a month or lakhs a month, right? It is about tens in a month or maybe hundreds in a year. So that is the number that we are looking at. And even for those volumes which are ideal for aerospace and space applications, we will have to go through a lot of certifications. Now briefly I would like to touch upon the national strategy for additive manufacturing, which was brought out by the Indian government. This strategy was brought out in February of 2022. It has a lot of strategy outcomes, industry-wise opportunities, adoption barriers and focus areas. But maybe if I had to sum it up and say what is the message of this policy that the government of India put out. Now government of India putting out the strategy itself means that this is an important technology. And in that they said that they want to develop indigenous technological capabilities. That's one of the big focuses. And get into industry 4.0 kind of a scenario in the country. So maybe here I will talk about the adoption barriers. Even though this is named as adoption barriers even in the policy, how we should look at it is that there is an opportunity in every barrier that we see here. First is the process and performance. Today we have a few technologies, let's say laser powder bed, we have DED or something like that, but all of the processes have some of their own limitations also. If you see laser powder bed, where there is a lot of material data available, where there is a lot of confidence in people that yes, you can use laser powder bed, the problem is that the sizes are limited. You can't print really huge parts. And even if you can, then the rate is much slower when compared to maybe a DED technology. So maybe it's not fast enough. So there are a lot of performance and process barriers which need to be overcome. So this is a barrier, but if you think about it, it's probably an opportunity for all of you. Maybe you can do an improvement. Maybe you can't print a material, let's say like pure copper with laser powder bed today because of its reflectivity. And that's an opportunity for you to come up with something innovative to solve that problem, right? Second thing is material. I think the talk that just got concluded about adopting the material for additive is a really big area where innovation can happen. When we look at indigenization, on which the Indian government has so much stress and is asking us to make a lot of things in-house, then we have the opportunity there to probably go to a similar metal, and we don't need a 1:1 substitution there. So what is this substitute metal going to be, and what parameters will we melt it is what is the opportunity in material. AM ecosystem. Now I think we all understand that AM is not a standalone technology. You need powder, you need the printer, but after that you also need to finish it, post-process it. So it is another new step in the process. But do we have the ecosystem around it? Do we have local powder manufacturers? Do we have finishing operations which are around in India? Do we have automatic support removal options? Do we have all this? No. So this is again an area where we can definitely innovate. Business cases. Have we found all those really, really good parts which make both technical and economical sense to print? Not yet. There's opportunity there. Qualification and certification. Has ASTM come out with all the standards? Has ISO come up with standard for everything in additive manufacturing that this has to be done like this? No. There is still a lot of prints that is happening which will give us the data to get to that stage. And then there is legal and framework which is more about IP protection and all of these things. So just a list of few barriers which I really think is opportunities and not barriers for all of us here. Moving on then, are all industries adopting AM? Which industries are adopting AM? I will talk about what the policy says here, but I would like to mention that we are also kind of in agreement with what is being said there. When you look at the aerospace industry in India, it is the defense that will probably drive this, but and apart from that, it will be the avionics, that is 3D printing of electronics or electrical components, these kind of things. Okay, so that's the aerospace market. Tier 2 and Tier 3 kind of industries will benefit a lot from it, not Tier 1. So maybe we will not make that GE fuel nozzle, but we'll make a fuel nozzle for ISRO probably, right? So that's the aerospace sector. Defense and aerospace, I think, closely tied, but when it comes to defense, there's again Navy and all of these things which require different set of standards. Medical, I think the previous talk was really good to tell us what is the stage at which AM is in medical, so I will skip that. Electronics is coming up very big, especially the semiconductor industry, and when it comes to semiconductor industry, we have seen ceramics is something that they are very interested in. Used to make equipment, not the semiconductors themselves, right? Then we have automotive. Binder jetting technology may somewhat, maybe in a few years coming forward, have that cost benefit of making parts at a cheap rate for automotive, but we are not there today. All other things fall into industrial. Consumer is more like your toys or fashion industry, shoes. I don't know if you know, but Adidas has these shoes that are 3D printed. They have soles that are 3D printed. And the athletes will go get their legs scanned, and then the shoes are made to suit their legs. And it gives them like a millisecond of an advantage, but that's what makes you win a race, right? So all of that will fall into consumer and construction. We have somebody here also today who has been printing with concrete, right? So many different industries, each of them using additive in their own way. Some of them for prototyping, some of them for end use parts, and some of them are because you can make really unique products. When I look at electronics, they are making all these smart wearable watches, rings and all of that, and when you 3D print, you can 3D print the sensors also on it, right? So that's a very, very unique product that can come out. So every industry is using additive in a different way. And maybe with that I will end my talk. And this is some of the pictures from our Wipro 3D facility. I welcome all of you to come and visit us. I'm open to any questions. Should I keep time?
Oh, wonderful.
Thank you so much. You have really taken us a wide spectrum of steps involved, from raw material availability to realizing component to industry, what are the steps involved across realizing. Thank you so much. It was a very nice lecture. And may I invite a couple of questions?
Maybe none. Okay, there's one. No. Either it was really boring or it was super
very
clear.
clear, very nice. It is so clear that there are no questions.
Yes, please.
It's not technical, but can our students do internships in your place?
Yes, sir. You can get through our HR. We always offer.
Yeah, we would like to explore that. We have, as you know, we have manufacturing program here, master's level program. So we would like to have more collaboration.
There's so much work, we are most welcoming to interns.
Okay, thank you.
We will not be able to do everything ourselves.
It's a nice talk, ma'am. My question is with respect to some GE fuel nozzle. You have said that some 13 parts made into a single part through AM. But when we comes to replacement of the part, means if there are more some parts are necessary for the replacement, will the repair cost will be viable if we go on to a single part with respect to AM?
So GE has done a case study not only on this part, but they have an engine called as a catalyst engine. All right, the whole casing of that engine has been 3D printed with. They don't have any external pipes attaching to it anymore. So the casing is with all those channels and everything kind of runs through it. So for that, it's a small engine. It's like, I think 6 people carrying kind of a plane or something like that. What they've realized is that when they do this kind of a strategy, if something wrong goes in those components, they just take it out, put a new one and let the aircraft run. So they save on the time, which is actually money for them. So if your aircraft is stranded, then it is a problem. So then they take it offline, you do whatever repair correction is there and replace it. So it is worth, if you look at the larger picture, which they also call as life cycle analysis, LCA, then it does make sense. But if you look at the part to part comparison, maybe it does.
Thank you. It was really inspiring to see that you could contribute to aerospace and satellite applications.
Yes.
Our researchers and all will be really inspired to follow.
Sure.
Thank you so much for it.
Thank you, ma'am. Thank you, everybody. I take it, ma'am. I'm not so. Please come.
Thank you, sir. Thank you. Now I invite Dr. Inaugural from ARCI and adjunct faculty of SEST, University of Hyderabad, to deliver a talk on metal powder bed fusion, materials and case studies. Dr. Inaugural.
जरूरत है Hello. Yeah. So, good afternoon all. Thank you for the opportunity. So, since morning you have been listening to the additive manufacturing basics from Professor Jankiram and also some medical related applications, and also Wipro 3D has given some aspects highlighted, and also detailed classification of additive manufacturing has been covered. So here I would like to touch upon certain things, because as a part of a workshop, I think we have to, what is this? Okay. It's not going? Yeah. Yeah, I would like to just highlight upon certain aspects which I think as a workshop we should bring these aspects into your mind. So additive manufacturing actually comes with the three basic things: material and some method of binding that material, and then process to bring these two things together, right? So if you understand this, so any additive manufacturing classification technology what they mentioned will fall into this these three if you divide entirely, right? Even it's a powder bed, metal, plastic, whatever it is, you have material, some form, it can be powder form, it can be wire form, it can be sheet, or it can be liquid, and you have some method to bring those each unit of that powder particles, wire, melted or fused, sheet, maybe ultrasonicated or friction stir welded or something, liquid and all. Right? These are the different methods where you will bring them, bind them, and this is something powder bed, powder wire fed, and liquid bath. These are the different technologies which will bring these two things together. So these things will make, depending upon combination of these, you will see the different technologies. Right? So broadly, ASTM has classified them into 7 categories, what you saw in the first lecture. So I will not spend much time on that. So this is how they classified it, depending upon different combinations of material and process used. And these are the different schematics of this thing. It's already covered, so I will not spend much time here. And these are all different OEMs coming from all these different technologies derived from different combinations. And this is what I would like to highlight here a little bit. So you can see this is a powder bed additive manufacturing. It was highlighted that this schematic you saw in the morning. This is another schematic where powder is fed from the top and it's being spread here. And here you have a powder in the already loaded and it's being raised here and it is spread here, and the part will be made in this chamber. Right? The difference is it's top feeding and there is a already loaded, preloaded powder like the preloaded tank here. So what I would like to highlight here is the smallest unit. This is, I'm talking about powder bed here, powder bed fusion out of the technologies what we discussed, different classification. You can see the smallest unit is the one track, one melt pool. So this comes from the laser, means the beam, the energy what we are using here. It can be electron beam, it can be a laser. So let's focus on laser. The spot size of the laser will decide this melt pool, single unit. Like in a construction of a wall, brick is the smallest unit. So like that, this is the smallest unit. So this width and the shape all matters to the quality of the part, right? It's like you take a sketch pen and fill a drawing in a sheet. So how precisely you will start and you end up between the two borders, means start border and end border, and next track how you will put. So how exactly you will overlap. So if you do fast, if you take smaller tip, you will have more lines to make, and you may end up with the overlap defect, which will lead to porosity. So I am coming from laser to the defect of the AM part, right? So this is the technology. Somebody told in the morning, smallest feature you can make, highest resolution, powder bed laser, right? So but that will come from the spot size what we choose. So smaller the spot size, smaller is the sketch pen to pencil. If you take a pencil and fill the same drawing, if you take a sketch pen and fill the same drawing, so defects will be more where? In pencil, right? So, but you will achieve finer features in pencil. But sketch pen you can't achieve the feature. So we'll put that thing, entire metal additive manufacturing. According to me, I put like that. So powder bed laser, we can put it as a pencil, right? Electron beam, we can put it as a pen. And then wire arc additive manufacturing or DED. DED we can put as a sketch pen. Wire arc additive manufacturing we can put it as a highlighter, like a brush. So now you see your tools are changing. The source of melting the wire or powder is changing. So that will defining your feature size and defects. So more defects will be in powder bed because of the smaller spot size and smaller melt pool and more overlaps and repeated heating. So you can also imagine this as a one weld. Welding is how difficult and how challenging in the processing, manufacturing. So we are putting thousands of weld together here. So that will multiply the welding problems in terms of, in case of additive manufacturing, you can imagine like that. But the thing is here melt pool is small and well controlled melt pool, and we can optimize the process parameters so that we will leave the less damage to the overall microstructure and component of the component properties. So this is another thing what I would like to highlight here is there are different technologies involved for bringing the laser inside. So this is called varioscan, this is called F theta lens, right? So these are the two technologies used in powder bed additive manufacturing to focus the laser on the plane, right? So why we need these technologies? If there is a one lens, the focal plane will be curvature, right? So to keep it flat, we need a technology here which is varying here. You can see the two arrows here. And in F theta lens, this lens will play a role to keep this focal plane flat. So that is how you are getting fixed plane in powder bed additive manufacturing. There are many developments happen, so I'm not touching on that because of lack of time here. And yeah, I had a video here. I'll just go to the video. Yeah, so this is the video I'd like to show you. In this will summarize what I was telling so far. Yeah. Can you see it? So this is the powder, right? The energy you need to melt the powder. The precision, the process where you are bringing them together. So you can see how the powder will flow in the system. This is sieving, powder sieving is happening here, and sieved powder will come to the loader where you have a controlled dosage of the powder. See here. So the defined quantity of the powder will fall and that powder will get spread. This is the top loading. You will see the laser now, how the laser path is going. Yeah, sorry. Yeah. So that's the optical fiber which will bring the laser into the optic head. You can see this varying, which will make focal plane flat. This they call it as a galvo, flying optics. Right, this is how the actual process happens in the chamber. You can see the recoater is moving to and fro. So this is how the component is withdrawn, right? So with this, I will go to my actual presentation. I hope you got the powder bed additive manufacturing process and how exactly the things happen during the actual processing. Yeah. So in ARCI we have we have two SLM systems and one EBM system, and we have our own powder making atomizer. It's a inert gas atomizer, so we can make a spherical powder which is required for powder bed system, and we have related software, magic software, and we have our own in-house characterization and post-processing facilities. So we have from new material production, new material to the component and to the characterization under one roof. So this is a powder atomizing facility, right? So yeah. So with this facility, we are able to touch upon about dozens of powders in last 3 to 4 years. So alloys are atomized at ARCI, means we made a powder at ARCI, and these are all commercial powders which we touched. So you can see IN78, IN65. This is a BZL2 alloy, it's a Russian alloy. The ingots were taken from the scrap, means damaged components of a aero engine, and that were cut into pieces, and we used that as an ingot to make the metal powder. So we made BZL2LY powder, and we did some study on that. It was a sponsored project. And then we have some aluminum alloy development. There are some high strength, high temperature alloys used in aerospace, especially strategic application. So where high temperature and strength is required. So, but additive manufacturing, those alloys are non-weldable, so it's difficult to make in additive manufacturing, like 2000 series and 6000 series. So what we thought is, we'll take the additive manufacturable alloy, that is ALSI 10mg cast alloy. So modify that so that it will have a higher strength and retain for some more higher temperature, means applications can be. So we thought of in that project, Indo-Italy sponsored project, we are trying some aluminum alloy developments. And this is S13 tool steel, it's a pressure die casting die material, challenging for AM, so we are able to do that. M2 tool steel also we are working on, and we have some success in that recently. And SS321 is another stainless steel. People talk 316L, so SS321 is very rarely spoken because it's a austenitic stainless steel for higher temperature application, especially for strategic application. We are able to procure that material from third party, and we supplied some components to strategic application. And this is the alloy I was telling, 6000 series. It cracks like anything. So we thought to improve the ALSI 10mg in this project to achieve some better improved property comparable to H20. And we have some copper alloy and titanium alloy. We worked on magnetic material also for EV applications. Some basic studies have been done. We have in ARCI some on magnetic vertical. So we made some component of NDFEB test coupons, and so we are waiting for further progress on that. So this is a cobalt chrome Fe alloy medical application. What the previous the Murugayan sir was presenting, we are also part of that project, right? So we have this entire process happening, and these are the different advantages of additive manufacturing we are looking. And the next slides you will see some case studies demonstrated. So the one thing we should keep in mind for a powder bed additive manufacturing is a powder specification. So it has to be spherical because we are spreading the powder. So powder has to roll on its own so that it will spread uniformly. So we are talking layer thickness of 20 micron, 30 micron, 50 micron, 60 micron, right? So when I am saying suppose 50 micron, so your particle, so you can imagine how thin I am talking. So how I am achieving that? I am spreading that. So how good the spreading should be. If it is non-spherical, it may make a line. So one particle may sit in some orientation, it may make a line in my entire layer spread. So your particle's distribution has to be defined, and also the morphology has to be taken care. So elemental composition and all will anyway, we are sourcing it from the known source and certified source, but we have to make sure the sphericality and distribution. So when I say distribution, it is a D10, D50, D90, means fraction of 10%, fraction of 50%, fraction of 90%. So we usually talk in mostly all the OEMs talk for powder bed fusion about 15 to 45 micron, with the D50 around 25 micron, right? So if you are in that range, we can talk 50 micron, 60 micron layer thickness. And if you are really focusing on 20 and 30, you have to be little, shift towards D50, 20 micron, then only you will be able to reproduce or repeatable layer thickness you will be achieving, and your parameters will work, right? So this is the entire cycle of how powder flows into the system. So some powder, most of the powder goes into component, and there will be some little loss. It's 10% written here, but we can able to confine it to less than 5%, and in some cases it is almost less than 1%. And reusable powder, you will see some videos where I will show you how you can collect the powder back and use it. But one thing here, major inventory is a powder. So even though your part is 100 gram, but height of some 6 inch, So you have to have a powder for 6-inch height, not for the weight. So don't compare powder, okay, I want 100 gram powder, why you are asking 10 kg powder? It's not like that. So it goes by height. So height of the component will decide how much powder you need. It's not that all powder will be waste. We can reuse the powder for some cycles, but the height will decide how much powder you have to have beforehand, right? Yeah, so these are some indigenous ARCI produced powder qualification. What we did is we took a Midhani ingots and we made a powder of iron 718 and we compared with the commercial iron 718 powder available. Right, so I'll not spend much time on this. This is a paper published on this work of indigenous ARCI produced powder, iron 718. You can refer the literature. Here what we studied is the post-heat treatment. So if you have it's an iron 718 has to go to post-heat treatment. There are different cycles of heat treatment. So what we thought is because it's additive manufacture rapidly solidified, so we are treating it like already quenched. So we thought we'll use only the post-quenched heat treatment. So we tried different aging temperatures here, and you can refer the literature. And this is another material, iron 625. We did a similar study with the ARCI powder. And this was, I was telling, BZL 12Y powder, Russian alloy. So we took ingots and we melted and we studied up to the tensile behavior. You can see the micro cracks here. You can see the cracks. Because here aluminum titanium, if it's highlighted, you can see here aluminum titanium percentage more than 10%. It's a non-weldable superalloy. It's difficult for additive manufacturing. The project was to study how difficult and what kind of cracks and how it is going to be. We are able to see the components. You can see the component here, tensile sample of 60 mm height, comfortably 10 mm diameter made, but cracks are micro cracks. So if you see M2 tool steel, cracks are gross cracks. You can, as soon as you build, you will see a part coming out. But here you can see the part successfully, but it has micro cracks. So once we identify what is the problem, where exactly is the problem, and how the microstructure is behaving for such a rapid solidification, we can think of modifying the alloy or adapting the alloy for additive manufacturing. So that was the task of the project. And this is where interesting thing, what we did is we took a ALSI 10 mg alloy and we modified with the Y203. You can see here the particles are covered by nanoparticles of Y203. So we did ball milling, high energy ball milling with a very short time. So this is aluminum particle and this is after yttria treatment. You can see some particles sitting here. If you do the EDS, you can see, EDAX, you can see the particles here Y203 and here aluminum, right? So we did this and we were able to achieve 20% increase in the hardness by just adding the Y203 treatment to the ALSI 10 mg. So similar elemental modification also being tried in one of the project. So this I will just skip. Okay, and this is a detailed study of how parameters are developed for a third-party powder. So if you get a powder which you don't know, means you don't have the parameters. So what we will do is we have to go from the single track, what we saw in the last Murugan sir lecture. So he did single track, he made a melt pool, he measures the melt pool weight, dimensions and all, optimize the parameter and then choose the parameter. And in the first talk you saw the scanning pattern, right? So border, different color, down skin he was tracking support structure and all. So all these needs a different set of combinations of laser power, scan speed, hatch distance. So we have to optimize all those bunch of parameters for each sector of the layer. So that's where you can say I can use the entire parameter file for any component to be produced. So we do that study. You can see these three parameters, P1, P2, P3, they have a different power and speed, but having a good microstructure and defect free. So we compared that at a different stage and we optimized the heat treatment also. And we're able to demonstrate this. I have a component, demonstrated component in the next slides. You can see here the tensile properties. After heat treatment, we're able to achieve the on par with the conventional properties. Right. So this is another work we did, hybrid. On copper plate, we made a steel additive manufacturing. So from the first layer, first few layer is important how the interface comes out. You can see the network of a steel impregnated into copper alloy. So 3D scan, you can see here. So it's like a Mysore pak with the ghee. Ghee is penetrated everywhere. So copper is everywhere and steel is connected. So interlocked interface. So you can see the tensile property. See here, the interface is still far away from the broken zone. So it's a micro tensile test. We are able to generate the test coupon from the interface, by a wire idiom, and it's a micro tensile test. We are able to see the property, interface property better than the copper, one of the material, right? And it's published in a Journal of Manufacturing Process. You can refer the paper for more details. This is one application. We took a component. We reduced the weight by 50%. It's a DFM, designed for additive manufacturing, and we supplied 8 of these components for as a part of the project to a strategy. And this entire properties were studied and compared and qualified. So you can see this video. This will play. Yeah, give me 2 minutes, madam.
We have 5 minutes.
Yeah, 5 minutes. Okay. Good. So here in this, this video is making wall block. What I said, the 50% weight reduction. You'll see from support structure design, weight reduction, DFM to support structure design, and then manufacturing. Yeah. So this is the DFM part. This is the orientation and support structure design. You can see the red things are all support structure. So this is a slice viewer. We can see the slices virtually and clear it for the production. It's the actual process happening in the chamber. So this is how we draw the powder, and this powder which you are seeing here, this all can be used. So the part weight is hardly 4 kg, but we are using almost 60 kg of the material here. But the remaining material can be used to produce another part. This is how we are removing the support structure. You can see the different designs of support structure as it goes inside. So those are all designed to protect the particular edge and features there. So this component has interconnected lines, channels, and conventionally machining of even the design, the old design what they had. This design machining also was taking about 6 weeks time, 6 to 8 weeks time. So we are able to make these components with a reduced weight. Weeks, we can make 3 components in a week, with including post-processing time. Right, and this is another case. You can see there is a conformer cooling channel made, and this pin is 12 mm here, and as it goes up, it will become 10 mm. So this pin of 200 mm height is made in S13 tool steel, printed in ARCI, and there was no channels like this before. We added these channels for the actual application. So it's a 2.5 mm diameter cooling channel inside, and we made 4 pins. And this is as I said, it's a cast part. It is making this cylindrical, long, about 60 mm hole inside here in the cast part. So machined and placed in the actual production. You can see the pin here. You can see the cooling lines connected. This is the entire assembly which will fit on in the actual production pressure die casting process. So you can see the without cooling channel, with cooling channel, the surface temperature after every shot. So about 20% reduction in the surface temperature. And you can see the rejections become 0, and you can see the defects are almost gone. So they were able to save 2 seconds per shot. It's a pressure die casting process. They used to make a 4 cast part in 1 shot. So it's each cycle was 30 seconds, and they were used to wait every cycle to reduce this temperature to in this range. So this pin alone, entire assembly is okay, but only pin temperature has to be reduced because it's making internal feature in the cast. So if there is any problem with this pin, you will get the rejections in the part qualification. you can't even repair it because it's the internal surface. So they used to change this pin after every 2000 shots. They used to put down the entire production and change this pin and go back to the production again. So but when we did this cooling channel inside, they were able to take 6000 shots without any problem. So production increased, casting process production increased, and waiting time reduced by 2 seconds. So these are the benefits they got, and they appreciated the case study with their letter and certificate, right? This is another thing to reduce the time. It's a hybrid. We took a conventional part, and then see when the die whatever tool I am talking. So 200 mm I told, but 60 mm of that is a simple conventional machining we can do. So remaining 140 mm, 160 mm we can make additive manufacturing. So we can bring a conventional part, and then on that we can make a complicated part by additive manufacturing. So that's what we tried here. So detailed study has been done for the interface study and all. This is another iron 708 part NGV. So this is from powder to the what you are seeing here, along with holes, about 0.5 mm holes and all we have done, and there is a DFAM to adapt it to additive manufacturing. And this is another good application, I should say, for time saving. So this is the entire part we shaped like this, then we built it. When they came for second time with some more modification, so what we did is we took a conventional cylindrical rod. On that we only printed top 5 mm where we really need additive manufacturing. So these fins what you are seeing here is a 0.5 mm thin wall placed at particular angle. You can see here. So when they came back, we took a rod. On that we made AM part. Then we machined conventionally for the backside features. Then this is the final die. So this is the aluminum foil bundle which has been shaped with this die. So that this plays a very critical role to achieve the efficiency. This is actually battery application. So efficiency of the battery depends upon how smoothly you folded them. This folding has done. So that depends upon these features and the position of these fins. So this was done in 2 to 3 days from first model to this and then third model, right? So this is another application. So you can see the X-ray here, right? X-ray here. So this plate is 2.1 mm thickness, 2.1 mm thickness, and each side we have 400 micron features, and inside this 2.1 mm we have 300 micron cooling channel, right? So you can see here, can you see this small thing here? There is a thin line inside. It's a 300 micron cooling channel from this end to this end. Can you see the X-ray here? From this end to this end. There are features like this and this on the both side, and we have given a provision for thermocouple also here. So this plate has been demonstrated with the 10 numbers of these produced, and results are not here. So it's a hydrogen oxygen fuel cell plate, right? So such things are possible. It's a part integration. Previously they used to make 2 plates of 2.1 mm and they used to weld them to achieve the conformal channel inside. So now we made it in 2.1 mm, everything in one go. And this is another thing. The only thing you have to highlight here is a feature. This is the top feature. What you are seeing here is a 100 micron wall thickness with 1 mm diameter ID. So it's a stainless steel part used in medical application. This I will skip. It's a micro channel plate. So many channels here are of 0.5 and 2 mm. So here post processing played a major role, because somebody told in the morning, even achieving a fine feature is difficult in additive manufacturing. That is one of the limitations related to many things: powder size, spot, laser spot size and all. So here also we face that challenge, but in post processing we are able to manage to achieve the required dimensions. This is a extrusion die for ceramic, very fine feature. You can see here these holes are rounded inside corners. So it's usually done by iridium such dies, but you can't achieve this inner corner chamfer. So we are able to make 3D printing die, 3D printed extrusion die in aluminium, which gave you extruded part with the required features. This is during COVID. We were called to make these components. So John sir is here. So we were able to make these things in 2 days of during COVID time to one of the DRDO developments required for a COVID related applications. right? So these are all some other components we made, just to show you. This is one component we made it for BDL Vizag on weekend. So Friday they had problem, so we got the reverse engineering done of this part, these two parts, and we printed on Friday night, Saturday afternoon it was ready, and they took, and Monday they placed it back and the production was back. So yeah, such things are possible. And this is another bark requirement. We're able to make these spaces for a small scale reactor. Right. The EBM what we have, this is electron beam. So we are focusing as of now on medical applications. So these are some components made out of TI64. And we have some hydroxyapatite coating technology being developed, coating on these titanium alloy parts. Yeah, thank you, madam.
Thank you very much for discussing with us all the developments. It is very exciting to see, not just in India, but within Hyderabad there is so much development in the additive manufacturing. And also for the videos, which gave us a clear picture of the support structure and how much intricacies are there in the design of the parts before you take up the process.
Thank you.
Yeah. So can you have
Guru, nice talk.
Thank you.
Two questions. Very trivial, but it came to my mind. See, if I see the powder morphology, the powder that is prepared in ARCI, it has a lot of satellite particles.
Yes, sir.
And it is well known that in air atomization, no satellite particle
yes, sir.
It forms basically. Does it cause any effect?
Actually, we play there, sir. Whatever I said, no, exactly you have to be there and all. But as a process domain expert, so we have some window to play there in the machine. So we as I said, if you want to play with 30 micron, you should have a particle size in that particular range. So what we do is we just increase that window according to the particle size, and those satellites were not serious problem to us when we did. But in between, what one of our colleagues suggested is just do a ball mill, fast ball mill, and just take care of those satellites if they can remove them. So we tried that also, so it worked.
Thank you.
Yeah.
Second thing is, see, this is basically melting and solidification process, right? Do you have any control on cooling? Because, in my opinion, cooling has something to do with the roughness of the final layer also, am I right?
Roughness of the component depends upon the layer thickness, first of all. But cooling, when you said, in fact, we want preheating here. And the cooling rate, what you are telling, the melt pool, what we are talking is 100 micron by maybe about another 100 micron by 100 micron, you can say. So such a small melt pool with the entire area at other temperature. So it's a rapid solidification. The modeling simulation shows that process simulation. Cooling rates are about 10 to the power of 6 to 10 to the power of 8 Kelvin per second. So in laser cladding and all, we talk 10 to the power of 5, 6. Here it is 8, 7 and all. So such a high rapid solidification. So we can't control that cooling. But in some applications, what the other speakers were telling, and M2 tool steel and all, we want heating instead of cooling. So we want to maintain the temperature of the entire bed above certain temperature for depending upon the material. So we always keep about 100, 150. As of now, 200 is available. So we try to heat it, but cooling it to such a small melt pool, controlling the cooling rate is challenging. In EBM they try, but entire bed temperature they try, not the melt pool.
Hello. Thank you for the nice talk, sir. Actually, the question is about the reusability of the powder. When you are using that laser, then powder particle are going to be, means that one particle is going to be melted and the nearby particle is about to be melted. When you are going to be reuse it, then its characteristics is going to be changed.
Right.
Then when you made that component about to reuse it, then the properties of the component is different, altogether different, that fresh powder.
Yeah. So what we do is, first of all, we limit the number of cycles to be used. So we can't keep on using the same powder, right? And after certain number of use, we add a fresh powder to it. So we'll reduce the effect. And the changes what you are talking is not much. And we sieve the powder after every use, before using, because we have to sieve out the agglomerates what you are telling. The particles which are affected or agglomerated got too much heat than the required, they will get agglomerate, right? So those things will be sieved out with a particular sieve. So when I said my particle size distribution has to be like this, 45 is the maximum. So I will sieve with 50 micron or 60 micron sieve. I will make sure that my particle size are within. So the expose of heat to the particle to the heat, it's I told rapid solidification. So it will not be that much time to change the entire properties of the particles, right?
Is there any certification of that powder that there is some raw material is there and then you made your own powder? Is there any certifications for that?
Yeah, there is a certification by Simulac in India. They certified one of the powder for IN 718 for one of the OEM. So usually it's they tell this is what we have. Powder supplier will tell I have powder of this composition and this is the specification. So
one more question last. What about the cost? Actually, when we go for the SLM, that the product cost is much more higher than the conventional manufacturing methods, because that powder cost is obviously in lakhs or 18,000 or maybe more than that per kg cost. If we use that, let's say 60 kg or 100 kg of that powder, then obviously it is very much high that conventional machining.
The initial cost, inventory cost is high. She explained, I think, the previous talk, how you have to see the cost in additive manufacturing. You can't compare like just conventional one part and additive manufactured one part. You have to see the entire cycle, life cycle. So where else you can use that powder also you have to see, and how many components can come to you in a year of that material also you have to see before getting into that.
Okay, sir. Thank you, sir.
And there are different advantages compared with, if you are comparing with conventional, there are different altogether advantages. Then only you have to come to additive manufacturing. So seeing that advantage, you have to balance your, all the economics and business involved.
Excuse me, sir. Just extension of same questions. How much percentage of powder we can reuse, and for how many cycles we can use?
I can't tell you the number, but I gave you the percentage, right? So, yeah, we are using 100 kg of stainless steel with my experience. Even after 6 months, we are running the machine continuously. So, I was able to see the oversized particle of some 100 grams, right? So, it all depends upon your parameters also, how smartly and how smoothly you are making each layer deposition and all. And entire process is happening in inert atmosphere. Okay, oxygen is maintained below 100 ppm. And oxidation, if it happens also, we remove those oxide particles which are flying away from towards the gas loop. There will be some particular zone, it will fall there, and we remove that separately. We will not mix everything in the chamber. So if you know the operation one cycle, you will understand how the operator is taking care of the powder during the entire process.
Hi sir. Sir, when you print any actual part to be used in the real life application, have you seen any property change with respect to the orientation of that part, like the printing layer orientation?
Yeah, you saw some properties in some few slides, horizontal and vertical. So that is a simple thing we do every time. Okay. 45 degree horizontal and vertical. So mostly first we study horizontal and vertical, and then the best parameter we take for 45 one test. Right, so there will be a change because it's if you are talking as built, then you will find the difference. If you are doing post heat treatment to nullify it, then you will have a better chance of achieving isometric properties all along. So there will be a difference.
Okay. So when you how you optimize parameters, you directly go for a trial and error method, or are there any simulation methods that you use?
there are many ways to do it. So we don't have any process simulation as of now. So we take a parameter window and we choose that. First we eliminate by density and then porosity. Then we choose the best parameter for further study.
So in all these parameters, when you apply, you will be making some trial samples, right? So in the actual part, when you make out of the last one,
along with the part, the test coupons will be built and they will be tested separately.
So how matching the properties of the final product will be with these trial samples?
You have to see. They do structural analysis, but process simulation has to be done to see that what exactly you are asking. Yeah.
Yeah, Dr. Gururaj. I have a very rudimentary question about the spot size and the minimum feature definition. Is it correct to say the spot size, laser spot size defines the melt pool size, or is it correct to say
material
or e-beam size, whatever?
Okay.
Or is it correct to say the power per unit area interaction defines the, because many students are there, which one is the correct way to define that?
Yeah, I would like to say it's both. So because you can't change the spot size, once you buy the machine it's fixed, right? There are very few machines, they are giving you option, but they will come and change the spot size if you really want. So, but the machines what we have getting in from OEM, they are fixed 80 micron, some machines are with 60 micron, some machines are with 100 micron, right? So spot size is fixed. So now what we are doing is, depending upon my particle size distribution for a given material, I am defining my parameter window. So there, what you said, the second part will come into picture. So my 100 micron fixed laser spot will limit my parameter window to achieve the features. So features are fixed by 100 micron, and then within the given window, you can go from 100 micron to 120 or 100 micron to 80 micron. So your scan speed and power will decide that. Means ultimately laser energy density will decide that. But as I said, it's not one laser, one scan speed, one power, one scan speed, one hatch distance for entire layer. Depending upon the section, border will take different combinations of these. Hatch will take different combinations of this, downskin will take different combination of this. So there are different sectors in a layer. So we have to have a different bunch of that. There we have to define our own power and speed to achieve the required melt pool width. But 100 micron will define the entire range.
Thank you very much. I think that there should be some tips for the students to go and show them.
Yeah, you are all welcome to ARCI and see yourself what is happening. Yeah.
I have one small question about you have a metal pool and you have borders around the metal pool. So the anisotropy of the property, will it get minimized when you do post-heat treatment?
Yes, madam. Yes, madam. Post-heat treatment is for that.
Helps?
Yes, madam.
So, thank you very much.
Thank you, madam.
I request you to please present the shawl and memento.
It's okay. It's okay.
Congratulations, doing excellent.
He is the afternoon speaking.
Roy Johnson?
He is our associate.
I would like to express my thank you for ma'am, and I like Professor Koti sir to please. For the third session of RAM 2023, we request Professor Koteswar Rao sir to chair the session.
Thank you, Harita. I welcome you all for the post-lunch session. It is extremely challenging. You're all privileged. You get a chance to sleep. But myself, as the session chair and the speaker, at least we are not supposed to sleep. And I request our speaker also to make sure that you won't sleep with his talk. In this session, we have 3 talks. All are invited. The first one by Dr. John from DRDL. The second will be Professor Surya from IIT Hyderabad. Third one will be by Professor Vishwanath from IIT Hyderabad. So I request Dr. John to start his lecture. Sir, is it possible to make it in 30 minutes? You were given.
I'll skip some other things.
Yeah, to cover up something.
Yes.
Thank you.
So I can go up to 250.
Okay. Yeah.
So good afternoon to all of you. So it is a great pleasure for me to give my presentation at this workshop on RAM 2023. Okay, first of all, I thank the organizers, University of Hyderabad and ARCI for inviting me to give this presentation lecture on this topic. And again, they put me in some difficult situations. They have given a very good lunch. So we all had a very good lunch. So I also enjoyed. So now, it is for me, it's difficult to keep you all awake, but I will try my best. Okay? So just going to my presentation. So myself, John Vasaria Jagaraj from DRDL. So I'm now presently I'm working as technology director. So my areas of work is on product engineering, product development, and additive manufacturing for some last 5-6 years. Okay. So this topic is on additive manufacturing technologies and its opportunities in aerospace applications. So in this talk, I will be presenting not on the pure technical part of it, how it is be useful for defense applications. So it is generally it's a overall general talk. There will not be much deep insights to be there, but how the technology is used for different in aerospace and defense applications. So we go with the presentation. The contents is like this. It is just start with the introduction. So I think you might have already exposed in the morning sessions what is the introduction. I will also start with go with the same introduction, but how it is used for defense applications I will be connecting then whenever the slides are coming. The categories of additive manufacturing, all you may be knowing, and special applications. So there I will just put some special applications which are relevant to for our application for defense applications. Then additive manufacturing process defects and qualification. Maybe I will skip these things for want of time, and some case studies, challenges, and conclusion. With this, we'll go with the presentation. So I need not to explain all these things, but so it is again start from CAD model, conversion into STL file, slicing software, additive manufacturing, and 3D object. All together comes under the process of additive manufacturing or 3D printing. So it is done by layer, and all you know that these are the 7 technologies, starting from wet polymerization, material extrusion, material jetting, binder jetting, powder bed extrusion, sheet lamination, and DAD. So it is change the concept. So when we want to do the design to manufacture, now it is manufactured to design. So it is giving the designer the more flexibility to go for the make the components, think of their products, and some of the products I will show the applications in my future slides. So with these 7 technologies, so now we can see that there are a lot of technologies. Depends on the type of input power, type of materials, type of what are the methodologies used. It depends on that one. You can see there are number of technologies which are coming out, and more things are getting patented. So anybody is having some ideas, you students, researchers can think on these technologies and put your efforts to make it a new technology. So like, say for example, if you take a wet polymerization. So whether it is cured with laser or cured with light. So 2 different technologies. Whether it is cured from the top or cured from the bottom, then again 2 technologies. So there are different peoples, different startups are coming. I can say we can go through discussion with so many people. We can see that lot of startups are coming with these technologies. Okay, so the same way material jetting, material extrusion, binder jetting. So it can be this. It is not the limited. It is a big table, you can say. Okay, so just a brief breakthroughs in the additive manufacturing. I want to highlight when each technology has come into existence. Say for example, if we can say that additive manufacturing is from 28,000 BCE. So that time the complete ceramic artifact we started using the ceramic artifact, part making, everything. So though it is a very old technology, then in 1984, SLA was first, Charles Hull has patented that stereolithography apparatus, SLA. Before that, in 1980, Ryo Kodama has just identified the material for this, which can be 3D dimensional model regarding the manufacturing of solid printed model. Then the SLA has come. Then when we say in 1987, SLS came into, Carl Descartes has patented SLS. Then in 1987-88, Scott Crump and wife Lisa Crump co-founded that FDM, Stratasys. Then FDM came into existence. Then in 2000, POM, Precision Optical Manufacturing, they founded the DMD machine. And EOS has 2003, EOS has come with that carbon dioxide laser printing machine. So these are some glimpse of this technology. So to say that the technology is very recent, it is last 20 to 30 years. So that is the way the technology has developed. So what are the application areas? When we have to go for this additive manufacturing. So whenever there is any optimization, whether there any shape or size to be reduced, weight to be reduced. For us, it's one of the very important things where the weight to be reduced. When any flying component, the weight should be minimum. So there the weight is very important. And number of parts. Morning our Dr. Guraj was explaining about the wall block, where the number of parts is made into a single wall block with additive manufacturing. So such type of challenging jobs we can go for additive manufacturing. And saving of resources. When there is a real saving is there, then we can go for think of the additive manufacturing. Say like either it can be cost saving, time saving, or material saving. So in the last slide we can see what is the decision matrix when we want to go for this additive manufacturing. And another one is repair and replacement. So to reproduce obsolete parts. So this is one of the things which we are now using, because our machineries which are in our defense applications are very old machineries. Now we cannot able to get new machineries because of lot of band and defense things. So what we are doing, we are not able to get the parts. So we are making the parts for us. So even recently, every week I am getting some requirement from our workshop to get some seals or some type of components, which we are not able to get from the market. We are making it ourselves and getting it done. So we take the measurements, we make the part and use it. So such type of things, there is no other go for some other technology. So additive manufacturing is one of the promising technology. And whenever any complex design is there, so when we go for conformal cooling, so such systems, some lattice design, some new materials, meta materials, then we should be afforded to go for additive manufacturing. Then in the case of printing in space, printing in remote locations where we cannot keep the inventory of the materials, so such times we have to go for additive manufacturing. There is no other go, because when there is a part can be made by conventional manufacturing, then we should not go for additive manufacturing. That is the thing. So whenever there is a need, so that time we have to go for the additive manufacturing. So these are some of the parts, so which is done in US, 3D printed barracks, which is used in building, 3D printing in buildings. Any test repositories are there, they can tell about how it is used in different applications, and lightweight metal alloys, and like printed runway for aerospace. So these are things actually when we want to make a bigger components. So like combat vehicle hulls. So that can be made with, because normally what happens, we have to take a big block and machine it out, lot of materials will be wasted. So that times we have to go for additive manufacturing where we can save the materials, very costly materials. So that's other applications. So why defense sector is interested in additive manufacturing? So when we want to reduce the lead time for product development or produce the parts in complex geometry, when we want to optimize the design, reduce weight of the components, or it can be functionally graded materials. So these are the applications where we want to go for defense sectors want to go for additive manufacturing. So like say for example, when the production volume is more and complexity is less, then in that case additive manufacturing is not the right solution. When the complexity is more and then production volume is more or less not, I cannot say it's less, we can go for medium level listing. So in that case we can go for additive manufacturing. So I will go with the 7 technologies, but how it is used in defense applications, that I will be relating. So stereolithography apparatus, so it is like VAT polymerization. So it can be either top down, so whether VAT can be kept in the this thing, so the laser can be from top or laser can be light from the bottom. So these are 2 technologies, DLP based SLA and this thing. So it is having very wide materials, like Formlabs machine is there at our place, at our DRDL. So it is having a very wide variety of materials, and we are using it for different applications. Like what I say that there are some very small features which is used in transmitter components. So we are making, previously we used to make it with conventional materials and do with light of machining, and which we are facing a lot of problems. Now we could able to do it with these materials and some seals and O-ring materials that I told, that old machines which don't have the parts, which is not available in the market, I cannot go it. So just making it, and it is used, and it is now actual machines made into operation. So this is something like 2 months back we did this component O-ring, and there is another component which was done in 2 days back. So it is kept the machine actually, which is making it one of the very critical machine was under breakdown. When we put the part, it is now working. So this is so that way it is useful for certain applications. So we are making flexible parts with this technology. Apart from it is having very wide applications in different biomedical applications, everything. But we are using it for making flexible parts. And material extrusion, so it is like fused filament fabrication. It is 2 things, one is FDM or FFF, fused filament fabrication. So you can stop me anytime actually, because I am going fast because these technologies are known to all the people, but I am just linking with the components which I am made with these things. But if anybody is having any doubts, you can stop me. Okay, so like FDM, I think you may be knowing that it is having a strategies as patented FDM. So people came out with fused filament fabrication, which is not having a heated chamber, it is a normal cooled chamber. So with these 2 technologies, we can make use of different materials by extrusion methodology. So we are making components. Actually, this is a facility, strategies machine facilities at DRDL, at my division. So we are making components which is used like supports. Actually, this is called supports. Sorry. These components are called supports because it is guide the missile inside the canisters. So these components which will fly away once, which will fly away once the missile comes out. So we want it very lightweight, and anyway, it is not going to be used. It's not going to take any loads on that one. So that type of things actually what happens, but the problem is when it's flying, it should go out of the missile path. So how much is going out, it is depends on the design. So how it is flies depends on the aerodynamic this thing. So there will be a lot of changes in the design will be keep on coming every day, morning one design, afternoon one design. So they want to make it trial, do the trial, see that how it is coming out. So this gives one of the wonderful technology which is given a lot of supports. Otherwise I have to make it in aluminum, means I have to take a block, machine it, it will take 3 days, then I will put it and then it fails. Then another thing. But it is done in the morning we did, within 2 hours we printed and made the component and checked. So that is an advantage which we got it. So this is support, and this electronic gauge. So what happened, you can see the component, I don't know whether everybody is clear about this thing. Actually it is having a lot of stiffness in between, and it is one of the lightweight component. So it is just to hold that electronic packages in position. But what happens if you want to make it in aluminum? Previously it was made in aluminum. So what happened, there will not be accessibility for the tool to have machining that component. So it was, so we suggested why don't we go in additive manufacturing. So we selected different materials, we worked out different design studies say that where we have to provide extra stiffness and everything. Then we made it printed, then we have provided all the screw inserts into that one, so that the components can be fixed on that. So with that one, actually we found that actually this is one of the good thing which is very saves time, which cannot be made with aluminum. So we with plastic material we did it, and it was used. And there are other components like opening mechanism, flap opening mechanism for missiles, everything we did with this one. Some of the things has flown with the same components. And this is the last one, that this component. It is again called a subboard, which we want to study the center. It is a tungsten material. It is a conical this thing, that it is like a bullet actually. When the bullet is going through some medium, so how it generates that waves actually, that aerodynamic structure you want to see. So that one, that blocks us to fly off. So these blocks, if you want to make it in nylon, so it takes a lot of material, but if you do it in additive manufacturing, it saves material. So that one we made some components with that one. Okay. And same way, continuation of material extrusion. There is now pellet printing is there, where we can use the pellets. The cost of pellets is, I think, 1/10 of the cost of the total in wire form. So that is a technology. So pellets are being used for some applications. Recently it has come, some people came to me and they explained about this technology which can be made with cheaper components. Okay. And another one is the continuous carbon fiber. So which is one of the other important things which is used in our applications, where because the carbon fibers gives better strength. So with using carbon fiber and polymer, because carbon fiber itself will not have, we cannot use it because we cannot have layer to layer bonding, things will not be there. So we use polymer, the polymer used as a bonding agent. So it can be like any of these techniques, like in situ pregnation or co-extrusion. Anisoprint is giving it the co-extrusion, tau preparation, extrusion like Mark Forge, in situ consolidation, Arrivo and DMM is desktop metal is giving, and inline impregnation. So we are also working on to develop one of these technology to make our components, lightweight components with carbon fibers. So this is a thing. So material jetting, so I need not to say, actually it is used in jewelry things. So it is used very well used in making jewels with wax patterns, and it can be used for high volume jewelry, and we can design what are the jewel patterns we want. So it is very good market actually. I can say when we see the engineering things, this is having a very good market. I can say that so many people are working with this technology. I think in Hyderabad itself there's so many machines are there, and the material cost itself, it is market is very high for these items. Okay, then aerosol printing. This is one of the good application when we make patch antennas for special application, when we want to make very small antennas, and say you can see that the components which is there in mobiles and these antennas, which it can be made with 3D printing. So here the size will be, feature size will be in 10 microns to millimeters. So there actually this is one of the technology which we are also exploring, and we are using it for some embedded sensors in our applications. Okay, binder jetting. So binder jetting is one of the good technology, and GE did a lot of work on this binder jetting. It is, when compared with powder bed fusion, it is cheaper, and copper printing can be done, and since it use some polymer based binders, and it once the printing is completed, then it goes for what you say, debinding, and then it goes for sintering. So what we get, we can make components with ceramics and copper. So ceramic components, already we are working in some ceramic components using this technology. And powder bed fusion, so everybody knows, I think morning onwards so many presentations, just all some 5 different names like DMLS, SLS, SLM, all these names belongs to this same powder bed fusion, and we have the facility at our DRDL. And this component, what are the components used with this one? So these are some of the components which we made with these things, like wind tunnel models. Wind tunnel models were actually normally used in wind tunnels to check the aerodynamic characteristics of any missile models. So, so the components has to be made. So normally the lead time to make the components is 4 to 6 months. But due to the recent reducing the time for lead time for the projects, so we have made this model within a 3 weeks time. So it's some 6 months model to 3 weeks. So the model was made in 3 weeks. It is hypersonic wind test demonstrator vehicle. So it was done completely, and then it was tested, and the data was given to aerodynamics, and within 1.5 months time the test was conducted. So that is a necessity, but there are challenges. How to get a wind tunnel models need a very good surface finish. So anyway, I will be discussing on the challenges on the last part. So it needs very good surface finish. And this part, like a toroidal bottle. So this is another thing, is a gas bottle. It is a diameter of approximately 115 mm. So this gas bottle should be, normally conventional method should be made in 2 parts and should be welded. So it needs some electron beam welding. It's a titanium material. So we should not have any splatter inside. So that is another challenge. So that also I will be discussing in the forthcoming slides. Okay. Then apart from that, EBM. So electron beam melting is another technology similar to SLM, but we want this technology for some refractory materials, some materials which was kept in controlled environment. For say example like C103, tungsten. So such type of materials we want to go for printing. So EBM is the only methodology. So anyway, so we are, but the problem is the issue is that it cannot. The layer height is to be slightly bigger in compared to SLM, so we cannot get very intricate parts, but it is useful for certain special materials, refractory materials. So it's sheet lamination. So it is like laminated object manufacturing. So it can it is used for different applications, and mostly is for making some demonstrative models. And the ultrasonic additive manufacturing. So this Fabrisonic has come with that ultrasonic additive manufacturing, which is under the same LOM. So there actually we can make a small stiffness. Actually, when we want to make lightweight components, the stiffness has to be made with very small thin foils. So there actually we are finding this technology is useful, and we are working out on some stiffness in some airframe sections, which in the airframe sections are very thin, like 0.5 mm. So wherever some components to be loaded, that region to be stiffened. So that region, this is the technology. So direct energy deposition. So it is like again powder feed. So it is anyway. Actually, Professor Surya is already there. Actually, he will be explaining about the large size additive manufacturing, which we are already working with IIT Hyderabad from DRDO. From DRDO the project. So this is one of the machine. Actually, it is developed actually at IIT Hyderabad. It's one of the biggest. It is having a size of 2 meter by 2 meter by. Yes. Yeah. So 2 meter by 2 meter by 3.5 meters. So this is a machine which is under progress. It's already it is being developed by Professor Surya and his team. Okay. So wire arc additive manufacturing. Just I'll skip all these things. And this is another thing actually which we have recently started working on hybrid metal additive manufacturing, which we want to make some repairing of components which is made with our existing components. Okay, so I just skip on this one. Anyway, this melt manufacturing is another one thing which is like friction stir welding. Similar technology is used for solid state 3D printing. So ceramic parts. This is one now special applications, like ceramic parts is one of the special applications for defense applications. So there are different technologies are used. So we are working on some like VASP machine to print some radomes and such type of ceramic radomes and that type of things. Okay, then composite parts. I was just explaining about this composite technology which we are working on making composite for lightweight composite parts for some components like This is one component which I told, the renal cage, and there are other components which is made with this technology. And is another one good thing is making of additive manufacturing of solid propellant grains, rocket grains. So here actually what happened, solid propellant rocket grains are made with a mantle, which is mantle is kept and the propellant is poured into that one. So it is always difficult. Sometimes integrity of the component is very important. So but when we want to make smaller components or smaller missiles, there actually the mantle making and putting into that one is difficult. So this is one technology is coming up with making solid propellants. And 4D printing. So apart from 3D printing, the next step is 4D printing, where the either time or temperature will be used as a next dimension to deploy the material. So it is used in some wearable technologies, some smart wings and other things. 5D and 6D printing is nothing like with having a robot based same technology. And lattice structures, just I want to explain just one minute on this one. So this lattice structure is one of the very good technology, actually one of the very applications in additive manufacturing. Reason is that, see, there are certain components we want good strength as well as good dampening effect. So when we want a good damping effect, so what we do with the lattice structure and we infiltrate with some polymer materials. So when we do the infiltration with the polymer materials, it provides a damping effect as well as it provides good strength. So there are different techniques which can be used for these things. So it is up to the designers or researchers, they can work on these things. And just going to a process, just skip this thing. Actually, anyway, it is a complex process, a multidisciplinary process. And the defects, anyway, I think somebody might have already discussed about this thing, the porosity and the crack inclusion bonding defect. So these things, some of things cannot be avoided, but it can be done, it can be engineered to get the product. So I can say one small story in that one big. So we got even additive manufacturing, sometimes the porosity is more. Actually what we say like T by 10, like thickness is 2 mm, so porosity is allowed is T by 10, 0.2 mm up to 0.2 it is can be allowed. But some cases it's already, it is more than 0.2 also, because of the layer to layer, actually because in additive manufacturing is made by layer to layer, the layer to layer morphology is different, so it can be engineered so that even the porosity is bigger, it will not propagate. So that is advantage of that one. So these are the different verticals. When we take any additive manufacturing, we can go for, it starts from design and optimization and goes for materials metallurgy and goes for AI and qualification. So I just skip all these things. These are some case studies, as I told, the wind tunnel models. So here the challenge is that finishing of the components for N5 or N6 finish and inaccessible features. These are limitations which made these things to go again. And conformal cooling channels, we have made some conformal cooling things which for special applications. And this I told about the bottle. So it is actually, there is some design for additive manufacturing was done, and it is having inaccessible features inside. It's a completely single bottle without any weld. So it was done, it was qualified, and chemical polishing was established to clean the surfaces, internal surfaces. And then we did the CT, and it was actually, it is supposed to, I don't know whether I given that. It is supposed to do 1200 bar, it has to withstand. It went up to, in that our bus test, it went to more than 1380 bar. So that is the thing, the quality of the additive manufacture part. Okay, these injectors, I think recently Skyroot has claimed that it has made the cryogenic engine, the one too, with that one with the 3D printer. Even we did some components with this additive manufacture, we are using Inaugural 718 and SS. Okay, these are some of the plastic components I already explained. So these are the challenges. So what are the things? Challenges is like when we go for larger build volume, we don't have machines, some things we have to develop. And when we go for high temperature materials and things, we don't have the materials in India. And porosity and full dense part is another limitations. And finishing is another thing. So we say that finishing for different plastic things is already there. But hipping is one of the constraints. We don't have the hipping process in many of the external industries. Hipping is one of the constraints which we go with hipping, the properties better enhanced. and other polishing, and we established chemical milling for this one, electro polishing for some of the components for additive manufacturing. And coming to the last but one slide it is. So when we want to take a decision strategy, so we have to think about the bite to fly ratio. So what is the ratio of mass of the starting billet and what is the mass of the final finished component? So normally in additive manufacturing, so typically in subtractive manufacturing it is with 10, like in the case of subtractive manufacturing, but in the case of it is like 10% of the initial material only goes into the final product, particularly in the case of additive this thing. But in the case of additive manufacturing we come closer to 1. So that is the thing. When it is coming to 1, then there is a need to go for additive manufacturing. Then saving of resources, as I mentioned, it is can be like cost saving, time saving, material saving, optimization when we want to optimize the shape, weight, number of parts. Or if it's a complex design, when we go for lattice design, metamaterials, there is no other go, we have to go for additive manufacturing. And digital manufacturing, it is printing in space or printing in remote locations and replacement of parts. So these are the things which mandate that additive manufacturing is needed for certain applications. So concluding remarks. So additive manufacturing is technologically enabled innovation, and it's having a potential to disrupt the manufacturing sector, aerospace manufacturing sector. There are challenges in adopting manufacturing technology in aerospace. Still, we are not flown any components in particularly from the with the additive manufacturing company. It has to undergo a lot of qualification tests, and there is a lot of R&D efforts is needed for making full dense parts, property enhancement of 3D printed parts, qualification and finishing. With this, thank you for your patience. Jai Hind.
Thank you, Dr. Chan.
Yes.
Now we have time for a few questions. Yes.
Hello. If you want to fabricate a product using multi-component alloy system, and if has a different melting point metal powders in that, which is one is highest and lowest, what are the possible difficulties which may arise during producing the product and how to overcome those?
See, actually I am not an academician. I can say academicians can work out, tell what are the things, but we cannot go from higher melting point to lower melting point in a single stage. You have to have the materials in between. There is functionally graded materials. So we have to have the step by step to go to the highest melting point and the lowest melting point. So we should have the grading in between. But anyway, actually it is an academic question. Maybe somebody as a metallurgist can work out that thing, but we have not worked out on that things.
Okay, thank you.
Yeah.
No, it's pre-alloyed now. It has only one melting point. That's all my actual.
Yeah. Any other questions?
Is quality control maintained by additive manufacturing?
See, quality control is in what you say. It is not in only one place. We have to start from the powder, the process, and finally even the operator who is doing that one. That is also another quality control. Then the final product. So product qualification is like we have lot of tests to be conducted on the part for product qualification. But process qualification is one of the important thing, which already there are some standards that already came out from ASTM as well as DNV, and they have already came out with certain standards. So based on that, it has to be qualified from the starting material. So what is a powder material and what is the process is used and repeatability of the process, everything to be qualified. It is not only qualification starts with only one thing, but final product qualification, it can be goes for functional test. As I told in my case that air bottle, gas bottle, we went for proof pressure test. We go for next all the tensile test properties on the specimens will be done. Then micro macro structures will be done. Then porosity will be measured, and CT will be done, and finally we go for a burst test. So that will qualify the product, but process is different.
Okay. So I have one question.
Yes.
Where do we keep this AM? Is it in net shift technology or near net shift technology?
You can say near net shift technology, because actually we need the final machining. So because of the surface finish and the requirements is there, so we can say that certain places we want to go for closer. Actually, what we do actually in the components, we keep some 0.2 or 0.5 mm extra material on the top of it. Then we go for finishing. So that it have the so one of the reasons is that what I can say, because of the powder particles, again in microscope you can see that there is small pores on the surface. So what happens sometimes, our people think this moisture is getting into that one, so which is creating problem. So we need it to be do with some machining things. So we have to complete with conventional machining.
Do you see any optimism that in near future we can make it as a net shift technology?
Yeah, actually certain areas we can use it. So when we what you say, because particularly another thing is another now upcoming areas that the laser beam structure. So how they use that laser this thing. Actually we are all using one type of laser beam which is having a different pattern. But when we want to do some type of modifications on that one and able to give a small glazing thing on the top of additive manufactured part, so that if there is no actually particles will get glazed. So then in that case it is so the finish will be good. So we can able to. But actually it is again needs. So it is having laser beam shaping again. Right. We have to change it. So it should be hybrid. So that those things are there.
Thank you, sir.
Yeah.
Yeah, we have some formalities.
Good afternoon, sir.
Yeah.
Actually, I have one practical question. Being the aerospace industry, on which material you are focusing more, and that too on which parts? Theoretically, we are doing lot of work, but you are belong to DRDO.
Yeah.
That's why I ask you questions, sir. I think so. IN 719.
So I can diplomatically say that. See, for example, recently Semilac has qualified Inconel 718.
Yes.
So it means that Inconel 718 is widely used. So that's only they went for the qualification and it was completely qualified.
Only powder or all process ecosystem they have qualified it, sir?
No, it's a powder. Actually, first of all, the powder has to be qualified.
Okay.
So before using it in a material, so Inconel 719 is one of the aerospace powder which is widely used. So DRDO has approached Semilac to qualify that one. So it is now qualified. Next, we are working on SS316. Aluminum is less, because aluminum, actually very few in the labs working on aluminum, because when we go for lightweight materials. SS316 is another thing. Next one is working
what about
titanium?
What about precipitation kind of system, sir?
See, precipitation hardened material like 17.4 pH is already there. But say the requirement is very less. Say for example, one of the wind tunnel models was made with 17.4 pH. Okay. But when we make the total components made out of all the things, we can see that one is very less.
So the problem is about material performance, or?
That's not the material performance, the application performance. So see what is the way I look into that one is like, so if I go with the component and the cost of that component, if I go with the conventional machining method, if I get a 15.5 pH or 17.4 pH material which I can get it from the market and go for machining, the cost will be very much less when compared with go with this thing. But when I go for the like Inconel 718, there's actually an engine component. Engine component for making is we have to take a big block. So the cost of material will be very high. So then that case we go with additive manufacturing so that we get the advantage of that one. So instead of making some simple parts. So that is the thing.
Thank you.
Thank you, sir. We have some formalities to perform. From the industry. Thank you. Nice. The next talk will be by Professor Surya of IIT Hyderabad. Surya, we request you to finish in 30 minutes because of time constraints. Is it possible?
It is possible. I don't need a pointer, that's fine.
You don't need,
Because for 4 screens, pointer does not make sense.
Okay, okay.
Pointer is used for a single screen. I think this you can switch off. So one is enough. Okay, good morning everyone. Good afternoon. And I hope you had good lunch. And thankfully, Dr. John took the first challenge of post-lunch session. So I'm thankful for him. Okay, so let me start. So the topic I am covering is on large area additive manufacturing of metallic components. So let me start with a very rhetorical question. Okay, so you go to any conference, go to any event, and you kind of keep listening that additive manufacturing is the future, additive manufacturing is the wonder tech of the technologies, and additive manufacturing is great. Okay, and it is actually. Okay, but you go to an industry and ask them, what are the actual components, proportion of components they are making through additive manufacturing? Okay, and you'll realize that that number is very, very small. Okay, so what is the reason why the expectation or the promise or the potential of additive manufacturing, and trust me, it has a lot of potential. Okay, I think we are really underutilizing it. Okay, and what is the reason between the gap between the potential and the actual usage? Okay, so there are many reasons, of course, but in my opinion, at least I would point out to 3 of them. In addition, certification is another thing. So certification of additive manufacturing is a major challenge or a bottleneck. But beyond that, I would say 3 major reasons. One, metals. So most of the 3D printing technologies, what you see, are mostly today polymer based. Metal based are also coming, but still you have numbers wise, proportions wise, metals are small. 2, the size of the components which you are able to build. You kind of, have 500 mm, 300 mm is the normal sizes. Okay, whereas most of industry components look beyond it, and of course the cost of it. Okay, so 3rd, we cannot address, but at least we started looking at how we can address point 1 and 2. That is, how can we make large metal additive manufacturing components? Okay, so that's kind of where our focus is, the large area additive manufacturing. That's where we are coming from. Okay, so if you look at this, is essentially kind of the classification of additive manufacturing processes. You have, so this is the ASTM standard definition. Okay, so as per the ASTM or ISO standards, these are the various technologies of additive manufacturing families which are available. Okay, and among these, I think 3 of them are what are capable of metal additive manufacturing: sheet lamination, powder bed fusion, and direct energy deposition. Of course, material extrusion and binder jetting are also possible today, but I put them in italics because you don't get the pure metal there. It's more like metal mixed with polymers, polymer medium, metal injection molding, etc. So it is debatable whether the metal is really metal there or not. Okay, so a mechanical like me, fine. As long as it is ingredient is 99.99% metal, it's fine with me. Okay, but a metallurgist will say, look sir, metal is not really metal. Metal has to have that grain growth important. Okay, and it's just because you're gluing together metal particles doesn't make it an Inconel or any other material. Okay, so the grain growth should happen. Okay. So the italics one, the material extrusion and the binder jetting, it does not happen because you are just gluing it in a medium and just binding them together. So that's why, so for structural requirements they don't adhere, but for thermal high temperature requirements like a burner etc., they're just fine. Okay, so that's why I kept them in italic. But full grade metals or kind of, I mean, metals in both metallurgical as well as material related aspects. Three major components are there: sheet lamination, powder bed fusion, and direct energy deposition. Sheet lamination again is only limited because it is a solid state welding, so only aluminum or high ductile materials can be possible. Steels and titaniums are very difficult. I mean, people have done them, but not really convenient or not really good to do so. Okay, so that leaves us essentially only two processes for metals, handling metals, robust manner. Okay, so powder bed fusion and DAD. Okay. So if you look at it broadly, you can categorize metal additive manufacturing into two major categories: one which use powder and a laser or electron beam, and one which use wire and either a arc or any other form of metal. Okay. And if you look at it, these are kind of pros and cons for it. Okay, so each they have their own advantages and disadvantages. Okay, so some are very good surface finish, some are high build rates, etc. I will not go into the detail, but the point is essentially depending on your application. If you're looking for small components, small I mean essentially 20-30 mm components, powder based components and laser based components are better. But if you are looking for large components, large in the sense essentially 1 meter, 2 meter in size, okay, wire based or arc based components are much better. Okay, so depending on the context, you may have to pick. Of course, there are nuances always. Okay, but broadly speaking, this is what I would say is for large area, large components, large size components, wire is much economical, much faster, etc. Okay, so this is kind of the big comparison you can draw on. Okay, so so this is what we are doing is actually what we are doing can be called as incremental welding also, because you are not really taking any new novel system. Whatever is your GMAW system is what you are taking, MIG welding system, and just doing welding one after another. Okay, so for example, if you look at the component here, okay, so if you look carefully, it's just one welding bead or another welding bead or another welding bead. So instead of the welding acting as joining materials, we are doing it like depositing one bead over another. Okay, and but you can notice that usually whenever I say that, people say, look, hey, I mean, MIG welding is a very what you can say, rough process or a nasty process. It's not a clean or a elegant process. Okay, but not necessarily so. Okay, so you can look at it. These are components which are as built. Okay, and literally I am putting one bead or another bead or another bead without any deviation, without any unevenness, without any spatter also. Okay, so it is possible to control the process parameters and other these things to actually get good quality deposition happening. Okay, so different people call it with different names. US calls it wire DED. Who used to call it hybrid layer manufacturing, IIT Bombay, Cranfield used to call it VAM, etc. Okay, but the idea is you are using wire as the raw material and you are using arc as the energy source. So that brings us to the large additive, metallic additive manufacturing components. Okay, so when I mean large, I am referring to components which are like 500 mm, 1 meter. In fact, yes, Dr. John was mentioning you are even looking at much bigger components also. Okay, so for example, Relativity has one of the space companies in US, Relativity, has built components which are 2 meter, 3 meter long for space fuel tanks, etc. also. Okay, so this is what we mean by large metal additive. Okay, so what is required, okay, for large metal? Okay, so kind of I will say there are 4 major aspects which are needed to obtain large metal additive manufacturing components, you need high deposition rates. You need to have geometrical complexity possible. You need to manage the residual stresses or the thermal distortions, etc. And you need to kind of also characterize or standardize the materials which you are building out of it. Okay, so these are the 4 challenges which I think are kind of pretty important to be addressed, and this is what we are doing. Okay, so what we have done is kind of how do you address various challenges for metal additive manufacturing. As I said, first is you want high deposition rates. You want to build large components. That means you should be capable of depositing large material deposition rates. So firstly, of course, this is how our setup looks like. Our setup is built on only 2 systems: a CNC 3-axis CNC or any CNC, and a welding robot, or a welding machine, JMAW weld machine. Okay, these 2, and it costs you, for example, not even a lakh to integrate them together. That's it. Okay, the ingredients is a standard CNC machine and a standard MIG welding machine. Okay, and these we are integrated. Okay, that's it. Okay, and you can actually replicate it very easily and conveniently. So what we have done is, in the first step, not just MIG welding, but even done twin wire MIG welding also. Okay, so if you are familiar, there is something called as a twin wire MIG welding. So what is the advantage is, of course, you have 2 materials and you have higher deposition rates. So you can deposit at faster speeds. Okay, that's one part of the advantage. But we also realized it for a little different purpose. What we have done is actually use 2 different wire materials and control the proportion of these 2 in a localized fashion, and even were able to generate FGMs using it. Okay, so for example, here we have tried ER70, which is a low hardness speed, and ER110, which is a high hardness steel. Okay, and control the proportion of these 75%, 25% of soft, and gradually change it to, for example, 75% of the soft and 25% of the hard. Okay, and you can locally vary tailored materials you can obtain using this. Okay, so for example, this is a component, and you can see how we are able to control the hardness in a localized fashion. Okay, so this is essentially one part of it. Then we also done hybrid of a different nature. So we have done hybrid of both wire and powder. Okay, so this is essentially, the idea is very similar to your rough machining and finish machining. What do you do when you have to do machining of a large component? You use a 16 mm cutter, machine bulk of it, then you use a 5 mm cutter and go in small finish machining. Okay, so that is the same concept we have used for powder and wire, is deposit the bulk of the material using a heavy deposition rate, wire based. Okay, then the final features are deposited using powder. Okay, the idea sounds simple, but actually pretty difficult to implement, because you're talking different energy sources with different energy densities. The laser has a very different energy density, and the arc has a very different energy density. Okay, so the footprint or the HIZ regions, etc., are very different. Okay, but yes, so that's kind of, we are able to integrate them together, and we also have done hybrid for powder plus wire also. Okay, it's not simultaneous hybrid, it is sequential hybrid. Okay, so that's, there is also other methods which does simultaneous hybrid. I don't think it is advantageous in this context. We have done sequential hybrid here. Then comes to the geometrical complexity. Okay, so what are the various ways in which you can obtain, because one of the major challenges is overhanging features. Okay, so powder bed you can manage, but in DED overhanging features are a challenge. So what we have done is, can we tilt the base plate in such a manner that you will be able to kind of generate the tool path. So kind of, I mean, all the process planning, etc., which goes behind it. Okay, so but if you look carefully, so this is a simple impeller kind of a geometry which we have created, and how we have done is rotated the geometry in a localized fashion. Okay, and see, 5-axis machining itself is a challenge. Okay, so creating a 5-axis toolpath for machining is challenging. Creating a 5-axis toolpath for a deposition is even more challenging, because your feed rate is also a function of your deposition rate. Okay, so if I go at the same speed, I may just cut, I may not cut, I may just do it. Okay, whereas here it is a function of radius, so every location, because it is omega r. Okay, so if you are kind of familiar with the CNC systems, it is omega r, so the same omega does not help you. Okay, because the r is changing, the radius from the center is changing, and so you will end up with different feed rates at different or deposition rates. So each location you have to control the XYZ and A and C and the feed rate also. Okay, so this is kind of why it is fairly complicated, but it is possible. Okay, so I think one of my PhD student has done all the code. He has written his own MATLAB code to do this. Okay, so but it is possible for you to kind of do what we call as higher axis kinematics, where instead of depending on a overhanging feature, you tilt the base plate in such a manner that you can create complex geometries. Okay, and then of course we are also working on hybrid both additive as well as other mechanisms, because I believe see, this is essentially kind of, I keep saying, judiciously use AM. Okay, I've been working in additive manufacturing from last 15-20 years. Okay, and I'm a great fan of it. Okay, but we should not behave like a salesman saying AM is magical. Okay, when you talk about forging, you know what forging can do, you know what forging cannot do. When you talk casting, you know what casting can do, what casting cannot do. Okay, and it does not really kind of trouble you. Okay, and you know where you will use casting and then where you will do welding, or where how you will use forging and casting together, or how you will use forging and welding together, or any other methods. Okay, why is it that when it comes to additive manufacturing we don't talk about hybrid processes? Okay, why not mix them together with other processes where overall you have a benefit? Okay, so this is kind of where we started looking at. For example, can we look at hybridizing deposition and forming process? Okay, where for example we are predominantly working on non-uniform depositions here, where a base plate, so most of the times you kind of assume that the base plate in a additive manufacturing is a flat surface. Okay, now whereas can you generate a non-flat substrate using for example incremental forming or some other process, and then deposit on that using non-uniform deposition and bend it. Okay, so this is kind of the idea, is also people sometimes call it 4D printing, etc., etc. Okay, but the idea remains that how can you identify where additive manufacturing is better by combining it with a different process also. Okay, and there is no kind of inferiority in accepting that, look, this is better if you combine it rather than just going solo. Okay, and this is where kind of how we have been doing. So kind of what we do is keep saying is judicious AM. Okay, so use additive manufacturing judiciously, not blindly. Okay, and then the third aspect we are looking at is the distortions and the residual stresses, because this is, if you're kind of familiar with it, if you make a small component, you'll have distortions and residual stresses. Okay, but if you make a large component, it becomes even bigger. So for example, a 1 degree distortion in a 200 mm base plate is manageable. Okay, it is still a problem, but manageable. But if you're talking a 1 meter component and the same 1 degree, okay, will mean a lot bigger distortion. Okay, so distortions are a problem in AM, but are a much bigger problem when you scale it up. Okay, so how do you kind of, address them? So this is kind of, so we have done all the basic process parameters. Okay, so how different current, speed, geometrical ratio, how they function. Okay, and the parameters for them. Okay, so then measured the distortions among them, and created beautiful color maps. Okay, so kind of and this kind of created a summary out of it, saying, look, what are the various parameters and how they are going to affect parameters. So see, everything affects. Okay, so that's a moot point. Okay, I mean, it's useless to say that current is going to affect distortion or voltage is going to affect distortion. It affects. Okay, every one of us knows. Okay, the point is it significant or not? Okay, and that is what we have kind of tried to evaluate, is the influence of them. So you see, essentially we have rated them, what are the factors which have significant influence, what are the factors which have moderate influence, and what are the factors which have low influence. Okay, and concentrated on factors which have significant influence, and moderate influence or low influence, kind of not too worried. Okay, and then essentially kind of we also done the major thermal management part of it. Okay, so kind of done simulation of it, then generated the thermal history of it. Okay, so this is how the material thermal cycle, each particle in a kind of deposition is happening. You see, essentially it is jumping where it is depositing, then it is cooling down, where the neighbor is again depositing, again it is having a raise. Okay, again it is cooling down, again where the next neighbor is depositing, again you have a cooling raise, again so and so. Okay, so this is essentially thermal histories most of you have plotted, or you can easily plot. Okay, but the point here is, what do you make out of these thermal histories? Okay, so again I have seen people saying, look, additive manufacturing, the component is subjected to different thermal histories, and so there is a problem. Okay, even the mic in this room or the chair in this room is subjected to thermal histories. Okay, I mean, in the day it is AC and cool, or etc. Okay, so everything is subjected to history, thermal history, heating and cooling cycles. Okay, so the point is, like, just because it is subjected to thermal histories doesn't mean that there is a problem. Okay, you have to know where to look for. Okay, so kind of, so I think, I will pause here. Okay, for a key point. Okay, so because people keep saying, look, additive manufacturing, different thermal histories, different temperatures, different depositions, etc. Okay, not a worry. Okay, so always differentiate a change and a change of consequence. Okay, as I said, a chair also in this room undergoes change in the temperature. Okay, doesn't mean that it is a change of consequence. What is a change of consequence is when this, I think we need okay, so what matters is essentially what is a change of consequence. Okay, so that means what is that matters. Okay, and that we started looking. Okay, so if you looked at it, what we realized is then we started plotting what we call as our T8/5 region. Okay, you see, if you carefully look at this band here, okay, this is, for this material it is the 8/5 band. Okay, so that means close to the recrystallization and all that. Okay, and if your temperatures are within this band, okay, as you can see on the right side, then there is a softening happening. Okay, whereas if these temperatures are not within that band, there is no softening happening. Okay, so it is simple. Look at the temperature zones, okay, and check, is the temperature changes happening within the recrystallization zone or not. Okay, or depending on the material you are looking, in this case it is 8/5, etc. Okay, look at whether that change is happening in the region of consequence. If it is not, purely heating and cooling does not really matter. Okay, so that is kind of where to look for, kind of what we were looking. Okay, so this is one important example for us. Is you can see essentially wherever that region heating and cooling cycles have occurred in that location, you can see that there is a softening and the hardness are reduced. Okay, and wherever there is not, there is no softening and hardness hasn't reduced. Okay, so that's kind of a key important takeaway for us. Okay, so and based on that we also started looking at what is the reason for the residual stresses. Okay, so I mean generating some data ki A is connected to B, B is connected to C, and I mean A influences B, B influences C. Okay, I mean it's pointless. Okay, can you go at the root of it? Why is residual stresses happening, and can you address it? Okay, residual stresses are happening because they do not happen because of temperature. Mark my words, residual stresses and distortion does not occur because of temperature. They occur because of temperature difference. Okay, you uniformly heat, you uniformly cool, it does not matter. Okay, not much. Okay, I mean some of course, but not really. Okay, the difference, you heat some portion, you cool some portion, or one portion is heated little, another portion is heated lot more. That is the reason. The imbalance in the temperature is what causes distortions. Okay, and can we look at it in a generalized manner and try to reduce them? Okay, so this is kind of how we started doing it. Okay, so kind of we started looking, for example, can you do selective heating, selective cooling? Okay, so what we have done is wherever you need higher concentration, we are selectively cooling it, and wherever you need this thing, selectively heating it. You see, we have put a resistor heater and a coolant to heat a portion, cool a portion, etc. Okay, so in that fashion, kind of we have tried different mechanisms, etc. And so naturally, we were able to reduce the residual stresses or distortions mainly by reducing the mismatch in the temperature. Okay, that's one part of it. Okay, so we are doing it for different geometries, different shapes, etc. Okay, but we are not really happy with it. Okay, because the solutions we were getting was very specific to each geometry. Solution 1 for method geometry 1, solution 2 for geometry 2 is fine for a conference paper, but not good enough as a technical solution. Okay, as a researcher, it's not really satisfying to us. Okay, so how can we move away from different geometries and have a more generic approach of doing it? Okay, so kind of, I mean, so this is kind of what we looked at. So why are the distortions happening? Okay, because you need to kind of reduce the imbalance, but reduce the imbalance both at a local level and at a global level also. Okay, and then our fractal curves, which are both a mix of global and local curves, can you use them for reducing the distortions, etc. Okay, so this is kind of what we have done is, I mean, if you are not familiar with fractal curves, just Google them out. Okay, but Hilbert is one fractal curve which I have tried. Okay, so what we have seen is, for example, in this case, we have tried it out. Same amount of heat, same amount of deposition, same parameter, same everything is same, but instead of the regular methods, we have used a fractal curve for depositing. Okay, and we are able to reduce the distortion by 30%. Okay, so that means the total amount of heat which is going into the system is still the same. But what we have done is distributed this heat in a better manner, okay, and reduce the imbalance in the heat, and you are able to reduce essentially significant distortion reduction, etc. Okay, and this method is not just for geometry or geometry B, but any method, any geometry, it is applicable. The fractal, you can create your own this thing. Okay, so that's kind of how we are happy that it is a more generic solution what we are kind of looking at. Okay, so this is, I mean, okay, so the point is, you can always think of this thing, A is related to B, B is related to C, etc., etc. Okay, but if you have to look at what is the consequence, or I mean the real reason, okay, behind the distortions, behind the residual stresses, behind the softening, okay, and then analyze it from that point. And then essentially kind of our fourth aspect has been technology adaptation or standardization. Okay, so kind of have done the characterization studies where different how the properties vary across for different layers, different heights, etc. Okay, and again here also we have observed that the same that temperature cooling versus reheating, recooling versus in the zone of activity. Okay, so it does not matter for us whether you are depositing 100 layers or 200 layers. The first layer and the 199 layer are same. It's just the top layer which is undergoing your rapid solidification and has a different property. Okay, so that means the middle layers are subjected to the same phenomena of reheating, resolidification, etc., and have uniform, by and large, uniform properties across the layers. Okay, so that means if your component is 100 layers, 1 to 98, you get the same properties. Last 2 layers are water because of rapid solidification have different properties. And if you have 1 to 200 layers, still 1 to 198, it is the same properties. Okay, or similar properties, not of significant difference. Okay, and last 2 layers again are water different. Okay, so where we are able to kind of address that, look, hey, it doesn't matter whether you are depositing n number of layers, you are depositing 200 layers, and each of these layers is having a different thermal history, etc. Okay, you just look at the last 1 or 2 layers and address them. Okay, so this is kind of, I mean, how we are looking. Then of course we also done some work on design for additive manufacturing, how we can include some of the additive manufacturing constraints into the topology optimization codes itself. Okay, so for example, if you look at it, this, for example, I mean, is a standing component. Okay, if you are familiar with deposition and this thing, it's an island and a nuisance to deposit. Why? Because the material has to go there, it has to start, it has to stop. Okay, so that kind of one tiny material addition is not going to be beneficial, rather going to be counterproductive. Okay, whereas in your topology optimization algorithm, it thinks that it is some material addition is there and it is kind of accounts it. Okay, so how can we kind of mix topology optimization with additive manufacturing constraints? Okay, and we have kind of done that. So for example, you see, most of the topology optimization codes give you a lot of voids. Okay, whereas a void is a headache in additive manufacturing because it means start and stop or interruption of a process, and every time you are interrupting the process, it means there is a possibility of a defect or a void, okay, or a gap happening. Okay, so you want to kind of not purely look at it a geometrical or a topology optimization. You also have to factor in that, look, additive manufacturing, you need to minimize this kind of discontinuities. Okay, so and can that be added as a factor in the topology optimization code, etc. Okay, so that's kind of what we have done here. Okay, so some work also kind of trying to factor in the anisotropy of the process deposition. This is for polymers predominantly. Okay, so you can kind of see how different results, etc. occur. Okay, so this is our 4 aspects we have been touching. Okay, when it comes to large area, is higher deposition rate, handling the kind of tool path, handling the thermal, and handling the characterization or the benchmarking. So this kind of how we are trying to scale up what is possible in additive manufacturing for metals, for larger components. Okay, so kind of I think, and I will just close with some thoughts to ponder. Okay, so where does all this kind of lead in the Indian context? I think, I mean, kind of we have been discussing, I'm sure a lot of discussion happened in the day across what is additive manufacturing going to do. Okay, so when it comes to mass production, I think many other countries are way ahead of India. Okay, I mean, I think China is too far, okay, in mass production, and even Philippines and Vietnam are doing fairly good. Okay, so when it comes to mass production, I think there is no point in doing the catching up game, in my opinion. Okay, and whereas if you look at it, India's strength has always been in the service industry. Okay, so maybe hospitality, maybe IT, maybe kind of services, etc. Okay, so and the future of manufacturing is no longer mass production, but mass customization. Okay, so I think, I mean, I will not elaborate it here, just Google them, what is mass customization versus mass production. Okay, but the point is, future of in general manufacturing is more and more towards mass customization. That means even if you are buying a simple bag or a slipper, you want it to be unique. Okay, you don't want kind of how many of us want to kind of buy the same just to put a joke, okay. So my daughter hates Reliance Trends, okay. Nothing to do with Reliance, okay. It's just that there are 3 of them in the place where we buy, okay. And every time she wears something, she notices that her friends also wear the same thing, okay. I mean, local store, the kind of, I mean, so all of us need and feel unique, okay. You want unique products, you want unique clothing, you want unique footwear, you want unique this thing. And it is more and more where you're not just uniquely buying them, but you want to make them yourself. You want to kind of be part of making that customization yourself, okay. And in that regard, service as well as manufacturing are woven together, okay. So can India take a leadership role in mass customization? Okay, and I think, I mean, additive manufacturing definitely has a significant role when it comes to mass customization. It's the ideal tool for doing so. Okay, so kind of, I think, I mean, in that context, where, so to kind of, I think somebody was asking, what are the future prospects of additive manufacturing? Don't compare or don't compete additive manufacturing with conventional manufacturing methods. It is not right. Okay, forging and casting are still best for those respective components, okay. So don't think of creating a connecting rod using additive manufacturing. Connecting rod must be created using forging only, okay, if you want it to be economical, okay. Rather look at where additive manufacturing has an edge, okay, and try to do them, okay. And additive manufacturing definitely have an edge in low volume productions with customization, etc. happening, and that's where I think you must focus for the additive, okay. Kind of, I think with that I will thank the audience for patiently listening to me, and I think exactly 30 minutes.
Yeah, thank you.
Okay.
Thank you, Professor.
Yeah, right.
Yeah, we have some time for questions now. I have one question, little scientific.
Sure.
So as of now, it is thermodynamically metastable component that we make. I won't call it as unstable.
Okay.
Because of the thermal consequences that you have showed, and also the heterogeneous microstructure, all these things put together makes the component as thermodynamically metastable. How to make it a stable component or near stable component?
I wouldn't say it is unstable in the first place.
I'm calling it as metastable.
Yeah, but look at, for example, how casting happens. Does casted object suddenly and uniformly solidify?
But
no.
Those are bearable, for example.
But I mean, so the point is, it's a point of mapping the technology and the final utility. Okay, so you know how a casted object solidifies, and we know it is not uniform solidification. You know there is a path to that solidification. Okay. And you just are able to handle that and map that properly with your application, okay. So similarly, I think it's not really whether it is metastable or not, okay. Does the process map with your final product or final application, okay. And this application is what decides whether that process is parastability, is it a problem or not. Okay, so kind of, I mean, so whenever you are evaluating, evaluation should always include the application and application in mind.
Right.
And that is the criterion in which we are going to use it. Okay, so pick applications where, okay, so for example, there are ways to solve it. So for example, we have done induction heating, okay, where you kind of, I mean, you can control we've done that, okay. So you put an induction heater and control the way in which it was cooling down or heating down. We were able to control the thermal map in it. Even we have tried using additional laser to kind of localized heating, localized cooling. All that is done, okay. But there again, local solutions, okay. So, I mean, I would come back and say, find a solution if there is a problem, okay, but the problem, is there a problem or not, is defined by your end application,
right.
Okay. So end application is going to kind of judge whether it is a problem or not. If your end application is cool with it, for example, so if you're talking aerospace component with a high fatigue life, with a rotor component, etc., I would say it is not adequate. You have to put it through a heat treatment cycle. Okay, but if you are talking a marine impeller with a much bigger size, I would say it does not matter. The change is robust enough, and you can avoid the thermal heat treatment cycle and directly go for it. Okay, it is the application which decides.
That's what I'm coming to. Why we are not thinking about a common heat treatment cycle, a post-process?
Why should we? I mean, see.
As and when we worry about these, thermal inequalities, so on.
Correct. So I mean, it's the same concept. See, for example, if you're talking welding, for example, okay. Now,
a gas product or a weld product.
Okay, no, just take welding. Okay. Now, welding, there are situations where you subject the product to post-weld heat treatment, and there are situations where you do not bother subjecting the product to post-weld heat treatments. And whether you subject it to post-weld heat treatment or not, it's dependent on the application. Okay, so if you're talking aerospace component, again, GE, motor casings, etc., they will subject it to heat treatment. Whereas if you're talking a building with, steel structures, you don't bother. Okay, so the application, so the same question, it never occurred to us that why is welding not consistently heat treated or not? Okay, so why is it a problem suddenly that, so you don't look at welding as must need a heat treatment or must not need a heat treatment. It depends on the application. Okay, so similarly, why is it any different for additive manufacturing?
No, 95% of the weld components are automatically heat treated before putting it to final service.
That depends on the application, yes. Yeah. But if similar application is there, then probably yes. Okay. So I'm just saying, let the application decide it. Let's not our apprehensions decide it.
No,
okay.
It's not apprehension. For example, like that, in case of AM products, why we are not thinking as one of the necessary steps rather than playing with again deposition parameters and looking at how low we can cut down the residual system?
That's because, the point is, if you are talking heat treatment cycle, the part has to, not really. The part has to be made before cracking. Okay, see, the near net shape, let us assume that you have decided that you want to do heat treatment cycle. Okay, and or probably it is part of the process treatment. Even then, thermal management is a problem because you do not want cracks to appear in the process itself. During the build process itself, if there is a crack appearing, it's useless. Okay, definitely. Whether you do heat treatment also, it is still useless.
Definitely.
Okay, so it is inevitable to manage the residual stresses, whether you are still doing heat treatment or not, you still have to kind of keep them in control. Isn't it? What happens, for example, if I say, look, heat treatment cycle is inevitable. Even then, if the part cracks up during the point, obviously. So thermal management is inevitable, even if you do heat treatment cycles.
Okay.
So the kind of, so that's where, but it is very contextual. Because one thing is, additive manufacturing is not a single process. Additive manufacturing is DED, additive manufacturing is powder bed, additive manufacturing is ultrasonic, and additive manufacturing is for Inconel, for titanium, and the answer for each of these is different. Okay, so there is no one answer there. The answer for my powder bed and the answer for DED is very different. The answer for Inconel and titanium is very different. So again, so that context is always has to be kept in mind. Yes.
Okay. Yeah. Any other questions? Yes.
Hello. Sir, thank you very much for that very much nice talk. My work is also on wire arc additive manufacturing. And trying to work on that multi-material fabrication, whenever we go for the multi-material fabrication, then let's say there is some stainless steel and Inconel. If we want to combine that, there are some properties.
I think, basically what the system gives is a mechanism for two materials to combine. Okay. Yes. And whether the two materials are going to combine or not is dependent. I mean, put it very bluntly, it's like we are like a marriage bureau. Okay, dulha dulhan, if they are agreeable, we can make the process happen. Where I am getting material A and material B, and I am going to kind of melt them in the molten melt pool.
My question is somewhat different.
Okay,
my question is how can we manage the process parameter during that fabrication?
I think process parameter is always a donkey work. One by one you have to try, there is no answer for it. You have to try each of the process parameter, come across 10 failed samples, then you will realize one proper sample. So I don't have an answer for you. I don't know the answer for how to get the process parameters, except anything with process parameters, all I know is donkey work, one by one, one by one, one by one, you just do it patiently. Okay, and you kind of get 10 failed samples, then you can hope for 11th successful sample. Okay.
Thank you very much, sir. Thank you, sir.
Any other questions? Yeah, if not, let us thank Professor Surya.
Thank you.
We have few formalities.
Okay.
Thank you. For me also it's right.
Thank you.
Thank you. Yeah, one more. Yeah, the next speaker is Professor Vishnath from IIT Hyderabad. He straight away came from airport now. We should appreciate his efforts. Yeah, take your time, no issues.
Yeah, I'm ready, no problem.
Please give him a bottle of water.
It was a pleasant flight, nothing to worry about, just 1 hour late.
After flight, we are worried about that part. I request you to take around 30 to 35 minutes.
Sure.
Yeah, please.
Good afternoon, everyone. I hope everybody can see the slides. Thank you for waiting for me. Thanks to Dr. Jay Gautam and Dr. Gururaj for accommodating my special request to put it as the last talk. I hope I'm audible to everyone. Yeah.
So far from the morning you might have seen a lot of lectures on additive manufacturing, mostly on fabrication, microstructural characterization. Now I think in this presentation I want to bring a flavor of a numerical modeling, right? A process modeling. So some of these things are efforts from my group with certain collaborations. So mostly I collaborate with PRDO and Dr. Murshid Imam from IT Partner. So with these efforts, I will not show much of the result. I'll show that how you can make a digital twin, right? This is the buzzword of late, how to make a digital twin. To make such a digital twin, you need to know simulations or the process model, right? In this effort, I will try to focus on mostly on VAM to explain the concept, and DED and SLM, which is also ongoing efforts in our group. I'll try to showcase what are the complexities existing in them, right? If you have any questions, you can feel free to stop me and ask. I'll still stick to my time. Now, everybody might have shown you what is additive manufacturing, right? Or they might have called it as 3D printing, right? This 3D printing or additive manufacturing did not start yesterday or a decade earlier. It started long back in 1926. Now, I will not talk much about this because you might have seen this in several other seminars today, but a short point I want to mention is, as you all know, it is joining material layer by layer, right? And constituents can be from the feedstock, right, which can be wire, powder, etc. Then type of heat source. Your heat source can be an arc, weld arc, or it can be a laser beam, or it can be electron beam, and so on. Manipulator, which is like how do you do your slicings, XY managers, and other kind of things. In order to do that, CAD model will try to help you facilitate this. All these three things are equally important when you take care of process modeling, right? So, you might have seen this, but I just want to only emphasize on clamps, right? Here, just look at the clamps. We'll get back to this clamps. The rest of the picture, you might have seen this kind of things again and again today. So, only on this clamp, I'll get back to you, and you remind me if I forget about that clamp, right? So, in today's model, mostly I'll focus on VAM, which is wire arc, which is a direct energy deposition, arc based. DED is a powder based, and SLM is a powder bed based. These three things I'll emphasize with more focus on physics on this wire arc, and quickly I go over what are the additional complexities and challenges that come to make a digital twin. Now, when you come to direct energy deposition, you can see that you have a feedstock that gets into the molten pool depending upon your voltage current waveforms. Your arc will try to initiate the melt, then it becomes a droplet and it just short circuits. Once it just short circuits, it will retrieve back. These are all things you might have seen it. So this is quite important. This arc generates two things. One is it changes the electrical resistance for the waveform, that which I will not discuss upon it. We will focus more on what is the heat flux this is dumping onto the molten pool or to the deposition. That is our prime focus. If we can know this part, then half the thing is done in process modeling. Let me tell you why it is half of the things are done. Because how do I go back? Additive manufacturing is a thermomechanical process, right? There is no mechanical loading, but it will still deviate from your net, near net shape. It will have residual stresses, right? If it's a simple mechanical boundary value problem, you have a differential equation, you have loading conditions. But where is the mechanical loading here? To understand that, you need to know that the culprit is thermal. The culprit is thermal. So, if you understand the thermal process, how the temperature distribution is done, this temperature distribution will eventually lead into mechanical loading, and that we will showcase it in the coming slide. Now, this is pretty important slide. I like this slide out of my presentation because this purely tells about the physics, right? Now let us take, this is the black spot is your melt pool, and you are trying to deposit along this direction, right? So as you keep on moving in this direction, the material which is on the trailing side gets cooled. Once it gets cooled, it will cause thermal contraction, right? And that will cause tensile stresses. Whereas the one which is ahead of it, it is getting heated up, right? Once it gets heated up, it will try to push, right? That will cause compressive stresses, right? Now, to understand what is the genesis of residual stresses in any additive manufacturing process. Here it is a weld arc, right? For laser it may be a smaller fusion zone, for electron beam it may be different. But more or less the physics would be same, right? In order to understand how the residual stresses are being generated here, I would try to take 2 points, the same picture, a point X which is very near to the fusion zone. Can you see a blue line running here? And little bit away, a point Y, which is little bit farther down, right? Now, I can move my torch in this direction, or I can assume that I can traverse my point along this direction in the reverse. It's a relative motion. So, if I understand at different places how this point X is there, it is as good as moving heat source, right? So, I will consider the first point X. You start at 0 residual stresses because of this thermal expansion and contraction. You go up into the tensile regime, right? Sorry, you don't go into you go into the compressive regime. You go into the compressive regime because it's in this direction. You are moving into the thing, and then as it touches the yield locus, it is a plastic flow. This is a plastic flow. The material is going into plastic zone, right? Plasticity, yielding will happen. So based on its yield locus, it will, some point is this black color curve is the yield locus. It will hit onto it, and additional loading will only cause it to move along the yield locus, and as it goes farther off from this point B to C, it starts again cooling down, right? Once it does it, it will again go into, it starts with the compression, goes into the tensile regime. And in the tensile regime, it hits again in the yield locus. Now, in residual stresses, all residual stresses are not bad. The tensile residual stresses are our evil, not the compressive residual stresses. Because these processes are surface processes. Any tensile stresses will result into crack openings or surface defects, right? So, this point, once it hits into the tensile regime, it stays like this. Because it is a yielded part, even if I relax it, once it cools off, goes to the point D, this residual state AE will remain as it is. Now, this is one of the place which resulted in this kind of a AE is your total tensile residual stress. Now, if you go about for point B, starting from A, B, C, D, it will first it is ahead of the pool, so it will go into tension, remain slightly tension. It's in the compression zone. It will be in the compression, slightly go into compression. Then, depending upon how farther it is, it may not go and hit on the tensile regime on the yield part. It will only be there within the yield locus. So this can be recoverable. So this is how the genesis of residual stresses for one single point of traverse. But additive manufacturing and residual stresses is not so easy to comprehend, because you have multiple passes, you have multiple layers, you get reheating, several different things are there. So this is one single point genesis, but in reality it is a kind of convolution of all the traverses and all the heat sources that are being generated. So it is not just linear addition, because of the plasticity, it's a convolution in a non-linear domain. So the residual stresses which you see on the component or in your deposition is much more complex, but the genesis is there in this part. Now, so in order to know the real residual stresses in your components, you need a tool. You cannot simply explain for one single point, right? So we need to use some numerical tool. So what we will do is, we will use finite element method to start with. Now this is a simple finite element model like everybody does it. There are two parts of it. One part is a thermal cycle, another part is a structural cycle. I know it is pretty small, you cannot see it, don't worry, I'm here to explain it to you. If you understand this slide and this part of it, any other modeling, you can do it reasonably well. So now, when you do either welding or a deposition, we know how to convert temperature into a residual stresses, that we were successful. But we know that thermal distribution is much more complex, depends upon the traverse or layer deposition and so on and so forth, or your slicing and other things. So in order to do that, we will decouple our simulations. We will run our thermal simulations first and couple it with the structural simulations, because in structural there is no loading. There is no loading in this. The temperature, I hope you cannot see this, the end result is the temperature contours. The temperature contours is the loading for the structural programs. As such, there is no mechanical loading into it. Right. So this is first complexity which we conquer. The second one is material is being deposited. The material mass is being added. How do you model it? Right. There's a simple technique called element birth and death technique. We use element birth technique here. Death technique is for like a wear and corrosion, so other kind of things. So first, whatever is your deposition, you do total deposit as your finite element mesh. You mesh it as such, and then you deactivate everything. And when the torch is under certain point, you activate only those points. Those mass, those stiffness, right? As you go along, you have to keep activating it. So as you do your traverse, either it is inside in, outside, or a hash pattern, zigzag pattern, it all depends upon which things you are doing it will govern you. I'm sorry about that. So now, we understood how to do the material addition to this. The next part we want to take care is how this weld arc is giving heat flux into the system. There are several models into the heat source model, right? Out of all those things, There is a line source model, Rosenthal model. Welding people will know everything about this. But these are not good. This was the first time Goldak, which was not now, it is in 1970s, has come up with double ellipsoidal model, right? In the double ellipsoidal model, if you look at it, this is the front part, this is the rear part. But if you look at earlier when I showed the genesis of the stress contours, it was pretty much similar. The contour shape ahead in the front was different ellipsoid, backside was different ellipse. And he has given a thumb rules. And this model is so popular because you can deposit at different process parameters, take the weld bead, do a fructography, and depending upon your process parameter, your weld quality, the depth, fusion zone, everything would change, right? He has given these parameters A, B, C, which are dependent on the actual weld quality. Even though it's a thumb rule, it is much better, and it has been not kind of challenged except for one limitation so far. So even though it is 1970 model, you keep on using this thing. Okay, fine. So this is heat that is coming into it. And what is the challenge? The challenge is it doesn't take care of Marangoni flow inside the molten pool, right? Or weld pool dynamics. Weld pool dynamics it doesn't consider. For that, you need to use the additive manufacturing stalwart Professor Devshish Roy has come up with it. But if you start doing that kind of simulations, you have to use supercomputers to do that. Unlike this, it's pretty easy. Even a BTech student can do that. Now, this is heat source. Similarly, there is a heat sink that is going on. The base plate is trying to suck it, right? So, depending upon what is the conductivity of your base plate, you have to change your conductivity. But I'm not going to model my base plate for thermal analysis. So I'll adjust my filling coefficient. And then these are at very high temperatures at the arc. So it has radiation. You have to take care of radiation. So your heat source is Goldak double ellipsoidal model, environmental convection, and radiation kind of a heat loss. This is you are actually loading onto the material, which will convert back into a thermal mechanical loading at later part. Once you feed this and you take care of element activation, it's a simple finite element analysis. You get your temperature contours. But you need to understand that these materials are subjected to very high temperature. So the material should also be temperature dependent. Because this material softening will happen as you increase the temperature. This element mismatch due to softening is a secondary loading to the material. So that's the reason you need to feed in temperature dependent things. And you use whatever zigzag model with certain finite element mesh, and you can keep track it. For example, here we are using zigzag model. The track one goes like this, 1, 2, 3, 4, something so forth. Now, this is our example heat source model, right? Everybody will ask, did you validate your result? Yes, we did validate our result. We're putting a thermocouple at 3 different locations. Unfortunately, I cannot put a thermocouple inside my weld pool because it will burn it as I deposit it. So, but this validation is not that great of a validation. But yeah, to publish papers, I always have to do that. It's okay. Now, but I wanted to know if my thermal stresses is the culprit. I wanted to know much greater details about this thermal distribution. I'm a finite element guy. I can do data mining, right? I will do my data mining, right? I might have shown this match within 5% error, but I'm not interested in this because your real culprit is thermal distribution. So I look at it at a given point, let's say on P6, on this point P6, I am looking at the temperature distribution. So the P6 is this one. This is for all the points. At the mid track, I have taken at the center of the track P1 to P12, I plotted it. It looks nothing, it looks hazy. So I zoomed it a little bit. Then I saw certain pattern. Then I took a P6 and tried to analyze it. What is really happening in this single thing? So let us look at this part. Now I am at P6, but my weld started at P1. It is on the track 1. It is going like this. Until it comes up to 4, I am being not affected. So I am at 0. As it comes closer to the P6 from the track 3, 4 and 5, I get heated up slightly. And because I am going zigzag, I may see certain blips. And exactly when the point is on the P6, the temperature will shoot up to the maximum. Then as it goes to P7, the next track, as it goes down, certain again raising of the stress, temperature will happen. As I do P11 or P12, I have pumped in a lot of heat. The heat capacity is there. So it will not go to 0, but it will remain as it is. But it will die down slowly. So these are the 5 phases. These 5 phases will help several different things. How is the melt pool dictating? Based on your melt pool, what are the phase fractions that are forming? Several different things can be comprehended if you know exact properties. But in this study, we are not going to the microstructure. That's for a later. Maybe you guys can take it up. So this is what, if you can generate this, you know much about what is going on in the additive manufacturing. Now you feed it, you put your stresses, and if you have a cooling cycle, annealing or water heat treatment or whatever it is, you can follow up your things, continue your simulations for later part of it. Now, I'm sorry about it. Now, once I clearly determine my thermal history, which is much better than this one, I feed it into my structural component. There is no structural loading. It is differential stiffness and the temperature contours that play as a mechanical loading. I do element activation similarly, but with a delta lag, right? A small microsecond delta lag. And then I run my simulation structural and I get it, right? Did I say that to remind? Yeah. Did I say to remind me the clamp? So if you look at your temperature contours, displacement contours, this is structural analysis. If you look at your kind of a contours, this is under the clamped condition. It will give you one clamped condition. But when you remove the clamp, it will relax, right? That is your actual condition. That will dictate your actual deformations and near net shapes. So you need to continue your simulation with an unclamping. So to do that, there's a magic trick that you need to follow in finite element, and then do your unclamping, and then what you get is your correct residual stresses. So this is the complexity for a simple VAM. I have only 5 minutes, so I'll try to stick it to only 4 to 5 minutes to apprise you what is the challenges if you go to the next level, right? If you go to the DED or SLM, it is three-way triangle, right? So far I have explained to you only this arm of it, which is thermal and mechanical. Once you go into it, it is metallurgical also. So you have to do three-way analysis based on your temperature TTT diagram, which phase fractions are there, how melt pool convections are there. All those things has to be taken into the consideration. This is one complexity, that is, it's a multi-physics with a third arm added to it. There is another complexity to it. You start with a powder. Powder is a discrete medium. You put a heat source. That will again give you nice contours like what I have shown. That if you want to also capture the melt pool convection, melt pool dynamics, you need to do fluid analysis or fluid mechanic analysis, right? That is a Eulerian framework. And then once you recrystallize and try to get into your solidified form, recrystallization itself is a big challenge if you connect it with the microstructure. But even without, if I do it phenomenologically, that is again similar to the VAM. It is a Lagrangian framework. So you have multi-physics of a higher level and different frameworks to do a problem such as DED and SLM. And what are the things are there? If you try to deal with it, you have to deal with melt pool dynamics, evaporation depending upon type of things, wetting, capillarity, powder, gravity, sintering, phase transitions, all things are there. So I will not show much of the things. If you follow all these kind of things, you can get into it. I think I will take only 1 minute. I will not teach all, I will not show all these things. So in order to do these things, let me conclude. Since there are 3 frameworks are there, to follow the discrete particles, you can use open source called LIGGHTS, which is a discrete element framework, and then use finite fluid mechanics approach to capture the whirlpool dynamics, and then Lagrangian framework to do your residual stresses and near net shapes if you want to do powder bed fusion. So I think with this, an overview, greater details into WAM and what are challenges ahead for the DED SLM, I'll stop this, and I thank the chair for giving me the opportunity as well as organizers.
Thank you, Professor Vishwanath. Yeah, we have some time for questions. Tired? Our day is not done yet. Yeah, morning they announced, right, that there are some incentives for asking good questions. Maybe the coming question might have an incentive, irrespective of its quality.
I believe in one thing. There is always a silly answer, but there is no silly question. So you can always ask.
Yes. You will not get anything, only answer.
I don't know that also.
As you just alluded upon at the end, mixing the continuum-based technologies, continuum-based modeling and also discrete modeling. But in the very beginning, you were talking about calculating the residual stresses and other things through a finite element by element birth and death. But at its core, at least the physics looks more towards a discrete system, at least for the powder-based ones. So is doing finite elements sort of a simpler and more doable solution because those packages are probably more easily available, or is it?
It's quick.
Does it not make a difference even if you
No,
go
it
to
does
the
make a difference.
DM sort of approach?
It does make a difference. I didn't have time to show it. So we did certain things. This is what some of the things we do it quickly. Here first we need to know what is the whirlpool, what is the heat convection inside. We quickly do it using phenomenological framework as a continuous framework. But we know that this is not correct. You have to again redo it, and maybe this is the actual reality. We are still at a nascent stage.
Is this still a continuum approach or is this a discrete?
This is a discrete. I started with the balls
Okay.
that gets melted into it.
Okay.
Maybe in the next
so
slide you can
find
see.
equations for two solid bodies interacting.
It does change because a lot of other physics will govern, especially the weld quality is greatly dependent on the weld pool dynamics. So the discrete to molten pool does play a role, and there are also phase transition that takes place, and that will give an eigenstrains, eigenloading, that will give from the mechanical to metallurgical arm. Eigenstresses has to be introduced depending upon the temperature, phase fractions, all those things you need to know about it. Whatever you are doing with a finite element, assuming everything continuum, no, all these things is just a 101 of these things. But reality is different, and if you want to have closer predictions, and it really makes sense because this can capture the porosity, whereas your continuum totally ignores the porosity and other kind of things. So you are right that 101 is only to kind of know the physics of it, but we just started 201, so we are not yet into it. Just started it, but it is more relevant. That's the reason we have to deal with it. It captures the real physics and inhomogeneities. All other things that are present are there inside, so that will govern more. But to start with, we also started as a BTech student.
And I also have a cliched question. A lot of these modeling, probably for the benefit of students also around, the material property inputs, a little bit of modeling that I've done, one of the biggest problem I face is what sort of input material properties do you give the models, especially when trying to do a multi-physics problems. What is your take on how would you?
No, I have only in detail when I showed VAM, I only showed thermomechanical. There, when I give you a thermomechanical, I need to, it's an thermoelastoplastic. So elastoplastic properties as a temperature dependent, if I have to give, that is sufficient for
that's the question. A lot of times you don't necessarily have those. In the sense, what's your general opinion about working around things like that?
No, without that we cannot actually, material properties actually before we start even doing this, that is one phase one has to work on it, then only it's a feeder.
Yeah, I understand that, but what I'm asking is oftentimes you don't necessarily have access to those numbers, like conductivity, mechanical properties at high temperatures, those things you don't necessarily have. But we sort of say, okay, let's just do a room temperature, take the room temperature values and do the calculations or some workarounds like that. But I'll just...
Diffusivity,
but even if
doing a transformation from liquid to solid.
Yes, so you would do that, but even otherwise, even to get, let's say, elastic modulus of these materials as a function of temperatures, it's not easy to.
Yes, you may have to come from different methods, maybe atomistic or something like that, to put into it. If you just simplify your model, what you predict will also be there. Even though I praised Goldak as something so great, it captures only 90% of heat efficiency. There itself is my leak for engineering applications. With there itself, if I'm putting a very big leak, it doesn't matter if I close a smaller one, right? So it depends upon the applications. For engineering applications, people generally tend to use a Goldak and then get over it and do that. But it depends upon, for example, for small components nowadays, they want very much near net shape, because the problem here is you will not get a near net shape or a finishing and other kind of stuff. So if you want to get into the component level, you have to start with a basic these things and then build over it, because for a component level, the geometry will also add a kind of additional layer of complexity to create off from your near net shapes. So yeah, it depends upon, if you want small tolerances, small things, you have to do things properly. But if it's like engineering people, you put a factor of safety 2 and go, then it's okay. I think you can go with the phenomenological and continuum models to be a short and precise answer for you.
Thank you.
Yeah, please in the back. Can somebody pass on the mic there?
Yeah, I have a question regarding this well pool. So before and after the well pool, we were talking about this compressive and tensile stresses, but even within the well pool also there's a heat affected zone that varies completely. So can we be able to predict how these thermal stresses are varying in this heat affected zone?
Yes, that's what you need to move from your discrete framework to get into fluid mechanics framework, Eulerian framework, to predict that. If you predict that, you can even get into how different microstructures or nucleation will happen. If you want to that level, you can do that. If you want only simpler kind of things, use Goldak model, which will not put into any of those kind of stuff. Does that answer your question?
Yeah, question there.
Sir, my first question is, as we know that the final build quality is dependent upon lot of process parameter.
Yes.
Is there any numerical model you have developed or you are working on that to optimize the process parameter to get a good build quality? One question.
No. See, we just started. I just started, not even really I put 1 foot down. I didn't enter into the actual things. But one of my students is working using AIML methods. Based on the literature, put a reduced order model to get into your optimized model. I understand your question.
I'm asking about physics-based numerical models, not AI.
Physics-based numerical models, then you need to, here in your finite element, you are optimizing it for your equilibrium, right? Then if you want an additional constraint, let's say at some place my deflection is that thing, then you use another optimization tool like a Tosca or eyesight. It's a constraint optimization. Your equilibrium for the deformation will be one thing, and your another constraint has to be together minimized. That is one part, one leg will be in the physics, another leg will satisfy your constraint. I haven't done it, but
because
there's a scope for it. You can go ahead and
AI and ML only give the idea, but it will not tell any physics behind that, and that too we can't believe on the data. Whatever amount of data we have taken, it is in very small number because we don't have that much data for laser additive manufacturing till now.
That is true. I mean, it's like I would not directly go into 700 series first. I would start with a low-hanging fruit, use something, reduce models, and then go into the complexity to a next level. But yes, those combined optimization can be done. There are people who are working into multiple optimizations, non-physics based, but physics based can be done, but it will be very computationally expensive because every constraint is a multi-point constraint, and it will consume your process like anything. So yeah, in principle, yes, go ahead, you can do that one. It's a right thinking, but I have not presented that kind of stuff here.
And my second question, sir, it is related to Funny sir's question.
Yeah.
As the output, whatever we will get after numerical modeling, is most of depend upon the material properties.
Yes.
But here you told that material properties that much we are not considering. If you take example of laser powder bed fusion, there the energy absorption, then CP, all material intrinsic properties will play a large role.
No, let me put it, let me answer this question in a different way. I will start it in somewhere else. When I was in 8th class, my teacher told that Thomson watermelon model is atomic model. I love watermelons, so I loved it, right? Then my intermediate people told that you need Bohr's model, which was very boring. Then somebody came with, my first student said that we will do Born-Oppenheimer, whatever it is, nuclear interaction, we will do this one, we will not do that one as an electron cloud. Which one is correct? So is my 6th class teacher wrong? But I loved it when she taught. It depends upon what you are looking. If you are looking only up to the weights, then Thomson model is good. But if you are looking for electricity, magnetism, other kind of a properties, you need a revised model. So you ask yourself which model you want. For small deflection, this is good enough. But if I want to get into the microstructural feature, yes, you need a detailed properties. That's what I said. I hope you got my question.
Okay, thank you.
Thank you. We'll close the session here. Thank you very much, Professor Vishwanath, for an energetic talk.
Oh, great.
Thank you.
And let me just...
Yeah, there are few formalities before we close. Please go.
Thank you. Today is a lucky day.
Thank you.
Thank you very much. Thank you to Dr. Gurujal and Dr. Jay for accommodating me.
Now I hand over the session to these energetic people. Thank you.
Thank you.
Thank you, sir, for organizing it within the time. To felicitate you, I request Dr. Sudarshan Panikar. Welcome back to the final session of the day. There will be a small demo given by Mr. Yogendra Srivatsar, followed by the panel discussion.
Thank you very much to the management of SEST University of Hyderabad, and also Professor Gurraj sir and Jayaprakash sir for giving us the opportunity to be a part of your RAM event. And we as very small sponsors of this event would like to just share you a few thoughts and what we are into, so that you can explore with us your research activities and what best we can work with you is to be seen. So just starting with a small understanding of our profile. Philips Machine Tools is into metal cutting, metal forming, education, automation, additive manufacturing and supply chain management. It's a 60-year-old company based out of US, and we have completed 35 years of operations in India. And past 6 years we are into additive manufacturing. We started with conventional manufacturing, and now we are providing all-round solutions in manufacturing. So these are some of the technologies that we represent in India. We do milling, turning, grinding, additive manufacturing, metal forming, injection molding, YADMs, EDMs and automation. And our global presence, from US we handle the Western market, and from India we handle the Indian market. Just a second. So from India we handle the eastern market, wherein Bangladesh, China, India, Sri Lanka and Middle East is handled. And this is our presence all over India. We have 11 tech centers in India, displaying all our additive and subtractive technologies, open for everybody to come explore and utilize. And why we are different from others is our Philips 360 value proposition, wherein we support our vision of enhanced remote services, maximizing your uptime, and dedicated experts providing you leaps in productivity. Some of our esteemed customers are Bharat Forge, ISRO, HAL, Agnikul Cosmos, Cummins, and many more. These are our few associations: Markforged, Meltio, and EOS. Today I would just tell you about the latest technology, that is the LMD technology, called as laser metal deposition technology, a wire based DED technology. This comes from a company called Meltio, and the key features of this technology is that we have 3 variants in this technology. The first variant is a standalone machine, which is based on the LMD technology, and it is called the M450. Build volume, as you can see, 150 by 200 by 400. Now this helps you with the possibility of exploring any material which is available in a wire form in the market. So any welding wire can directly be used for doing additive manufacturing. So any welding wire, that means you start from SS, you go up to copper, bearing bronze, hastellite, tool steels, stellite and any other third party material we allow. So this drastically, what other speakers have spoken over the day, that the cost of additive manufacturing, how it has to be taken care of, how you have to look at it. You also have to look at it in terms of materials costing. So material costing goes down when you allow third party materials that we allow in our technology now, and the materials that you can buy in the open market can directly be used in the machine. Here we add to you something very new, which is a hot wire feed technology and the dual wire feed technology. Now the hot wire feed is always the substrate in laser powder bed fusion technology is heated for better results. Here you can heat the wire for a faster processing and better output, better smoother output basically, or better wall finish is what you can achieve here. And the second is the hot wire feed, dual wire feed, which allows you to use 2 materials. There was a question which arose that how would you be able to use 2 materials in a single build. So this technology allows you to interchange between 2 different wires, maybe, but the technical concept goes the same, that it should be mating wires. It is like Surya sir said that wires which can weld together only can be done together. It is not that you take two wires which cannot be done and you want to do it. It doesn't work that way. So keeping in mind the material characteristics, you can use a dual wire technology to simultaneously feed two wires, like Inconel and tool steel can work together. So that kind of technology, and it is safe, reliable. It uses a 1.2 kilowatt deposition head, and it is integration ready. Like I told you, there are three versions of this technology. One is the standalone. The second is the CNC based technology, wherein you can put this additive head onto a CNC machine and make it a hybrid machining center, where you can additively manufacture parts and then finish it according to the requirement. So something like this, where you have additively printed the part and then finished to achieve the exact quality what you require. So this helps you to give parts which are market ready. So this technology, unlike the other existing technologies, helps you to be market ready and also give you the best options. And also it can be integrated using a robot. So for large format 3D printing, like sir was speaking earlier in the day, you can utilize this technology for doing that kind of operations. So it can be integrated to a robot too. And this is the Meltio deposition head, which has coaxially 6 lasers, totally 1.2 kilowatt lasers, which melt the hot wire or the normal wire to basically print your 3D printed parts.
Our main objective was to develop a technology that's easy.
So this is the Meltio M450, the desktop
in almost
machine.
any work environment. Unlike other machines in the market, our machines are designed for industry, but do not require an industrial infrastructure. Meltio has a unique business model. Not only do we have the lowest cost machine in the market, but we also use the lowest cost materials. Furthermore, our machines are open. This means you can use metal wires directly from Meltio and obtain the benefits of our process development and material characterization, or you can acquire materials from any commercially available source. We've developed an easily scalable production model, which uses multiple printers. We are aware that many of our customers like to start with a prototype before transitioning to full production. That's why we cater to both scenarios. We've developed process parameters to achieve complex geometries, even in a free-access system. We've created a very interesting solution for the market with a low-cost, high-performance process that is flexible for almost any user.
So this is one of the most cost-effective solutions for additive manufacturing today into the market, where people are allowed to use their own materials and explore the possibilities of research. And last but not the least, we are coming to Philips Additive Hybrid, which is a hybrid solution.
Introducing Philips Additive Hybrid, powered by us, a moderately priced line of additive hybrid machines, bringing new capabilities to a wide range of industries and applications. Philips Corporation, a global manufacturing solutions leader, has taken the innovative laser metal deposition technology of Meltio and integrated it with the world-renowned CNC manufacturing technology of Haas, delivering the best value additive hybrid machines to the market. Combining the high precision of multiple lasers in a compact printhead with metal wire produces high-density parts with good resolution, fast deposition rates, and a clean working environment. The result is 3 machines in one, in a small footprint with full access travels and all the machining capabilities of Haas CNC. 3D print a large range of materials such as steel alloys, Inconel, titanium, aluminum, and copper. Or combine additive and subtractive processes with a one-time part setup, print to near net shape, and machine to final finish. Ideally suited for repair or part modification. If a surface erodes or important features wear, simply add material to build to original geometry. For new product development, go rapidly from design to prototype. Open new revenue streams by producing intricate parts cost effectively and by being able to combine different materials in a single part. Philips Additive Hybrid machines are available on Haas tool room mills, vertical mills, and universal machining centers, such as the 5-axis UMC 1000 model shown here. Laser power packages are available from 1200 to 3000 watt. This large variety of available machine models and laser power packages allows us to match the best hybrid machine solution for your parts and material requirements. At Philips, we're invested in your success. Our application engineering and service teams will work with you from initial parts review to machine and option selection, through installation, training, and ongoing after-sales support. Add, subtract, repeat. Maximize your manufacturing potential with the Philips Additive Hybrid.
So, thank you everyone. So, thanks a lot from Philips Additive, and thank you for attending this session. Thank you very much.
I would request Dr. Gulraj to please hand over the token. Thanks.
Thank you, sir.
We will now begin our final panel discussion session, for which I request Professor Shrikant and Professor Koteshwara to be the chair of the session.
Yeah, good evening everyone. Before we begin, I would like to call Professor Surya, Dr. Vishwanath, Mr. Yogendra, and Dr. Sudarshan Fani to join us as panelists. Yeah, please take. This also for Koti. Yeah. The discussion is basically is a generic discussion, will be a generic discussion to identify gaps in AM with an Indian perspective. Initially the panelists will start the discussion, and if you have to make some points, you will be asked to make those points. Let's start the discussion. The last presentation by Mr. Yogendra is a good point for discussion. The Philips has shown a system which, a new system for AM. With respect to the machines for additive manufacturing, I don't see much happening in India. So we basically import and then start using those machines. So what should we do?
My suggestion would be, see sir, it's not about only we just saying that this is not happening or that is not happening. It's all about how scientists or researchers can collaborate with the industry. There are people coming up who want to collaborate and develop new technologies. Hybrid is nothing which we cannot do in India. Okay, we as Philips, we already have the expertise of developing our own CNC machines. We have the expertise of selling manufacturing machines. But having an additive expertise is rare. But yes, if we collaborate with institutions of importance and various other institutions like IIT, ARCI and all, definitely there is a scope of developing that, but that initiative has to come out. That is what is lacking, I believe.
Maybe Professor Surya, would you like to?
I think anyway the government is arm-twisting us in the Make in India Atmanirbhar contest. You can't buy. So today if I have to purchase an equipment which is imported, it is taking me 9 months, literally 9 months, okay, to purchase a machine. So I mean the details apart, the emphasis is surely there in making in India. And I think let's look at it instead of a bureaucratic hassle as an opportunity, and where we can produce. And I think, yes, he was rightly saying, it's more a matter of initiative. And I see good initiatives actually happening in India. For example, we are developing a large area additive manufacturing for DRDO internally. Similarly, Wipro and IAC has developed a electron beam powder bed system, and I think Intech DMLS has done a powder bed laser system. Okay, so there are initiatives and there are growing emphasis, but I think more and more are expected to happen, and let's hope that these kind of forums form the crystal, kind of take the seed where industry and academia discuss and take it forward.
Vishwanath, would you like to say?
I'm not much of a fabrication guy, but to my knowledge, few efforts has been done in India. For example, what Professor Surya and his group are doing, that is really a very large initiative, and with the help of defense they are doing it, which is very one nice thing. And to my knowledge, RRCAD, Professor Paul is also developing an AM machines. So, but what I feel like is they are done in silos. And second part is, I don't think the students who are sitting on the other side, they like to develop a machine, right? They want to just to deposit it. But I would suggest that you should also think about trying to fabricate the machine, because you can also become an entrepreneur later, right? And what we need is more of the devices. Then only the R&D will begin. Otherwise, that's a bottleneck. That's what is my opinion on this.
Adding to what Dr. Vishwanath just now said, I remember one incident in Germany when I was in Germany. 10+2 students came to our lab, and they approached my professor, and they wanted to see AFM, scanning probe microscope. So my professor asked me to show, then I showed. They were not satisfied. They went back to the professor and they expressed their displeasure that they are not satisfied. The professor came to the lab and he said they are not happy. So in front of me, he asked the students, what exactly you want? Then the student said, can you just open all the parts and show us? Neither me nor my professor can do that, actually. And then out of curiosity, we asked, why you want to see all the parts inside? Then they said, their project is to construct a scanning tunneling microscope. So that's the project at the 10+2 level. So they have to make a scanning tunneling microscope and demonstrate in 6 months. So they wanted to see inside all the parts. I think that sort of thing, I think we should start in the academic institutions at least, to encourage students to take up such projects at BTech and MTech level at least. Yeah, anything from the audience? Anybody want to add on the discussion? Yeah, Koti.
Yeah. We all know that crisis should be seen as opportunity. In recent COVID times, that was an unwarranted situation for us. We were all struggling for survival. In the initial days, the country could not provide good masks even to the doctors who were helping the affected. From that condition we developed masks and also the vaccine eventually, and gave to the rest of the world and set a great example towards humanity. So we all did that because we were struggling for survival. We were forced to the corner. So now in science and technology, not only in the AM, in all aspects, maybe we should have our self-imposed restrictions saying that we are not going to get anything from anywhere, we have to do it by ourselves. Maybe by developing such kind of mindset like Japanese, maybe we can indigenize each and everything and eventually we can stand tall and proud. This is my submission to you.
Yeah, just would like to add on one point that we all look after machines which come from abroad and we think that it is developed by somebody outside India, but eventually the IITians are the ones who are there abroad and developing these machines and you are bringing them to India. So it's like people used to call it as a brain drain which is happening to the US from India. If we Indians sit in India and do the job, it would be something different. But yes, earlier the areas were not that easy. Ease of doing business was not that great. But now things have brought it been brought to a level where you can, and people should. Like sir just quoted Vishwanath sir about RRCAT. There were 3 organizations, startups who collaborated with RRCAT, and they are developing their own powder DED technology now. So they've started doing the job now. So it's just time and initiative, like I've earlier said also, and also the interest, what sir was saying, that nobody would like to develop a machine. So the interest of developing a machine, like the interest of developing a Vande Bharat high-speed train came to Sudhanshu Mani, the similar thought process should come into the young engineers. That would help us in doing more lot good to our country.
Continuing with that, Professor Surya in his talk made an interesting point of combining processes, the conventional processes like forging with AM. That is an excellent point. Can we provide intelligence to the conventional systems and to enhance the operational productivity, or to bring out a hybrid process which is called as a hybrid AM process? Professor Surya, if you can elaborate.
Thank you. I think just for correction, I was referring to farming and additive, not forging and additive. Okay, but yes, I think the broader idea is you are looking at each process having an advantage and a disadvantage, and we being open enough to identify the right combination of them. Okay, and when you're actually mixing them, there are possibilities of how kind of attributes and how you can do an intelligent system around it also. So usually, for example, in our class we give the example of that Boothroyd DFMA design for manufacturing and assembly, etc. And that does give a good reference frame to start. Okay, and it is possible. In fact, myself and my colleague Professor Venkat Reddy, we are working on such a mechanism where we can identify features. For example, when you give a geometry, identify different set of features right from the step file, and then kind of segregate that, look, these kind of attributes are easy to be manufactured through forming, these kind of attributes in geometry are easy to be manufactured through forging, for additive manufacturing, etc. It is possible, and I believe, and as I said, it's not novel. The framework is already, that kind of template is the standard DFMA module. It's just a matter of adding additive manufacturing into that framework. So I believe it is possible, and one should actually do it, not just possible, but good to take it.
In terms of starting a new machine for AM versus slightly converting or modifying the existing conventional machines for AM, or to be called as AM.
I think so. That is true. If you actually look at additive manufacturing machines, typically, if you remove the laser scanner with gyroscopes, okay, most of the machines use head movement. Okay, and if you do the break point, I mean kind of the costing analysis, the detailed costing analysis, 50% of the system cost will be on the kinematic setup to move the laser or move the head rather than really the head itself. Okay, so you can talk most of the systems, I think, I mean at least a significant number of them, more than 50% of your cost will not have anything to do with additive manufacturing. It will be just that controller, that x-axis, y-axis, z-axis movements. Okay, and that's where I think the kind of what has done, or what BFW or DMG Morrissey has done, is where they can hybridize it and where they can use existing machine or a new machine. But what you are doing is actually leveraging the controller and leveraging the axis part of it. And that's more than 50% of your cost. Whether you use an old machine for it or a new machine for it, you can, so for example, if you have, if you want to build a laser, a deposition head, instead of starting with a new one, if you just buy a 2030, in fact, that is how we started our process. When we started our process, no CNC manufacturer was willing to give us guarantee that if you integrate a welding machine with a CNC, we will retain the warranty. So literally myself and my guide went into all the kabaddi shops in Bombay, okay, literally roamed around, purchased a 30-year-old CNC machine at 1/4 of the cost, okay, and then integrated it and proved it, and then finally I think Hermle gave us warranty for the next setup. So it is definitely possible, and I would say a nice way of doing it, coining what you said, is remanufacturing, what they call, okay, or circular manufacturing, where a end of product machine is given a new lease of life and repurposed for a new application. And I think that is one good direction which one can definitely look at.
Anybody in the audience want to? Guru? Now, extending that discussion, now we have lasers and electron beam as sources in most of these systems. We still have to, unfortunately, import lasers and e-beam sources. So, is there anyone or people working on this, making lasers themselves and e-beam sources?
I believe not, to my knowledge much. It's a tough, but I would break it this way, okay. It's always a pyramid, okay. When we talk about Make in India, we don't have to always start thinking with Intel processors, okay. I mean, start with the easiest thing. If you go to this China Bazaars, are now thankfully they have been renamed as India Bazaars, okay. You go to them and you see 90% of the toys are also imported, and I mean, I don't see why. I mean, of course, we don't have technology probably for Intel processors yet, but we do have technology for these toys, or for these projectors, or these lights, or LED bulbs, etc. Okay, so maybe we can start with low-hanging fruits, at least to get the tempo going. Okay, I mean, doesn't mean that we stop it there. We also aim for the last. Okay, but I would say, if you're starting, don't worry too much. First, go grab the low-hanging fruits. And there is nothing shameful about grabbing low-hanging fruits. Okay, it's good strategy to do, and that's how you slowly learn. Okay, you slowly do the catching up game. You slowly kind of do the compensation game. Why not? Okay.
Yeah. Dr. Guru Raj has
related to laser development. CGCRI Calcutta, they have one 50-watt laser developed indigenously. But some controllers and all, they got it imported, but otherwise they claim that they have their own laser now. And they are developing now next stage, 200 watt something. And that 50-watt laser was demonstrated on old CNC existing in ARCI for laser scribing, means how laser will interact with the material we try. So next stage is they are coming up with a 200 watt laser, which we may try for some micro welding and all. It's a development, so it's going on. So the main scientist concerned during COVID, I think they lost him. So now the The supporting scientists are taking care of that. So that's how that got delayed. And about EBM, BARC is supporting electron guns. I attended one talk recently in Bangalore. A lady who is in charge of this from BARC presented a talk, and she is telling we can give you electron gun for EBM machines or electron welding machines. And one such a machine working in IIT Kharagpur for electron beam welding. Its source is from BARC. Yeah, just.
Okay, thank you for the information. You would like to add upon from the industry side, if you know something about?
See, lasers predominantly have been from Germany, and like what sir rightly said, low-hanging fruits have to be seen first. That is what Intech DMLS or AMS has done. They got the low-hanging fruits and they moved ahead. Lasers, yes, they are a bit of complicated things, but like CGCRI and different research institutes can concentrate on these kind of activities and involve some startups who would be interested over that. So that would actually add upon development of these.
Audience? You can also ask questions. I mean, it's not that you have to only. Okay. Throughout the talks, we figured out that there are bottlenecks with respect to the availability and indigenous production of the feedstock. Is there a way to quickly address this? I mean, yeah, if you consider all of these at it's one or two places people are working, but what is the intensity at which we have to take care of this aspect, because in order to bring cost effectiveness, it is very important about the feedstock. You'd like to?
Yeah. So first, let me put down what was my struggle. So I wanted to purchase a powder, which is very expensive. So, which is name powder. I started purchasing it 2 years back. And then several bottlenecks coming from the government. We need to do a global tendering, whatnot, everything has come in. And then we did everything. And suddenly COVID came, certain delays, second COVID over. Then the war came, they doubled the price. For whatever reason, if we ask some question, they will increase by few lakhs. So to purchase 11 kgs of a powder, it took me 2 years of time, right? Why? Because no one in India can make it. Right? Now, this question is in fact connected to the first question, right? There are also devices to make feedstock, right? Not only just a final device, but you also need other kind of devices where you can invest to make this technology cheaper, to bring it to the real world applications, right? So in that attempt, I think ARCI, Midani has put certain efforts. And I think Professor Murthy, our director, also mentioned that they were almost close to completing their inert gas atomization kind of stuff. So, I mean, there are a lot of avenues. Don't just think that it's a kind of an AM machine or a forming machine. There are multiple things, and there are a lot of scope. So, feedstock, unless you make this one cheaper, your AM will not become cheaper. So, if you want to depend on imported things, not only the cost, certain materials have a lot of embargo. They will not sell you just because you want it. You have to sign a lot of end user agreements and other kind of things. They will make n number of background checks before you can get it. And God knows what they're supplying is also right or wrong. So I think that is one thing. And one more thing I want to connect it with the device and the powder is, somehow the industry always tries to make a bigger device. And with an expensive powders and other things, people like Professor Gurraj, maybe Professor Surya, they understand that you need a system with a smaller, bank of powder rather than bigger ones, right? Where you can facilitate R&D, because to bring this technology, you need R&D and you need to consume powder. And certain powders, if you open it and it's gone wasted.
right? So I think companies and also people who make indigenous like Processuria or RRCAT, they should also focus on making R&D level so that you can better use of your resources rather than burn all your resources in making one small object to come true. So that's
that boils down to saying that we should also work on do research on feedstock materials and also use. Yeah, there is somebody who wants to say something.
Hello. Is it that we cannot make the powders, or we do not have the technology to make the powders? As in for legal issues and the patenting.
It is not that you cannot make. There is nothing which you cannot do. You can make powders. People have done it. Companies like Matrix Nano, companies like Indo-MIM, they are making the powders. It's not that you cannot, but it's the kind of interest the researcher takes into it. People concentrate on building one part in different angles with different structures, with different specifications, parameters and all. But there is also one angle to it that you can also work around on developing the powder for that. That's also a research work. But I hardly see, like I roam all over the country, but I hardly see people working towards development of powder. There is a setup called National Center for Additive Manufacturing. Now, they are promoting companies to come and do development of material, feedstock. The biggest roadblock in additive manufacturing being adopted by the industry is feedstock. The cost of the machine, everybody buys a machine, and someday or later that cost of the machine goes down. Or you have a smaller machine, you can. But the basic and the minimum hurt what the manufacturer feels is the price of the feedstock, which has changed in case of polymers. If you see, I can name around 10 people in India who are developing feedstock for polymers. So why can't you do it for metals? We have largest metal industries in the world in India. Why can't anybody collaborate with them, or why can't they themselves do that? Because they need to know the potential of it, that's it.
I'm asking as in the legal side of the equation. Can we not make the same powders here without any patenting issues, etc.?
I think usually these are covered under trade secrets, not patents. Okay. So most of it. So that means you have they have the technology, but they will not share the process parameters to make the technology. Okay. But it is still see, there are two factors to it. One is the know-how, and the other is the commercials of it. Okay. So for example, you see there are people in India, for example, we did try when we started working on DED 2 years back. We used to import and we used to use, for example, Orlicon powder. Okay, and later with Simulac, etc. Now we are using a powder from Indo-MIM, which is manufactured in Bangalore, and the cost of the powder is 150 to 110 depending on the material. Okay, so kind of drastically our powder cost has come down. And we did do all the characterization studies before adopting it, and the quality of the imported powder and the quality of the Indian manufactured powder was on par. There was no, it was not inferior in any manner. Okay, so yes, it is possible to make. Okay, so why are people not doing it? Okay, is one, the technology of it, probably for example, Inconel, they have been able to do it, but maybe if you talk C103, maybe titanium, maybe the process parameter understanding maybe need to be built. Okay, that's one part of it, and that is the challenge. The other part of it is also the economics of it. the cost of setting up such a facility and then selling it, okay, if you don't have enough market in India, then usually your cost of the powder will be more than what you are importing. Okay, so typically sometimes industries, for example, same again, Indo-MM is doing Inconel because there is market for it and they have the numbers and it's working out economical. But they're not, probably they are capable of other materials but not interested in other materials because the demand for it is small. Okay, so these both are factors. Okay, so there is technical which I believe can work, okay, and economical also, because I think slowly as the market grows, as the requirement grows, probably more and more I mean industries will be interested in making powder also.
No, this brings to the question of whether there is a problem in classroom learning and teaching, training, capacity building, research motivation in manufacturing science. Maybe Dr. Fani, if you would like to.
In fact, that's a deep-rooted problem that I see, and I'm at least till recently I'm not from the academia, so I come from a industry background or somebody who have worked for private companies, and especially in the field of mechanical engineering, things just it's not just classroom teaching. Things have to go both ways, and it is also the mindset, as it was also discussed at the very beginning by Professor Srikanth. So the mindset that you would want to do something on your own, be hands-on, that mindset is also quite important, especially in the field of mechanical engineering. And coming back to the question, this morning Professor Ghansham Krishna mentioned that when the manufacturing master's program was started in the University of Hyderabad, this is one of the very first ones in the manufacturing sciences and technology. So having made that start, I think it is also, and being part of ARCI, which has been closely associating with the university, one thing that I have seen in the last couple of years, especially for something like AM, which I would see as, even though I'm an outsider, I see this as a multidisciplinary, it's not just a stream in itself, it involves, and as Professor Surya also mentioned in his talk, in many ways you would have to have expertise of various other fields, and also make good connection with the basics. It's not as though it is something, it's not rocket science. It's a lot of it, it's still, the basics are still rooted in the manufacturing sciences. So in that regard, I would think very close interaction between the academic and the industrial partner, or whomsoever partners with the university, is very important. And also taking up projects, and as Professor Surya was also mentioning, setting up small goals, low-hanging fruit, identifying something that is possibly can be accomplished in 6 months to 1 year. It may not have any commercial importance, it may not give you a publication, but something that puts the students through the grind of doing it. And it will serve well, at least if they go ahead and get a PhD degree, it will serve them. And of course, the end goal of all this is being employed. It's not about getting the degree, it's about being employed and whatever skill you develop. And I'm sure Government of India has a lot of programs for skill development. But I think partnering very closely, and these models are there in abroad as well, like the Jet Propulsion Lab and the Caltech. And so the industry and university have worked very closely to deliver mechanical components that actually fly, not just publish. So I would say the university has to closely associate with the academia and industry. Interaction should be there. And given that Hyderabad is that a place, there's University of Hyderabad, IIT Hyderabad, and there's a lot of DRDO labs that do it all the time. So I think I'm aware that these things are in the process. We are in the process of working together, but a little more interaction and fundamentally change in the mindset of the student, that you would want to see something happen rather than go through the course, is probably it may not come up from the master's level itself. It probably has to come all the way from the beginning, but there's got to be a beginning somewhere. So that's my perspective.
Anybody wants to?
So one thing I wanted to tell is,
one of my faculty friend, when he joined, he asked director for 5 lakhs. So director doesn't want to give, but he asked him another question. I'll give you 5 lakhs. Can you make it 50 out of it? Then he said, no, thank you, and he came back. So why I said this is, we are all in the same boat, but I don't think now faculty are like that. I think everyone are hiring for crores of funding. Now they understood, right? That should come into your brain. You also think that I'll publish a paper, become a faculty, done. Now to answer your question on the powder, let's say if I want to make it tungsten or some other material, your technical know-how, right, like, is different, where you need to develop. After you develop, what you will do? You will publish 2 papers, get out of it. You don't want to translate. You don't want to make it, invest 5 lakhs and get 5 crores out of it. You are happy with it and just want to give the trade secret to someone and get away with it. So just think that out of PhD, you should not become a faculty, you should become technological entrepreneur. Then most of the answers will be in India only. That's what is my take.
Okay, let's move to another discussion point. Is about if you see everywhere additive manufacturing, wherever additive manufacturing programs are there, I mean such programs, most of them are structural components or structural products. But what is the status of AM of functional components like sensors, or for example magnetic sensors, or thermal sensors? They themselves are useful in data collection, in AM. For example, if you want to measure the surface temperature during the process, you need some sensor. I don't know how far we are in manufacturing our own sensors, data collection systems, data storage systems. Like to comment on anyone? Yeah.
I happen to be Dean Innovation and Startups, so the kind of cheap advantage is give me any topic and I can blabber on it. Okay, so I mean, because I keep hearing at least 100 to 200 presentations in a month, and I mean, so kind of I am fairly well, I know all the buzzwords and keywords, okay, not that I understand them, but at least I kind of am familiar with all the good. Okay, so I think coming to the question, okay, so there are technologies available for sensor level also, particularly for example aerosol technologies based processes people are doing. So people have tried, for example, Optomic has tried solar cell printing with this thing, and there are people who have successfully done gas sensors. There are successful people who have done, in fact even on our own institute also, people are doing gyroscope, micro gyroscope printing, etc. So it is possible, and I mean there is a fair amount of work happening there, but why it is not catching up to the extent is devices by and large are always mass manufactured. You don't need 2 devices, you always need 2 lakh devices. And when it comes to additive manufacturing, it is not a technology for small numbers, big numbers. So so technically it is possible, work is happening, but why you don't see a matching interest is particularly because of the numbers. You have devices, all these gyroscopes, 50 rupees, 20 rupees is what is the manufacturing cost. I think I'm pretty sure it's much cheaper in the bulk. Okay, and whereas if you manufacture them through additive manufacturing, each of them is going to cost you 10,000, 20,000 rupees, just the sensor of it. Okay, so that is probably one of the reasons. And of course, additive manufacturing is still approximation near net shape. So once you make it bigger, like I'm smartly doing, so the undulations become smaller. When you make it smaller,
yeah.
Maybe
I would like to add here about not exactly AM, like for example thin film based technologies, which probably also are layer by layer, deposition techniques. We happen to have many thin film labs across India, but I am not sure how far I know whether any lab has produced a complete device. For example, let's say a gyroscope or
they have, but again at a very low TRL level. So usually that Liga process etc. is what layer by layer Liga process involves the same. Okay, but not to a level where end user can use it. I think, for example, StarC is actually doing it. StarC is the hub of such device manufacturing and is mandated to do all that, and they have the best facilities in India. But I still think if you talk in the global level, what is the facilities we have are more of characterization rather than actual fabrication.
Solar panels are done like that in ARCI, we have online.
Yeah, solar cells, yeah.
And the technology what is working is a material jet technology. So they deposit the nano thickness layers on different materials. So yeah. And there is a 3D printer, but they don't call it as a 3D printer, they make it as a film maker. So it's a micron tip nozzle which will dispense the material.
What about conventional thin film, processes, like, you have a production line for like magnetic field sensors, for example, which needs probably a multi-target sputtering unit and, lithographic and,
So I believe it is possible.
It's possible, but yeah, not many are actually doing it. I think we had an interesting discussion, and I see that the time is also up. We'll close it here. If there is any further addition from the audience, you can make. Yeah, there are two people who want. Prashant, you can speak loudly if you want. You can.
The question is likely to be what is a good research thesis topic.
I don't know. Yeah, go ahead, Prashant. Yeah. At University of Hyderabad or throughout India? Yeah. Okay. I just quickly want to answer, and then if somebody else wants to continue, they can. At University of Hyderabad, we have several programs. In fact, there are several advertisements for hackathons, which includes manufacturing. Okay, and only once School of Engineering Sciences and Technology participated in such a hackathon. Okay, there is a technology enabling center. There is a ecosystem for startups. There is a ecosystem for discussion of ideas. You can go to TEC, DST Technology Enabling Center if you have an idea. You can start, they'll give you space, they'll give you also resources, some funding to work on your idea. Okay, such programs are there. But you see, your MTech program is so tight. I see you're already tired at 9 a.m. in the morning when you come to the class. So you have to take out some time from your sleep. And if you are interested to put some effort in that direction, that's from my side. If somebody wants to add.
Any other wants to? Otherwise I can go ahead.
Yeah, please go ahead.
Alright, so I will talk. So as I said, I am the in charge for startups at IIT Hyderabad. So just a couple of things. Mainly, I think in our opinion, the threshold or difficulty for the student should be reduced. Okay. So what we have is, for example, when you are a student and you have a great idea, okay, we also allow you to register some of these credits as an academic credit also, like independent project or entrepreneurship project. So this, whether the idea succeeds or fails, doesn't matter. You still have it also in your credit, academic record, that yes, you have done an entrepreneurship project of 3 credits or 6 credits. That one. 2, I think, kind of, we give you, you in the sense if you are an IT student, okay, if we give you around a support of 10 lakhs to start with, and if it is software 4 lakhs, if it is hardware 10 lakhs, and subsequently up to 25 lakhs of funding support to do that. 3, we have an academic schedule, it is approved by our board of governors, etc., where even when you are a student, you can be CEO of your company and do your study together. Okay, so that is also possible, and there is no problem in doing it. So I think enough facilitation is we do. Okay, and if you want to say, sir, I want to try on my idea and come back, we even offer you deferred placement. You can even convert, for example, let us say you're in a 4th year and you want 1 more year to work with. You can work on the project or your startup idea, spend 1 more year, convert into a dual degree. After 5 years, we'll give you your BTech in mechanical or material science or whatever is the subject, and we'll give you MTech in entrepreneurship, deep tech entrepreneurship, irrespective of whether your startup succeeded or failure. Okay, so that means you're reducing the risk involved, where you spend 1 more year, and if it is successful, very good, we are happy for you, you make money, we are very happy. Okay. 2, even if it is not successful, you go out at least with a degree, MTech degree, additional degree. Okay, so that kind of motivates more and more people, reduces the risk involved. So these are some things which are possible. Okay, and I think these are available in one form or another in most institutes. And I think, you can look at similar facilities in each of these institutes.
Except for that, to add to that, except for that academic linkage, academic credits, rest all is there at University of Hyderabad. Okay? Yeah. We are discussing about such addition into some credits for some additional co-curricular activities like some innovation, entrepreneurship activities. But I don't know how quickly we can bring into that MTech framework, which can give credits and or special MTech degree or something like that. But apart from that, the ecosystem, whatever Professor Surya said, which is there at IIT Hyderabad or other IITs, is also there at University of Hyderabad. So you have to explore basically, and these are all there on the website actually. If you see our website for innovation, research and innovation, what all things the students and faculty, it is not just for, if I have an idea, there are several faculty who have their own companies here. I hope you know that. So yeah.
Just want to add one point.
Yes, please. Yes, please.
Yeah. So what Professor Surya is much formal framework. Government also has an informal framework called Tinkerers Lab, Atal Tinkerers Lab. It has been started even at the school levels nowadays, and where we give, we open these labs 24/7, mostly after hours, and we give you material, we give you whatever devices. You do whatever you want. We don't even ask anything out of it, a product, but we only ask documentation, what you have done with it. So if you germinate your idea here, then whatever framework Professor Surya was telling is there at the other places. Incubation is there, pre-incubation is there. So there are avenues. You have to start somewhere.
Yes, please.
See, I would just like to tell here is that at R&D level you have a lot of jobs coming up, a lot of organizations investing on these kind of R&Ds. You speak about R&Ds only in Hyderabad. You have DRDOs, you have Hyundai R&D who have invested heavily on additive manufacturing. Amar Raja Batteries is another such company who is investing heavily. But then what they lack is people who really want to sit and do research which can help the manufacturing. People like Professor was talking about, people want to just do their bit of research work, make 2 papers and leave. So that is not what a manufacturing setup requires from you. So they require this. Apart from that, every machine installed. Today close to 180 metal additive machines are available in India. And if not 180 machines, all these 180 machines would require minimum 1 operator. So that is a basic math that you can do. Apart from that, companies who are adopting AM, like recently Raurkela steel plant adopted AM, and they adopted AM for jigs and fixtures. They require people to work for, develop 24/7 jigs and fixtures for them. Similar is the case with Saffron Aerospace in Hyderabad. So they are doing that, and Cyient has developed a complete, altogether a different ball game where they made it a Cyient DLM Private Limited. Now they moved that entity as a separate entity, and they are concentrating on doing AM manufacturing and then supplying to their customers all over the world. So there you again have scope of operators, you have scope of application engineers. The biggest scope would be application and research. Application engineer and research. That is the maximum scope what I see. And yeah, people who concentrate onto it, it is not just that everything is for AM. AM along with the conventional manufacturing will give you better scope than anything else. Professor Surya can help more on this.
No, I won't venture into this subject because I am into the other side of the fence. Okay, so I am always conscious of my students getting placed, so I won't venture into that domain.
Thank you. Thank you. I thank all the panelists for. You have somebody has a question? You still have a question?
Yeah, okay, sir. So, like, from the morning we discussed about AM printing parts from small objects to larger objects. So, can we go down to smaller, much more smaller scales, like at micro level or nano level? Like, can we print like carbon nanotubes or not that much, even though like micro parts, like in the micron size? Like, can we print such parts, or is there any constraints for size limitation like that?
I think additive is, as the name goes, adding material. So you add, you want smaller components, you add small. Okay, so there are technologies which can add very small. So for example, aerosol technologies are one such example, where the material is added in very, very small micro sprays. Okay, very small material components are added. Okay, or in fact, if you look at it, even some of the masking technologies are also used together. Okay, so it is possible. Okay, it's just that the material, the technology to add small material. So that is where the challenge comes. So usually what happens is most of the technologies depend on full layer and then masking some area and unmasking some area. Okay, so whereas additive depends on specifically adding, that's where the challenge comes. But it is possible, and there are some technologies. One, as I said, immediately which comes into the mind is aerosol technologies. Okay, where you add particle by particle
or at least spray by spray, droplet by droplet. They are also called as drop-on-demand technologies, where you have very micro droplets being added. And they are possible even, what they are doing is they are adopting, instead of redesigning and remanufacturing, they are adopting the technologies which are available, for example, in printing. If you look at your printer, normal printer, inkjet printer, okay, it is, you are adding a very, very micro droplet onto the paper. And the same setup, the same head actually can be used, or the same technology can be used for building also. Okay, so there are possible people are working, but I think a successful commercial model in that domain is not much there. I think except for the Optomec version, I don't think there are other major commercial models available to my knowledge. But yes, so just think about inkjet printing, and you want to use inkjet printing not for one layer, but for multiple layers. That's your editor.
Yeah, please. मेरा क्वेश्चन कुछ नहीं है सर, अभी जो सर ने आंसर दिया है उसी को कंटिन्यू है. Like old era, you cannot say now only DRDO, Ordnance Factory or some academics will provide the job only. If you compare other countries like Germany, USA, UK, private industry are the leader to provide the job. So, being a Philips, you cannot say ARCI, IIT Hyderabad or University of Hyderabad, these people will give the job, and that old era has gone now. Pani sir and Gurraj sir knows if they want one technician, they have to wait for 5 years. Even in some cases, they themselves working on projects without any students. And directly sir has asked a very good question. That was, I think he is not a student, but he asked the student question. Actually, when coming to job for private companies, even after doing PhD in metal additive manufacturing with lot of interest, with lot of knowledge, he is not able to get the job. So finally what he will do, he will search some business related job. Because in India, most of the industries are service provider. And I belong to farmer family, I know that we will get a tomato and we will sell in market for 4 rupees kg. That 4 rupees kg will convert into Hyderabad into 40 rupees kg. That 36 rupees who is earning, all knows. So ARCI, University of Hyderabad and IIT Hyderabad people, and I am also related to IIT Hyderabad also as an external PhD student. So these all people like a farmer, and who is taking the butter, we all know. So it's private industry's duty. I'm not blaming you.
But I will just correct you.
Sir.
MTech is what is meant for industry. PhD is never meant for industry. PhD is meant for research.
No, even
as the name calls. So, I mean, actually your employability is better with a MTech degree than a PhD degree.
Yes.
After PhD, your employability reduces, not increases.
No issue, sir. Even in case of MTech also, I am not blaming even industries also, because they are more service oriented and they cannot invest in such huge amount in core R&D sectors. So that is a problem, sir. So finally you have to take the call, consider the profiles and try to adjust them. Then definitely in 10 years, and from student side, I will tell 2 minutes. These days students are they are having lot of enthusiasm. Most of the students, they will read each and every day what is happening in 3D printing, how people are integrating AI, ML in 3D printing, even online, offline process optimization, how the people are doing. This all are, even they are connected through LinkedIn, Twitter with lot of other foreign universities professor also. Earlier days it is not so easy. So we are also doing our part, sir. That is not the issue.
Okay. So what I understand is you are offering him to give a job to you.
No. Because I am satisfied with Gurraj sir. I don't want job, sir. No. Because
on a lighter note. As sir said, on a lighter note, companies are ready to offer you jobs. It is you who has to be industry ready. Okay, people are reading news about 3D printers, but hardly I have seen students, a BTech or MTech, who practically has worked on a 3D printer. There are machines in engineering colleges here. but they are machines for displays. I have given machines for maximum colleges in Hyderabad. You name a college, I have given a machine. But I have given a machine with 10 kgs of material on a polymer machine. Still, after 5 years also, those 10 kgs have not got over. And the moment a student wants to operate it, the professor calls us, saying that please come, he wants to operate. So it's a gap.
That
it's
may
a
be a
gap
BTech or
because
MTech
you are
student.
not allowed to use the machine. Or you have to convince your professor in such a way that he instills confidence from you that yes, you will do something good. Okay, I have sold 50,000 rupees machine. I have sold a 10 crore rupee machine also. There are companies who want people, but then we get BTechs who don't even know how many types of castings are there. There is a gap. That gap has to be filled. And for that we have something called as Philips education.
Oh, again you want to
join us through our Philips
again we have to join
education.
it.
We will help you.
Yeah, thank you. I think we have offline you can ask. Huh? Please already wait. I thank, finally I thank the panelists. I hope not. We had a wonderful discussion. Thank you for participation. Please sit down. It's not yet over. Please sit down. You may occupy your seats. Thank you so much. There is a quiz type of thing to for the students.
I hope we don't have to.
No, I picked the questions from your presentations.
Sir, it's a small moment. Getting the cups. Just thank you to all the panelists. Thank you.
I will take once we are done with this. Thank you. Thank you. Yeah. So to end today, to end this program today, we wanted to see how far the participants were attentive in attending the presentations and this. So I made some questions out of the presentations. Those who answer will get a merit certificate, participation, a different certificate you can say. So that's the idea. But it's just to enjoy. Finish the day with some. So I'll start. You may have to raise. I may have to check who has raised the hand first and then ask the question. Okay? Or ask them to answer the question. Are you ready? Mostly applicable to the students. Okay, the first question. One of the speakers, Ms. Akshita, has shown a GE fuel nozzle component and referred to it as a first example of productionized AM product. Now, the question is, what is the material with which the fuel nozzle was made? Dikshit? Cobalt chromium. I've seen, and I see, good to note that there are several hands, and then there are 15 questions. So you will get only one certificate. Okay. Dikshit from University of Hyderabad. Yeah. Okay. Continuing with that alloy, cobalt chrome alloy, Dr. Murugan from IIT Chennai in his presentation. No, after the questions. He's the smartest in our school. In his talk, iron was added to cobalt chrome alloy to tap some advantages. Okay. Now the question is, what was the crystal structure they obtained, and to what it has been attributed to. Why? What?
So the option is BCC.
Okay.
So they wanted FCC structure. So finally.
No, the question is, why did they get BCC? Yes, please. The one. No. Why did they get BCC? మీరు ఎత్తారా చెయ్య?
Sir, due to rapid cooling.
Actually, he raised. Both can share. Yeah, they attributed the observation of BCC to rapid cooling, and then they heat treated again to get the FCC phase. Okay, good. Just take it lightly, it's, we're not going to fight there. Okay. The next question. What is the name of the Wipro 3D AM component that is orbiting in the space?
GSAT.
GSAT? What is it? It starts with GSAT. Where? Who is that? GSAT 19. No, there is a full name. That's a GSAT 19 is not a component. There is a name to the component. Anybody? Huh? Yeah. Huh? It's a feed cluster. Okay? It's called GSAT 19 Northwest Feed Cluster, the name of that component. Okay. The next question. This I think many of you can answer. So I have to be careful when why is the certification of products or materials or processes needed?
Standardization, to maintain the standardization.
That's all?
To ensure quality.
Better quality control. Rules and regulations are not yet defined.
Product standardization.
Few defects for million opportunities. So Sigma model is
But even if I combine all of these, you don't, yeah. Believingness.
To believe on the products.
Any other?
Choosing product safety and quality.
First is a quality, robustness, repeatedness, and safety. Very if you want to put a component in some service, first is the safety. Anyhow, I think all of you have answered. Let's all will get that. So okay. Now we are looking for somebody who answers something like that. There are plenty questions. Okay. We had a discussion on when Dr. Gururaj gave his talk. What in powder bed fusion? What are the parameters that define the smallest pool size?
Spot diameter.
What are the parameters? So the question, please listen to the question. What are the parameters that define the smallest melt pool size?
Particle size, like powder particle size.
Louder.
Melting.
There are several parameters. Pot size, somebody said.
Pot size, laser parameter, scanning speed, edge distance.
So that's what he was telling actually. It's actually I asked a question whether can we say only spot size defining the melt pool size. Then we have to add some power density is very important. Unless the laser or the electron beam interacts with the material, there's nothing happening there. Okay, so it's the power per centimeter square of the interaction area, which also the speed and other things also come into the picture, not just the laser spot. Here I see
Speed, layer thickness, scan speed.
scan speed. Of course, later on they added all these. So again, nobody gave the single answer. Close is Chauhan, but we'll see. We'll try next question. Please note down Chauhan's name. Okay, next question. This is about the feedstock for laser bed fusion. What are the requirements the particles have to satisfy to be considered or optimal properties, qualified to be used as a feedstock? Three of you have raised at once, sir. Who wants to answer? Okay.
Particle size, shapes, spheroidal shape. These are especially
Okay.
Sir, below 50 to 60.
We'll come to that. Yes. Density, porosity, shape, size. That is shape. What about distribution? Particle size distribution. Huh? So again, you want to ask a question or? Okay. Again, nobody answered completely. Coming to your this one, he was telling. We can give to them. Huh? Yeah, please note down. Name. Gururaj is recommending.
Sweta, John, and
Only one. Yeah.
Sir, my name is not recommended.
I don't know your equation with the doctor. Anyhow, so the next question again is the particle. Dr. Gururaj mentioned somewhere in his slide D. He was answering that D50 equals to. This is about the percentile thing. Huh? D50 equals to capital D50 equals to, let's say 33.9 micrometers. What is it? What is its meaning? Yes, the middle one in the middle.
10% of particles are less than 39.
Should be less than that. Yeah, that's the correct answer. So D10 equals to something implies 10% should be less than that particular number. Okay, please note down his. Okay. Okay, this is quite easy. The next question. As per the ISO ASTM standard, how many categories of AM are there? So many. So how many agree with 7? You said what? 18, huh? 7. You also said 7. So all of you said 7. That's the correct answer. But yeah, not difficult to give certificates to all of you. Okay, continuing with the same question. FDM, fused deposition modeling, and FFF, fused filament fabrication, are examples of which category of AM?
Material extrusion.
Okay. So
John.
Yeah, John. Huh? John. Okay. Huh? Better to distribute the certificates. No, don't worry. You can answer. Okay. Okay, this is also easy. So, why AM products or components are mostly considered as near net shape products? Yeah.
They need to be machine learning for a better service.
After the processing, yeah. Down.
Abhinav.
మీరు ఎలాగంటే మీరు అసమానం చేసినట్టున్నారు అది I might miss him, no? He's If he doesn't get a prize, difficult. Huh? Okay. Dr. John from DRDL in his talk mentioned that one important alloy powder is certified for AM processing.
IN
718, yeah, but I think he already. Okay, that's correct. Okay, this also is easy. What is the type of stress that we find in front of? I feel like changing. Huh? In front of what? I didn't complete. Okay, we'll go to the next question then. It seems trivial. Actually, the question was different, but anyhow, the answer is the same. Okay. Name the 3 AM processes that are exclusively classified as processes for purely metallic materials. No, wait. There are yeah. Okay. Same answer? Okay. But you got the any sir? Please note down. Name. Suresh. Okay. I think the questions are too simple, huh? Or they were attentive. That proves that they are attentive. Or maybe I made the questions in such a way that we prove that they are attentive. Okay. For large area AM components, what is the best combination of energy and feedstock? For large area, arc wire, yeah. Should we give her the write down your name? Yeah. No, let me finish. Yeah, last question. So the idea was to give as many as possible, but I see that the answers are distributed among only 8 or 7 students. Okay, this is a little tough. With respect to the thermal history during AM, such as VAM, what is change of consequence? Professor Surya in his talk made what do you mean by change?
Change in microstructure.
Change in microstructure.
Oxidation. Defects.
Distortion. Softening.
Oxidation.
Oxidation too.
Yes, sir.
Can be considered impaired rascal. I think that's it. You want to ask? Huh? Yeah, why not?
So in powder bed technology, the optic head technology was mentioned. So there are two types of optic head I mentioned. You have to tell both, not one.